very easily between theory and algorithms. And just a little tidbit I'd note about him: he's trained as a theoretical physicist, and his PhD advisor at Cambridge was Stephen Hawking. And I'm sure you're not yet tired of listening to that particular piece of information. So go ahead, Alan. Thanks for being here.
Okay, Anuj, thanks very much for inviting me here. Please let me know if I'm speaking too loud, too softly, or too slow or too fast. So I'm going to it's going to be a fairly high-level talk, but I'm hoping it's going to give people an overview of some areas of vision and show a lot of the sort of excitement involved in it. So I would say vision is extremely exciting, challenging, and interdisciplinary field of research. And I guess during my lifetime, I've sort of seen it develop from an area where big conferences might have about 100 people. And now you've got conferences which are now tens of thousands sometimes. It's been very interdisciplinary, and it's really succeeded by borrowing and adapting techniques from many disciplines: mathematics, computer science, statistics, engineering, and so on. Adopting these techniques, learning them, and then sort of developing them for vision applications. When thinking of what to discuss, I thought, well, there were so many things to talk about, so I went back to a summer school that I helped organize in 2013 in vision, and that required 71-hour lectures just to cover what the basics we thought should be covered at that time, or could be covered. And in fact, the whole program is available online, so some of it's dated, but other of it has not, so maybe some people would find this of interest. One historical comment about it is that, when we were making up the schedule, I took a chance and decided to get somebody from a rather obscure area called deep networks, which at the time people could not get their papers published in computer vision conferences. But I thought there was something interesting in it, so I persuaded Rob Fergus to give talks. And of course, I'm very pleased I did, because deep networks shot off immediately after that, thanks to Rob Fergus, Jan LeCun, and others. Vision, of course, is extremely practical. You have automated cars, you have face recognition systems, medical image analysis, so it's starting to work. And as I say sometimes, be nice to your students, because every student you have is a potential billionaire. Okay, so what techniques were involved? The summer school was an attempt to provide core techniques. So just a brief list here: filtering, geometry, differential equations, harmonic analysis, probability models, machine learning, many more. Machine learning, this was from the workshop title, but machine learning is a vast field which includes deep networks, support vector machines, many other things, sparsity optimization theory. And it also discussed interactions with related disciplines like image processing, machine learning, and biological vision. So since that's still up, it may be a resource for people looking around. Now, my personal motivations, yes, it was said in the introduction, I started academic life as a theoretical physicist trying to understand basic laws of the universe. And so when I moved to vision, my motivation was slightly similar, thinking that vision, although it seems deceptively easy, is a really fundamental problem. And it's actually, if you think about it, it's amazing that humans can see at all. So to get vision algorithms that work at the level of the human visual system is really, in a sense, ridiculously ambitious. Vision is humans' underappreciated superpower. We get information about the universe from distances of a fraction of an inch to hundreds of light years, hundreds of thousands of light years probably. I'm out of date, but we take it for granted because we can do it. Yet, animals, cats, dogs can't get information from static images at all. Almost no other animals can, except monkeys probably. And humans are good at vision because our brains devote an enormous amount of our brain to doing it. roughly half the neurons in your cortex are doing vision. And so to try and get vision algorithms to work as well as humans is almost like trying to work out how half your cortex works, which is why it's so ambitious. Why is it difficult? It's difficult because it's an inverse problem. Interpreting images requires inverting the process that generates the image. In these days, inverse computer graphics. I guess when I started, computer graphics was not a very advanced subject. You know, there were conspiracy theories which said that the moon landings had been faked by the Americans using computer graphics. But anyone who knew computer graphics at the time would know that it was far easier to send a rocket to the moon than to use computer graphics to fake it happening. Computer graphics has made enormous improvements since that time, but it remains challenging. Why? The same reason why vision is challenging, because of the complexity and ambiguity of images. So the set of images is infinite. The set of possible scenes is combinatorially large. So here is just a thought experiment. If you take a single object, you look at it from a range of different viewpoints under a range of different lighting conditions and a range of cameras. And for each factor that generates the image, you allow it to have 1,000 possible variables. If you do that, you find that for a single object alone, that you need 10 to the 39 possible images to represent what it could look like from all different views, all different lighting conditions, etc. This is huge. Okay, this is just to make you think, and I'll come back halfway through the talk to say why these things are important. The set of possible scenes is combinatorially large. This is an example of a scene with humans sitting down on a chair, another human walking by with a bag. The sort of information that a human could get out from looking at this is, you know, you could pass the scene, you could describe all the objects, what's happening there. This person is sitting down, this person is walking. And this is a slide I think I took from a grant proposal from my ex-colleague Song-Chung Zhu at UCLA. So images are infinite, set of possible scenes is combinatorially large. There'll be implications for that later on. For now, the talk is vision as Bayesian inference. I guess when during my career, I've been members of several different departments. At one time, I was a professor of statistics. At that time, there were certain issues about whether you are Bayesian or non-Bayesian. And I'm sure Rama can remember the same things. And there were sort of historical fights and great big arguments. But I have to say, I've always been a Bayesian ever since I learned about it. Although I have to admit, partly for religious reasons rather than practical ones at the time. And here is an example of how you could apply Bayes to vision. This comes from, I think originally from Pavan Singhar at MIT. You have an image. This image, if anyone looks at it, you would probably see it as a cube. I don't think anyone would see it as anything else. But if you think about why you see it as a cube, it's really quite problematic. So if you think about it from the point of Bayes' perspective, the posterior distribution of the object S given I is given by Bayes' formula. The likelihood function by itself, P of I given S, rules out many interpretations of the image. This image here could not have been generated by a sphere or by a cylinder or things like that, or any other type of objects. But still, there's a whole lot of objects that could have generated precisely the same image here. So the likelihood function rules out a lot of things here, but it doesn't rule out all of them by any means. There are too many possibilities. A prior is required, P of S, and the prior, to explain this effect has to say that other things being equal, you think that cubes are more likely than anything else. So this is sort of a conceptual idea. Can this be extended to real images? If you do it, has a whole lot of challenges. You'd have to define probability models that are rich enough to generate realistic images, and then you'd have to do inference on them to find the best interpretations. And some time ago, quite a long time ago now, I've seen two really genius level mathematicians, very big names, have a heated argument about whether this was practical or not. You know, one of them saying the problem with you, you know, is, you know, particular mathematician, you become so famous that nobody dares tell you when your ideas are crazy. You know, and putting probability distributions on images is crazy. You can't think about doing it. Anyway, so it's a very big challenge to do it. And I'll get back to it later on. So now though, so Bayesian inference, but of course, most people who think about vision these days will think about deep networks. Deep networks are, you know, incredibly successful, incredibly well known, and you can read about them in the New York Times or other places. So from the perspective of statistics, deep networks are learning distributions, probability of states given images, which are expressed in forms of particular functions, f of the state, f of the image, etc. And these functions have nice properties. They're differentiable in terms of the weight, so you can use stochastic gradient sense to measures to do it. And so this is really, in a sense, nothing more than sophisticated regression. The chair of my department, Jan Deleur, at statistics department at UCLA, used to say, yes, everything is regression. And often Jan was very often right. So if you take a deep network, you have this parameterized model, and given a well-specified domain with annotated training data, deep networks will perform incredibly well, much better than anything else that we had before. So ImageNet challenge, illustrated over here, you have a number of objects, images, and you want to say what the object is. Is this a dog or a cat or a car or something like that? And so there is this large data set constructed by Fei-Fei Li at Stanford, and you train deep networks on it. You have a test set, you have a training set, etc. You don't mix them up, of course. Essentially, you train regression models of this particular form. This is the performance down here. There was a big jump around 2012 to 13 where deep networks started working. Before that, the computer vision community didn't take them very seriously. After that, deep networks got better and better until now, well, this is 2 years ago, you're down at 2.3, and this is claimed to be humans. Humans are now up at 5.1. So people can get very excited by this, and they should get excited by the performance. The issue about whether deep nets are really beating humans, however, is something I'll return to. So deep networks can do wonderful things. You have these balanced annotated data sets. And one example of a sort of practical work that I do in collaboration with experts at the medical school at Hopkins is to do early detections of pancreatic tumors. So here you have computer tomography scans. This is set up for deep networks. You have yellow areas, which are annotated by our colleagues in the medical school to say where the pancreas is. And red would identify a particular tumor in the pancreas. In case you don't know, getting a tumor in the pancreas is a really bad thing. You do not want this to happen. They're usually detected late, and if it's detected late, it's probably going to kill you with very high probability. So this motivates the idea of trying to see if you can detect these tumors really early when they're tiny, because if they do, there's a chance that you can get a surgeon to go in, remove the tumor, in which case your survival rate goes up enormously. So this is really the situation where deep nets are very good at, provided, thanks to having good annotated data from colleagues. You can get results about how sensitivity and specificity you can get in these domains. The performance is generally getting very good, approaches the level of an expert radiologist. And I would say that we don't, unlike a somewhat notorious video where Jeff Hinton was predicting that radiologists would be replaced by computers, from my experience here, I'm not arguing that. I'm saying more that radiologists will become experts by having these computer systems available to help them, and the experts, radiologists, will become super experts. So I think these methods will lead to, increasingly better performance on, pancreatic tumors and other things, and has the potential of saving a huge number of lives. So there were huge successes of deep networks, and I should say that deep networks are not sort of like a fixed target. What I described there was sort of classic deep networks, which are essentially very sophisticated forms of regression. But there were recent innovations, recent inventions. There was methods of doing unsupervised learning. So you could learn the bottom part of deep networks, the feature vectors, by defining a surrogate task which doesn't require any annotation at all. And some of these unsupervised learning algorithms essentially learn very good features, vectors, and then you can classify objects in ImageNet using rather simple classifiers, just using these features. Requires far less training, etc. Another one is neural architecture search. Originally, deep networks had fixed architecture, and certainly when things like AlexNet came along, that was the first big deep network architectures that succeeded. People like me thought that maybe, Jeff Hinton's been very clever. He sort of learned a miraculous architecture, and you have to have exactly the same architectures that he had, or the whole thing won't work. But now, with neural architecture search, you can design ways that you can learn architectures from subcomponents and stick them together. And you can learn architectures which are better than ones that are hand designed. We had a practical example of that in the work on pancreatic tumors, where we designed a deep network to do things. We did neural architecture search. There's also adversarial attacks by giving imperceptible changes that seem to fool the networks, but then was later realized, particularly by people like Madri at MIT, that in fact you could defend against them and you could produce robust features, and that improved performance on many tasks. There's also things like neuromodular networks, and then in natural language processing, transformer networks. So it's a very exciting, dynamic field. There's a recent opinion paper I mentioned, which I just say because it gives pointers to the literature, which is vast at these stages. So they're innovative, but now to get back to my own, original motivation, I want things to work at the level of human performance, and you have to admit that deep networks start having limitations. If you give a deep network an image here of a car and you put a lot of occluders in front of it, like this bottle and this bird and this animal, etc., the deep network performance starts degrading. You can also change the context. You give this monkey a guitar and the monkey turns into a human, according to the deep network, presumably because the deep network has never seen a monkey with a guitar, but it has seen a human with a guitar, and monkeys and humans look fairly similar. Similarly over here, you have a penguin. You give the penguin a television set, the penguin turns into a human. I can't help pointing out that these two images were created by a master's student who started working with my group back at UCLA, and I was so impressed that he came up with these things that he became a PhD, and he's now about to become a professor at University of Santa Cruz in January. Another example over here are what you can call patch attacks. So you take the images here, you put in a little tiny patch, and this can cause the deep networks to perform really badly. I mean, these cannot just be any old patches. There's a rather sophisticated algorithm to select patches and put them in there, but nevertheless, these small changes, which would not affect a human at all, will cause current deep networks to make big mistakes. So in general, current deep networks are not robust to changes in images, which would not fool humans. Now, why are they non-robust? This gets back to the point I made at the beginning, that set of images is infinite, set of visual scenes is combinatorially big. So as good, researchers, I mean, this would apply to statistics, it applies to machine learning. You think that you should train algorithms on finite-sized, balanced, annotated data sets. You train, this seems good science. You train on one set, you test on another. They are assumed to be examples from the similar underlying distribution. There's a whole lot of theory underlying this, probably approximately correct theory, etc. Cross-validation methods, all those things sort of relate to these assumptions. But there's a big problem for vision. The set of images is infinite. The set of scenes is combinatorially complex, which means that finite-sized data sets are probably not representative, because you're trying to represent something that's combinatorially complex by something that's finite. Very hard to do. In restricted domains, it could be possible. So like in these computer tomography scans, I could believe that, that it's no longer combinatorially complex. The set of images is big, but it's, it's not as big as, it's not combinatorially complex big. Your internal, everyone's got, roughly the same internal organs. They look very similar. Okay, you can have tumors and things, but tumors look like other tumors. You're not faced with a huge combinatorial problem, but you are in the real world. You are if you take algorithms that are trained on ImageNet and you want to apply them to real images. The data sets, however big, invariably have biases which deep networks can exploit. So one reason why deep networks, well, I guess there were two reasons why deep networks appears to outperform humans on ImageNet. One reason is that deep networks can learn the biases in ImageNet, which humans cannot use because they're biases. For example, if there is a tree, if there's an object in a tree, a deep network in ImageNet will think it's a bird, because in ImageNet, the only objects in trees are birds. A human will know it could be a bird, it's probably a bird, but it could be many other things. The second point is that for some of the objects, humans simply don't care or aren't expert enough. I've got a computer vision app which surely uses deep networks that can learn to recognize plants, that recognizes plants in my garden far better than I can, because I'm not a gardening expert. But they can't recognize it better than my gardener. So it means that performance measures on finite-sized data sets can be misleading and may not reflect how the algorithm will perform in real-world conditions. So the pros and cons of these methods: deep networks are amazing techniques that sometimes appear to be superhuman, but in light of the infinite space of images and combinatorial complexity, I would say we need more challenging ways of evaluating algorithms like deep networks. Perhaps adversarial examiners which probe for weaknesses of the algorithms by having a dynamic training set instead of a fixed set. If you have a dynamic training set where you can change your images depending on the algorithm that you're testing and the performance the algorithm gives you on a subset of images, then you can essentially deal with combinatorial possibilities. And I should mention that this is not merely an academic problem, because flawed performance measures can lead to unrealistic expectations. Some poor person can set up an automated car driving system thinking that deep networks have solved object recognition because they perform better than humans on ImageNet. And that poor person is going to go bust because that's simply not correct. Another purpose is that results on biased data sets can have bad societal consequences. And there are many examples of that, of abuse of face recognition systems, which work badly on certain minority classes and things of that sort. So the same paper that I put up, which gives an overview of certain deep networks, also addresses those points as well. So now for the rest of my talk, however, I want to get back to generative models, and I want to mention two robustness challenges and which the current deep networks, which are purely regression, have difficulty with, but where generative deep networks that we'll describe do a lot better. And so I'll go back to the issue of classifying objects which are heavily occluded and classifying objects despite the patch attacks. The patch attacks are these small patches that could cause the deep networks to fail. Now, thinking about it from the point of data sets, both are situations where the statistics of the test data differ from the statistics of the training data. You test, when you classify the objects which are heavily occluded, you don't train the object detectors with images that are heavily occluded. And similarly over here, which you've tried. So strategy was to bring back generative models, sort of Bayesian ideas, make them generative on deep network features instead of the images. This means that you're taking advantage of the fact that deep networks are very good at generating features. It means you don't have to go to the trouble of doing generative models on image intensities, which indeed is very difficult, and also unnecessary, because lots of the details at the image level are irrelevant to the task of classifying the object. So here, examples of image objects which have occluders in front of them. This happens all the time. Occluders can be highly variable and exponential complexity. Vision systems, the argument, should be able to generalize to exponentially complex domains. Deep networks themselves are not very robust to these things. You can see their performance as the amount of occlusion increases, it decreases. Okay, so the first thing you think about if you're a deep network fanatic is, okay, give it more data. If you do, the performance gets better, but doesn't, still not so good. Now, why do I argue that's not the right thing to do? Well, I argue because the number of ways you can include an object is combinatorially complex. You can't give them enough data to train for all those situations. So here is a deep network, a series of feature layers that you've extracted, and then a decision process level, fully connected classification head that makes the decisions. Okay, and here is the top level, because this is what we'll be dealing with. You have a set of feature vectors, h and width. You have a set of feature vectors up here at every position, and this is a representation which the deep network learns and then tries to classify. So the generative model is simply to say, okay, let's take that part of the deep network, let's take those features and go back to probability distributions, things that are taught in statistics departments, probability, mixed distributions of feature activities, etc. And here are the equations. No time to go into the details of them, but it's basically you're having generative models of feature vectors, fairly simple ones, And you then have a network which has the deep network thing to give you the feature vectors, a process here to extract kernels. Then you have mixtures of, for each object, you have different views of the object, and you have generative models for every view. This, I should say, doesn't require any more supervision than the standard deep network. Everything here is learned in an unsupervised manner, but everything is purely generative, okay? And this means that just by doing this, you can take a deep network, you can make it generative just by adding this top level, and the inference is the same as the deep network. The training is a bit more complex because you have to do not only back propagation on the deep network, you also have to do clustering, but it's not that complicated. And if you do this, you have an alternative to a deep network. Now, is this good? Well, if you just use this, this is not going to be any more robust than the standard deep network on with respect to occluders or with respect to patch attacks. It's just doesn't have that ability. What it has is it's more interpretable. If it detects an object, it will know, it will estimate the viewpoint, and also down here it will estimate the features. Okay, but it can't deal with occlusions or patches. However, as a generative network, you can modify it easily so that it can. So there's a whole area of robust statistics that I used to study, from people like P.J. Huber and other people, and there are various ways of doing robustness. But one way of doing robustness that works for us here is simply saying, okay, sorry, I forgot, before I get here, there's interpretability of these layers to some extent. The activity of the patches here correspond to parts. The activity of the mixtures correspond to viewpoints, or in this case, bicycles with two wheels versus, for one person versus two people. But the point here is to say, if you have the generative model, you can go back to one of the classic statistical ways of making robustness, is you put in an outlier model. You say there's a probability that a feature vector at a particular position is generated by the object, or one of the objects from one of the mixture views, or is generated by something else. Right, the something else is an occluder, anything that is not part of the model. So this is very easy from a probabilistic generative point of view to do this, okay? So what should the occluders be? Well, the occluders could be anything else that could happen in the images. So there is the point, just doing a probability model, use the deep network to give you really nice features, because that means you don't have to bother to model the details of the image, which are irrelevant. Then you can have a fairly simple generative model for each object, for each viewpoint, which has some degree of interpretability. You can throw in an occluder process, which can deal with outliers with a variable ZP, taking value 1 if it's generated by the object, taking value 0 if it isn't, and you can do standard inference on this to decide, for each image which object generates it, which pixels in the object are generated, which pixels in the image are generated by the object model, and which ones are generated by outliers. So here, included object, and these things here are the model's ability to detect the outliers, the occluders, by switching them on. So it's not perfect, but it does detect more or less the tree, the bar, the head, etc., like that. Now with a deep network, the standard ones don't have any occluder processes. They don't know that some of the data comes from a different model. It doesn't come from the object they're expecting, it comes from something else. There's nothing in the standard deep network to deal with that. But it's very easy to do it using this Bayesian formulation. You can evaluate it, you can put in synthetic things, etc. And, you know, and you can validate, you know, you can classify these things fairly robustly with the deep networks. Even if you take all different types of deep networks and various tricks, you're doing very well if there's no occlusion. But as soon as the amount of occlusion comes up, these generative models, which have this explicit outlier process, which enables them to make them robust, do considerably better. And you can do it for object detection. And finally, for an example here of the patch attacks, to remind you, here are the objects. And, you know, without the patch attacks, and the patch attacks, these tiny little patches in there, these attacks are incredibly successful against standard deep networks. I should say these are black box attacks. You do not need to know the deep network that you are attacking. You only need to know its output, but you don't need to know anything about its parameters. And if you do the patch attacks of this sort, for the VGG networks, the patch attacks, there were two types that we tested on. One type of patch attack is successful 98.8% of the time. The other one is successful 92.3% of the time. These are so-called targeted attacks because it means you can turn the car into any target you want to. And this is how often you can do it on a standard deep network. If you take these generative models using these Bayesian ideas and an outlier process, you can still be attacked in this way, but the success rate of the attacks goes down to, you know, order 10%, 12% for this type, and 0.9% for that one. Also, the comp nets, you know, this is a generative one, perform slightly, a little bit worse than the deep networks when there's no occlusion, when it's a pure standard regression problem, but they're very close, and this generalization is important. I had a second part of the talk here, which I think I'll skip over for reasons of time. This was to say about the advantages of using computer graphics, so it will be up there. The idea of learning, of saying that humans, just to throw it out, I'll make one point, humans are the only visual system that we know that can do visual tasks well, and humans do not learn anything remotely like deep networks. Infants play with toys, you know, infants touch objects, they, you know, taste objects, they learn in that way. And here I got an infant volunteer just to show how the infant learns. And right, he's touching it, he's playing around with it, he's even biting it. You know, I suggest this is, you know, certain evidence, this is how human infants learn to recognize objects. This is not how deep networks are trained. If you think about it, this is, you know, what is a surrogate that a human infant could learn. I would say a human infant could learn a computer graphics model of an object. If you have a computer graphics model, you could train a lot of data from it, from a single model of a horse. You can then transfer it, and you can learn to detect the horse and parts of the horse almost as well as if you had the ground truth annotation on it. So this part is incredibly short, it's quite fun, but if people are interested, the slides will be available. So let me get up to the summary. So first, vision I think is extremely interesting, challenging, and rewarding research field. I have absolutely no regrets from leaving theoretical physics to work in vision. It involves a huge range of techniques. It's very rich. Getting into deep networks, currently the state of the art. They can give wonderful performance. They're extremely innovative. They're constantly evolving. But do remember that only one of many techniques. Don't forget geometry, probabilistic generated models, and many more. The next point is that the way we evaluate algorithms in vision on finite size balanced annotated data sets are problematic in face of the combinatorial complexity of the real world. We need tougher challenges and performance metrics if we expect the algorithms to work in reality, because otherwise we will be setting ourselves up for, failure and for, biases and various undesirable things. So the second part was a bit more technical. 2 challenges, occluders and patch attacks. And since I've been I wouldn't say a lifetime Bayesian, I've been a Bayesian since 1983 when I heard talks from Stuart Geman about it, is to say that generative models can be far more robust to occluders and patch attacks than regression methods like deep networks, because they can exploit outlier processes. It's easy to do with that. Computer graphics, that's the second set, is useful because it's a surrogate for how humans learn potentially. We can learn a lot from the human visual system and how it's developed. For further information, I think, this IPAM summer school has all these slides available that may be interesting to people. This opinion paper we had was going to appear, gives us sort of attempts to give an overview of deep networks, but also raises these issues about the limitations of working with finite sized data sets and the extra challenges that perhaps we need to do. So otherwise, I've gone a little bit over time. I'm sorry for that. And so I'll stop now, and I guess I'll stop sharing the screen.
Thanks very much, Alan. That's talk, and there's a lot to learn, and I will certainly replay the session several times. So I'm sure lots of people have questions, but I will just start the questions, and then we'll see how much time do we have. At the start of your talk, you said the interest is in modeling human vision. That's one of the goals. On the other hand, we have these techniques, these deep learning networks, which are doing excellent. They're doing very well. Are they a suggestion? Are they the candidates for that human model that you started your research with, or they are just for the time being something that is doing well, but the human vision model is still a long way to go?
I would say that the human vision model is a long way to go. And I guess with my students, when writing that opinion paper with Chengxi, we were debating, the debate is, I think the deep networks give you a very good starting point for developing human models. They are extremely successful. Certainly the feature vectors that you get out from them are very good. But part of the point of the second part of the talk is to say, I think where the decision processes that people are using are limited, and that if you take things like Bayesian methods, they're far more generative and successful, able to deal with these types of complex situations and also to generalize to situations that you haven't been trained on, which is what human vision does all the time. My concern is that the current ways we evaluate data sets on these finite sized data sets gives the misleading impression that the deep networks are as good as humans or better. I think that's misleading. That's why I think we need tougher challenges. So I think you'd have to modify deep networks in some way. What I discussed in the second part was sort of one type of modification, but I suggest you may have to go a lot further than that. And for me, the issue is, do you have to go so much further that you don't call them deep networks, or do you just, is it just, do you just have to do modifications of them and so they are modified deep networks? I'm not quite sure about that distinction.
Okay, thank you very much. I think we will just move on to the next presentation. Thanks once again, Alan. It's wonderful.
All right, let me share.
To introduce yeah, go ahead. It's a great pleasure to introduce our next speaker, Professor Ramachalapa. He is, as it happens, also a Bloomberg Distinguished Professor at Johns Hopkins University, a freshly minted one. I think you just moved there a few months ago.
Right.
He has appointments in electrical and computer engineering and biomedical engineering. He's a pioneer in the field of computer vision, statistical image analysis. We have read his books on marker random fields. He's one of those rare people who can actually give you a bird's eye view of fields at any given moment. And it's a great pleasure to have him talk about sort of the bird's eye view of the field. Go ahead, Rama.
Thank you, Anuj. I have been called a lot of things, but this is the first time somebody is calling me a bird. I hope I'm a hawk if I'm a bird. If I can fly high and still spot a little whatever on the ground. Anyway, it's fun to be with you all. You know, I learned at a very young age that I like statistics. Because I was following cricket. That's one of the passions I share with my distinguished colleague, Alan Yule. In addition to being a Bayesian, we can talk forever about cricket. Of course, we have differences of opinion about which country's cricket team is better, but that is something that you don't have to know about. But anyway, so as somebody interested, as a boy growing up and you know, watching cricket, although I was not a great cricket player, I liked, cricket. But then you can just follow the statistics of various players and how many boundaries they scored, how many catches they took, how many. So, right, that's where I understood, even if I'm not good at playing cricket, just being a statistician of cricket, I can, you know, tell people, you know, what a great thing I know about cricket. So that's when I got hooked to statistics. Cricket is the one that got me into statistics. Of course, baseball lovers here would probably resonate with that, all right? So anyway, I took a bunch of graduate statistics courses at Purdue when I was there as a student, 1977 to 1981. Purdue was a powerhouse in decision theory and especially in Bayes decision theory. I'm going to mention some names: Shanti Gupta, Prem Goel, Jim Berger. They were all there, and they were also Prem Puri and Pillai and Herb Rubin and so forth, right? They were Bayesians of various hues. Some were diehard Bayesians. Jim Berger was one, and then Herman Rubin was a cautious Bayesian. He always liked to trip up the Bayesian by coming up with some crazy example how a improper prior would mess everything up. In fact, he will chuckle. There was an example where he had a Cauchy prior and showed that the risk will be infinity if you didn't do it carefully, and then, you know, he will chuckle. Those of you who have known Herb Rubin, you would know that. Anyway, so I took all these statistics courses, decision theory, multivariate analysis, non-parametric statistics. The statistics professors gave me homeworks every week. I just didn't like that. I had to do 10 problems every week. So I said, every time I get a chance, I want to give some problems for statisticians. It's just my way of getting back at you guys, okay? So, of course, I decided to choose 9 because if I miss 9, I got to do 108. I'll be grossly unpopular, so I thought I will do 9. Anyway, how can I not mention some of my great teachers, right? Professor Asriel Rosenfeld, computer vision, one of the founding fathers, and he always challenged me by saying, Rama, the only time statistics can make any impact on computer vision is if you move away from linear models and Gaussian distribution. So he says all the signal processing people play around with least squares, mean square error, and Gaussian, and no, that's not cutting it. So first learn vision is hierarchical and vision is not Gaussian. Okay, so oh my goodness, I have heard it so many times. And Professor Kashyap is a diehard Bayesian, right? He really put me into this. And the next person here is Professor Kingston Fu. This is me, summer 1981. And Kingston actually started off as a control person and then did the statistical pattern recognition. He made SPRT famous for pattern recognition people, the Abraham Wald's the sequential probability ratio test. He even came up with a multi-class version of it, but it didn't have such elegant properties of the 2-class problem. And he also did syntactic pattern recognition. He loved putting probabilities on grammar rules. So he worked on stochastic languages, right? Stochastic formal languages that Songjun Zhu has been working on ever since. And this is Professor Tom Huang. He was at Purdue and he taught me computer vision. Jas Lansky, another pattern recognition person. I actually was given his manuscript in summer of 1979. Springer said, can somebody read this? And Fu told Shalapa could do it. So I read the whole manuscript. I thought his conversation of conjugate priors and reproducing Bayesian densities was not deep enough. So I offered to write that section using the fact that if there is sufficient statistics, one can actually figure out the structure of the conjugate prior, and therefore the recursive Bayesian learning will get more computationally efficient. He was such a generous man. I was just a PhD student. He said, oh, sure, I will put it in the book, and he even acknowledged me. So Fukunaga finally is a statistical pattern recognition guru. I took his class and I learned a lot about this. So I won't be here without these teachers. Even equally importantly, I have had so many brilliant students who taught me, and they knew they had to teach me a lot, and they were very patient, taught me, and I have, I think I'll be graduating my 111th PhD student on next Friday. And so these kids taught me everything. I cleverly put myself between these two groups, and I'm pretending to kind of have a good life, okay? Anyway, gotta be, yeah, that's the smart thing. Anyway. Neural networks, deep learning networks. So, I mean, to me, statisticians should have a big impact on it. It's all about data. And Alan even alluded to the fact that it's a very sophisticated regression. That is true. In fact, if you write down the entire expression from inputs to the output label, it's a f of g of h of k of a of b of, etc., right? Unfortunately, we only have 26 characters. There are 101 deep layers. So I don't know what you have to do. A, B, C, D, and then A, B, B, et cetera, et cetera. So it's a very long regression equation. That is fine. But to me, computer vision is not about regression. Only a few problems in computer vision are about regression, pose estimation, fiducial extraction, et cetera, et cetera. The moment geometry comes into play, as Alan mentioned, it cannot be all regression, right? But this, and I'll get more to this. Anyway, neural network is like a cat. It has 9 lives. I think it is right now in third or fourth life. When Hopfield came with his famous paper in 1982 in PNAS, it got a third life, whatever. And I was at USC at that time. Everybody was very excited. And Dimitri Soltis actually built an optical system for associative memory and so on. And the first neural network conference was in San Diego in 1987. I was there. They expected 500 people, a few thousand showed up. And I got interested in neural networks in a very different way. Boltzmann machine, right? My PhD thesis was on Markov random fields, so I was familiar with Gibbs distributions and so on. And the Boltzmann machine that Jeffrey Hinton was talking about in PDP books in the mid 80s about that. So I got into the Markov random field and then, into the neural network thing. But we talked about, I worked on, actually probably wrote a first book on computer vision and artificial neural networks. It's a small monograph based on Yitang Zhao's work. We did work on stereo and image restoration, optical flow, et cetera, et cetera. And then it turned out when you have 1986 paper from Julian Bazak on statistical analysis of dirty pictures, he mentioned the iterated conditional mode approach for coming up with an approximation for maximizing the posterior. And David Cooper at Brown argued he had already done it in 1983. And then if you look at the ICM for texture segmentation, it has striking similarity to Hopfield on Markov random fields. So we looked at MRFs in that category, writing a posterior distribution for texture labeling problem using Markov random fields. And then if you do the iterated conditional mode for that, it's basically a half-field network. Army was very interested with all the buzz about neural networks. They came to us and said, can you try it on an ATR problem? We did. We implemented LANET for ATR using FLIR, and there's a 2001 CVIU paper. At that time, we didn't have GPUs. We didn't have a lot of training data sets. So learning vector quantization beat CNNs, LANET 5. So I kind of looked at it, I said, okay, fine, so we didn't pursue that. Of course, then we wrote a first paper on face recognition in CVPR 1992 with Christoph van der Malsberg. Van der Malsberg had a very interesting neural network structure. He called it dynamic link architecture, which is a generalization of Fukushima's network. We used it for face recognition. Of course, then it's, what happened with AlexNet and so forth. The rest is history, as they say. Okay. I like statistics. As an Indian, of course, you grow with large population, so you have to like statistics. And, statistics had a lot of impact on computer vision. Okay, and Alan talked about generative models. I became aware of Peter Whittle's 1954 paper, 2D non-causal simultaneous autoregressive models. because I came across a 1977 Proceedings IEEE paper by Bill Larrymore, which talk about statistical analysis of homogeneous random fields. What happens is when you have a causal model, you can write the likelihood function very easily, like autoregressive models and given ARMA and so forth. But when you have a non-causal representation, it becomes difficult to write it in the interpolative version because the determinant, the transformation matrix from noise to the observations is no longer lower triangular, so you cannot approximate the determinant vanishes. When you take a log determinant, log of 1 is 0. When you have a non-causal model, it becomes very difficult. So this is the classical issue. So you have to assume some finite approximations and so forth. So because the likelihood is not same as maximizing likelihood is not same as minimizing least squares in the case of non-causal representations, Peter Whittle actually is a brilliant statistician. He talked about the inconsistency of least squares estimate. That kind of piqued my interest, right? And then I came across Larry Moore's paper, Proceedings IEEE. That took me to Julian Bezak's paper in 1974. Of course, almost anybody who has done any work on MRFs would have read that fantastic paper. And so I read that, and that's when I became aware of the Gibbs distribution issue. And Julian had the coding estimate and so on, which was not fully efficient. So I developed a least squares version, which it turned out he had already done it somewhere, which I was not aware of. So, all of this was fantastically exciting. And Moran and Bezak had this paper. So I had a paper on estimation and choice of neighborhoods for simultaneous autoregressive models and Markov random field models in information theory transaction 1983. This was my PhD thesis. Of course, there's also a paper in 1979 in Biometrica where we had a paper on dynamic texture models. It's already there, right? Okay, so statistics had all these interesting things for us. I thought 80s were the golden decades for statistical models of images, although my advisor and mentor, I had two advisors, Professor Kashyap as well as Professor Rosenfeld. That's a story for some other day. So I had Kashyap going strong with linear models and Rosenfeld being skeptical about it every day. So I had to somehow, it's like having two parents and who completely didn't agree with each other. And so I'm like the kid who has to somehow live with them and make sure I grow and et cetera, et cetera. So that's an interesting experience, I should say. Anyway, so, of course, the Gaiman paper was big. And I think, I already mentioned this. MRFs were quite popular. We had a lot of fun with it. But somehow Peter Whittle's 1954 paper really didn't take off much, although somebody pointed out to me that model is used for predicting the value of your home based on your neighbor's home. There's something called Zolo or something people told me, and I was surprised by that. MRFs were great. My first disappointment MRF was in 1982. Asriel organized a workshop on multi-resolution image representations at Leesburg. We used to have a Xerox training center here those days. Now it's something else. So he said, Rama, you talk so much about MRFs. Why don't you tell me how the multi-resolution stuff will work with MRFs? I'm just a first year into my assistant professor thing. So I looked at it in the literature and so forth. And that became a problem. And I'm going to say a little bit more about that. But then, if you have MRFs for texture segmentation, you have to see the training set, you have to fit models, and the same thing won't appear in the test data sets, right? And we really didn't go beyond third order, fourth order model. So when you think of deep learning with 120 million parameters, MRFs look very puny, and extensions to video was hard, hierarchical representations harder to analyze. For example, even in the case of a simple autoregressive time series model, if you take an average and then subsample, it immediately becomes ARMA, and then it stays ARMA forever. So given that ARMA model, can you predict the autoregression? No, it's very hard because there are multiple, non-identifiability issues, non-uniqueness issues. Econometrics used to worry about this. So I tried to develop MRFs for multi-scale. It was a struggle. Haluk Derin and Lakshmanan came with something. Again, it was not very strongly done. Although Gidas tried the renormalization group approach for hierarchical representations, it didn't take off. So in general, hierarchical representations are hard for statistics. And that is one of the things I'm going to keep repeating again and again. When I mean hierarchical, I have a data and some convolutions, another data, convolutions, another data, et cetera, et cetera. If you put non-linearities on top of it, I'm talking about deep networks. So it's a big challenge for statistics, and we'll talk about that. Another thing is discriminative models did better. That's another problem. I'm a generative model person. Sometimes the discriminative models will come from the left side and beat the heck out of you, right? That's the problem. And so, and absence of nonlinearities. For segmentation, I worked on it and others worked on it. Holub Derin, for example. And the normalized cut came. And Jitendra, my good friend, was so proud. He said, Rama, I can beat MRFs with normalized cuts anytime. I don't need to look at the textures before, and it works well. So what do you have to say, right? Because it starts with the image and then develops a segmentation algorithm. It doesn't assume there are MRFs for the various textures, and then you put a mosaic of those textures and you will do your segmentation, right? So these are the things. So these drawbacks point to why statistics is absent in deep learning despite being data-driven. You know, this is a plenary talk, so I may say some controversial things, but I'm in general a very nice guy, very easygoing guy. Anuj can point to that. But the fact is, statistics has hell of a problem when you do 101 layers model, and statistics has hell of a problem if you throw a nonlinearity, even as simple as ReLU. Of course, if you put sigmoid, all bets are off. So that is where the real challenge is here, right? So it is odd that something that depends so much on statistics should have more statisticians in it, data in it, right? You guys know what the data is. Okay, so where else statistics helped us? Performance characterization. Again, regression models. And Bob Haralick was pretty good at that. He used to push it. Of course, you know, performance characterization is what I call the Rodney Dangerfield of computer vision. People think, oh, you can't come up with new theorems and new algorithms, so you want to evaluate. But that's important, right? So Haralick had a hell of a time convincing everybody else that it's true. Being a fan of Professor C.R. Rao, you know, we had a 1981 proceeding symposium on decision theory, the Purdue Symposium. They used to bring books on that. And so C.R. Rao came and everybody was kind of so respectful and so forth. We had an event that evening, first night's evening, I think, and Shanti Gupta, he was the chair of statistics department at Purdue. I was given the honor of driving, being a chauffeur to Professor Rao, brought him back. And I said, Professor Rao, would you please sign your book? You know, I have a copy of it. I love it very much. He said, sure. He waited for 15 minutes in the lobby and he signed it. So I have great regard and respect for Professor Rao. So we said, what can Kremer Rao do for computer vision? So we developed all kinds of bounds for structure from motion and so on. In fact, we were able to evaluate the bias in estimating depth when you use a single monocular video using Kremer Rao bound, which was substantially approved by psychophysics researchers and so forth. When you do depth estimation using a single monocular video, where is the bias and so on. So the numerator. So, statistics is useful, right? Of course, if you have linear methods and so on. And we also used a bunch of these kinds of things. Peter Meir, who used to be with Azrael, we had a workshop on robust statistics in 1989, and least median squares was big because RANSAC was being used a lot for fitting problems in computer vision. So somebody had to worry about what happens if there are outliers. Least median squares had this interesting result. You can have even close to 30-40% of outliers and you can still survive. So robust statistics was in computer vision. And I developed some influence functions and so on for 2D power spectral estimation using Markov random fields. Of course, I came across my good friend Anuj Srivastava, and Anuj had the, I would call it an honor of working with Wolf Grenander. I tell you how I came across Wolf Grenander. When I did that work for Sklansky, that book, Springer gave me books worth $1,000 because I couldn't take a check. I was an F1 student, and I immediately bought the pattern theory book of Grenander. Something told me. I looked at the thing, I said, oh, this looks cool. I can't claim I understood all of it, but at least I had those books. I still have them, right? Of course, there is a new book with Miller, my friend and colleague at Hopkins, and so on. So I enjoyed working with Anuj. The Fisher-Rao metric we showed for activity recognition problem. I have a simple example in the next thing. And shape statistics. I'm afraid to say anything about it when Anuj is in the audience because I will look like a fool, so I'm not going to do that. But we had to worry about circular statistics. It's statistics on manifold if you want to estimate vehicle orientation because 360 degrees, so things have to close. We have an IJCV paper, and then we did some statistical learning on manifolds and so on. So manifolds are pretty interesting for computer vision. We did a Riemannian statistics for figuring out joint action in a football scene where people move with respect to each other in terms of what everybody is doing. So there is a correlation. And this is the work I did with Anuj, action recognition using contours. We will go around the contour and sample points and normalize them and put them on a sphere. And then, Fisher-Rao metric came. The only other computer vision person I know who uses Fisher-Rao metric is Maybank, Steve Maybank, And you can see, depending on different actions, they will map onto different parts of the manifold. And so that was all very interesting for me. Of course, Bayesian, Alan talked a lot about it. I got introduced to Bayesian thing because I wanted to develop a Bayesian information criterion for ARMA models. Kashyap did it for AR, October 1977, but every time I talk about BIC, I got to mention Kashyap's paper because not many people know. Everybody cites Gideon Schwartz's 1978, the small correspondence paper in BIC, but Kashyap is the one who did it first, 1977. In 1980, automatic control, he even had a very simple proof proving the inconsistency of the archaic case information criterion. Anybody who's interested in learning how to evaluate probability of error for a classifier, that's the correspondence you have to read. And, Alan talked about Bayesian models for object recognition. David Cooper spearheaded that. He really worked on it for many, many years with his students, Ruth Bold and many others. And of course, what happened in those days is that the priors are hard and likelihood is fine. And then when you want to integrate it to get the posterior, most of us, we just use the Laplace approximation and so on. Okay, so yeah, we wanted to use a hard prior, but we said, gee, we can't really integrate and get the real posterior. So we will, drive the likelihood Gaussian approximation. This is called Laplace approximation. I learned about it when I did the likelihood for ARMA. Likelihood for ARMA is also a beast. So if you want to throw a prior and integrate it to get the Bayes information criterion, of course, you have to use Laplace's approximation. I didn't know it, but that name, it was given to me by my advisor in a book by Asymptotic Expansions by Erdely. Some of you may know about it, Asymptotic Expansions by Erdely, that has this Laplace approximation. So we did some of that. So David Cooper gets the credit for that. And of course, Grenander, this is Grenander's school. Of course, we have Bayesian graphical models, Daphne Kohler, et cetera, Julia Pearl, and simulated particle filtering, MCMC, and so on. Interesting thing is, SVM became very good, and RVM, which really has the Bayesian interpretation, relevance vector machine. It's a hierarchical Bayes. Nobody talks about it much. I thought Tipping's RVM is actually more pleasing to me than SVM, but that is life. You develop things and etc. Statistics is struggling. Okay, what happened in computer vision is we had a period from 2005 to 2012, sparse representations, dictionaries, compressive sensing, and so on. And statistics was kind of barely present there, right? So I think, in fact, I would argue right from the 90s onwards, when hierarchical representations like Gabor filters became popular and effective, JPEG 2000, statistics kind of went behind a little bit because statistics has difficulty of dealing with these tower models. It's good for ramblers. It's not good for skyscrapers. I mean, I'm saying this, if there is some reaction to it, I'm happy to hear that, right? Deep learning is 101 layers. It's like a New York building, whereas Rambler is a single story, right? So, and also in the compressive sensing, there was L2 was not good. Really, we wanted L0. And then, of course, we got scared of it because of the NP complete issues. And so we went to L1, okay? So that is, then once the L1 comes, statistics is good. I mean, you can talk about the Cauchy and things like that for L1, but some of the theoretical properties are kind of hard to prove. So statistics was struggling here. Again, hierarchical models. I told you, multi-resolution pyramid was easy to build. You couldn't theoretically analyze it, but it was easy to build and analyze. Gabor, yeah, you can put the scale, you can put the orientation, you can develop multi-level hierarchical. The statistics, it was different. And of course, if you throw nonlinear ReLUs, it's even a problem. So I'm calling it deep learning miracle or mirage. Okay, Alan made good points about that. Since 2012, computer vision has become a one-trick pony. CVPR, everywhere is deep this, deep that. Okay, fine. It works well. We built a fantastic face verification system. We have given it to the government, 5-year effort of IARPA, Janus. So I know it works when things are correct, but it has issues too, even for a face recognition, right? So there is a follow-on program that they are talking about, Breyer, where they want to do it for 500 meters and 50-degree pitch and so on. In fact, the reason why we are even thinking of doing that is because deep learning has shown face recognition systems can be built. There are bias issues, there are all those issues, but when it works, it works. I mean, this kind of performance at 10⁻⁻⁷ false acceptance rate, 90% true acceptance rate, I never imagined it when I first started working in 1992, okay? But there's another problem we are working on. We are struggling, and Alan was part of that team problem too. For action detection, probability of miss for the best system is 0.5. That means I'm only 50% good. You can't deploy a system with that in a known facility. And then same actions in an unknown facility, I'm 71% wrong. What can you do? So deep learning doesn't solve everything. Deep learning is good for certain. I like to say when there is a mapping between data to label is unambiguous, deep learning is good. Don't go any further. Get the data and get it done. But anytime there are issues outside that, you really can't say much about it. So these are the kinds of actions. These are trimmed videos. In fact, action detection is untrimmed videos. There's a big parking lot, like here, multiple things happen. So you have to know where and what, right? And so it's a real problem. And we are in phase 3 right now, okay? So don't let people tell you that deep learning is a panacea for all problems. DIVA is a great example where we still have to do more work. And Alan talked about humans and machines working together. We did experiments with forensic examiners, a face verification system. There is a PNAS 2018 paper when best human forensic examiner works with the best face recognition algorithm from Maryland. It's really outstanding performance. Okay, so it's, DOJ knows that. Okay, now, despite being successful, deep learning methods are weak because we really don't know a lot. All theoretical results I'm seeing are for 3 layers, 2 layers. For example, scattering networks from Stefan Mala is beautiful, has more explainability, more interpretability, and so forth, but it doesn't go more than 5, 6 layers, okay? And to me, when I took a pattern recognition class way back in spring 1977 with Professor Tata Char at Indians of Science, we had to learn from chapter 3 of Dura and Hart, estimation of covariance matrix. And the thumb rule was for a D by D matrix, there are D into D plus 1 by 2 independent components. So you should at least have 3 times that number of samples to estimate a good covariance matrix. Okay, well, here we have 120 million parameters in deep learning and we have not that much data. So the whole idea that you can learn, so the statistical estimation theory is absent. Theory of point estimation by layman is not there here. We just have this optimization algorithm, SGD works, everybody is happy, SGD works, okay, fine. But nobody really says, oh my God, why are we learning so many parameters for such small amount of data? What are we saying, okay? So that means it tightly clings to the training data. You cannot wean out a deep learning network from its data. You cannot, that is the problem. Of course, we don't know, and I can pile on. I don't want to do that, okay? So what I'm going to do from now on is going to start giving you problems for statisticians. And I don't know, I'm going to give you some kind of a homework and maybe a deadline, do and see what kind of answers you have. All right, first thing I want to do, Alan mentioned it, domain adaptation. This is an old problem with a new name. When you train something with a data, a classifier, and then you have to test it, if the distribution of the test data is different from the trained data, you are going to be in trouble. This was nicely showcased with an example by Case Yenko's ECCV 2010 paper, simple objects, cups, shoes, and this and that, taken with 3 different cameras. You train using one, test on the other, the performance went down. Well, we were surprised by that. Anyway, we looked at it. My student Gopalan looked at it, okay? So then he came with an idea in 2011 ICC. You know, a very interesting idea. I always say, don't bet against hoteling. Now, hoteling's 1931, principal component analysis, right? Okay, here we have a problem where training data has labels, test data has no labels. So we call it unsupervised domain adaptation. You know, if you don't have labels, you still want to build a matcher. What is the method you can use? Principal component analysis, Pentland, eigenfaces, right? No ID. Take all the pictures, align them, get the covariance matrix, keep top 300, 200, whatever eigenvalues, get the eigenvectors, build the transformation matrix, and then express every phase you have in your data set on that eigenset. Given two pictures, you project onto the eigenbasis, get the coefficients. If they are close by, you are done. I never used any ID there. So principal component analysis, while is being the simplest of these methods, that really doesn't need ID. Okay, so we said, since target data doesn't have ID, maybe we should now do a subspace thing and put the target data as well as the source data on the Grassmannian manifold. We know where they are sitting. You can interpolate between them. And then at that point, you can create intermediate principal representations. And then you project both the target and the source data along that, get your feature vector, you classify, because you know the labels on the source target. It's a very simple idea, okay? Because it's unsupervised domain adaptation. I didn't want to do semi-supervised, unsupervised, and the principal component analysis allows these kinds of interpolation. It's almost like you are creating many intermediate eigens images. That's what it is, right? But analytically, not supported by samples. We did it for finite, and Gong et al. Just looked at it. We had this paper in November 2011, the next paper in CVPR 2012. Within 6 months, they added another couple of sentences to the software and so forth. So we did that, all right? And then we said, okay, we are dictionaries. And then I told my students, guys, hierarchy is important. Dictionary, put the hierarchy. Don't be a rambler. I said, build skyscrapers. Don't be a rambler. That's what I said. In vision, hierarchy is important. Otherwise, you're going to just deal with intensity, right? So we built a network. It had all the characteristics of, the neural network kind of thing, max pooling. By the way, I'm going to tell you something very funny. Yeah, I fell off the chair when I saw that. I bought this book, deep learning book by Goodfellow and Corwell and Vengio. And I'm patiently reading, and I go to chapter 9 and page 330, it said max pool. Believe it or not, they cite my 1988 paper with Yutong Zhou on optical flow stereo, one of them, as for max pooling. I said, wait a minute, that can't be true. But anyway, that's just a hilarious story. But if they say I suggested max pooling early on, I don't have to deny that. I'll accept it. Although Jeffrey Hinton has expressed opinions doubting max pooling, so people can argue. But anyway, max pooling is there. We did that, and then and then GANs came. So 2018, we did unsupervised domain adaptation. Okay, the idea is just like GAN is mediating between real and fake data, it can now mediate between source and target data. Okay, now you see the next slide. You know why GANs are popular. I did the beautiful differential geometry, stuff that Anuj and I have, Anuj taught me, so to speak, statistics on differential geometry. He's a leading computer vision expert on that. When we did that manifold, look at the numbers here. And then we did dictionaries, it got a little bit better, not so great. And then we used deep features in the same way and it got better. I go to GANs, the same data set. So for the same data set over a period of 8 years, GANs are doing. And this is a scary thing because, okay. So domain adaptation, unsupervised domain adaptation is still a very important problem. All we are showing is still on small data sets. So this is a great avenue for statisticians to play. Well, domain adaptation assumes both source and target data are available at the same time. What if you only have source and no target? Well, then you can do domain generalization, right? This is also a very important problem that statisticians should look at. Then what we do is we have multiple sources, and then we try to figure out as much as we can from multiple sources and then regularize and to be able to be ready when a totally new data we have never seen comes. I think that should excite statistics folks. I'm sure there is already generalization issues that they worry about. So problem number 2 is domain generalization, and I have a Nourif's paper. I will refer you to that. Problem 3. Okay, you have 101 layer, 151 layers. Somebody told me there is a 4K tall deep learning. I think Abbott at Virginia Polytechnic built it. I have not seen anybody using it. But so, I mean, where is the thing? You do 151 and then somebody does 198 and yeah. Okay. But we need the idea that, you know, these things are wild, were even known in the late 80s. That's why you had papers like optimal brain damage and things like that. People talked about dropping weights and so on. Because, you know, if you kind of say, hey, you know what, I have only this much of data, but I can build this bigger model, there is some kind of thing you have to be a little shy openly claiming that, right? Because statistics says you have a certain number of parameters for estimation accuracy, and then you turn everything around and say, I have this much data, but I want to build this bigger model. Okay, so pruning has to be done, but we have no idea. I mean, when we do statistical hypothesis testing, we ask the question, you know, hypothesis testing, whether the parameter is 0 or not 0, we set up the likelihood and significance levels. Yeah, none of that is working here because, again, nonlinear. The other thing, there is the thing about, oh, if you learn from noisy data, you will generalize well. Yeah, well, of course, when I order a soup in a deli, you know, it needs maybe a little bit more salt, but that doesn't argue for continuing to add salt. Or in India, we used to say snake charmers will take a little bit of a venom of cobra so that they get strong in case when they catch a cobra, it bites them, they don't die. But did they know how much venom they have to take every day to be strong? Right? They don't. So we don't know how much noise will give a robustness versus how it's going to throw everything off. Errors in variable formulation. There is actually a paper by Julian Besack in 1977. I forget whether Biometrica or Journal of Royal. It's a small paper. He talks about writing the joint likelihood and so on for Gaussian with noise and so forth. So we need some rigorous hypothesis testing procedure to come up. But I think, you know, I'll tell you, there is a piece of work by one of our Maryland students, Rastagari, where he binarized the neural network weights and achieved efficiency and so on, right? So such things are good. Now, okay, you have the hierarchical model, you have nonlinear model. These deep features, what do they represent? I'm training my deep features for doing face verification, face identification. But you know what? When I fed in my face, the detected face, I used an algorithm that not only, you know, detected the face, it also said the gender, it gave the age, it gave the fiducials and so on. I use it for classification. Immediately I find that this, my network is representing not only ID, okay, it's also representing gender. It also seems to remember the age. Actually, what you see here, this is ID. AI doesn't care for the first few layers of 101, and suddenly ID becomes big. And this guy is, you know, it keeps track of loses interest. It keeps track of gender, loses interest. It keeps track of age, and somehow age is still pretty, you know, close to this thing. So we are trying to look at it. On the other hand, there is a network that trained by Imperial College researcher Stefano Sofrilio. It does not represent a gender that much. So the reason why we are talking about gender bias in face recognition is the networks are coding not only ID, but they're also carrying as a baggage the gender with them. So when you carry a baggage like that, you're going to be biased. That is the thing that we learned. How did we learn? We used a procedure known as MIND, basically mutual information, because all these covariates, right? Pitch, gender, etc. How much is a deep feature, you know, carrying this information? So you can, you know, evaluate this using an optimization procedure. The details are in our paper, and I'm happy that I'm able to cite Professor Varadan's work because I have enormous regard for Professor Varadan, who is at Courant. Okay, so the next slide gets into detail in terms of how to do it. We have an archive paper and so on. So this is important. Okay, you know, when you build a model, a regression model, you have to know what it has in it. That's very important. And I think statisticians can help us in that. Of course, GANs have gone crazy. If you don't know what a GAN right now is, that means you have been hiding somewhere for a while. Okay, GANs are everywhere. All you have to do is just to look at the website, this person does not exist, .com, and you see beautiful faces being generated. GANs not only generate good pictures, they also generate false data, false this, deep fakes, etc., etc. And we have worked with GANs a lot, and others have done. To me, the punchline, a generative model without statistical validity is an anomaly. Okay, so statistics have to look at GANs and see what you can do with it, why it's working well. 2014, the pictures it synthesized were terrible. Now they're absolutely beautiful. What happened? How did it learn? Why is it learning? It's a min-max game. Decision theory has min-max as one of the things, right? Bayes, Neyman Pearson, and min-max. So you guys have a lot to say about that. The other one is I have lots of training data. Well, Alan made a point that finite sample data is not going to reveal. That is very true. We recently tested our face verification system. We retrained it on a 4.5 million identities, right? We know once we do that, it really became very good. It didn't have a domain adaptation issues. It didn't have demography issues. 4.5 million identity data set we used on a totally different demographic compared to what IARPA Janus program was or LFW was. But if you increase the number of identities, it seems to generalize well. That's fine. But you have so much data. Do you have time to work with all of it? Is there a best subset of the data that is useful? Again, this is a statistic problem, not losing the classifier. We had a crack at it some time ago, and we have not pushed it much, So basically, we want to know, given where the classifier right now is, what is the next best set of training data I should get to make it better? Okay, this is a sequential decision-making problem, and it fits in very well with statistics. Again, you have to worry about class imbalance. When you choose the next subset, you don't want to take 80% men again, right? So men, women, you have to do that. ID, you have to be fair, and et cetera, and it becomes like a very nice optimization, constraint optimization problem. Of course, it is NP hard, and so semi-definite programming and things like that. So I would argue this is something that you should do, and we tried it on that. What it would do is that, if I wanted faces that are different, then it will create these kinds of odd faces, because I wanted, this is like hard mining, in triplet embedding, right? But you want to get the most difficult training data set so that you are ready when the test data set is very nasty. As you can see, these are all difficult situations. On the other hand, if you say, no, I just want to, you please give me the friendly data sets to train on, because I don't want to be challenged too much, it will give you these kinds of data sets. Okay, so you have some control over which training data set you should use. Of course, the big expectation is what this would all do to healthcare. Of course, being at Hopkins, I worry about it a lot. Hopkins has something known as PMAP, Precision Medicine Analytical Platform. It has all kinds of data in it, records, the doctor's notes, diagnostic images, and so forth. And the kind of machine learning algorithm that's working on it right now, Bayesian hierarchical models, Scott Ziegler and Aki Nishimura in biostatistics and so forth. So to me, this is extremely interesting, because we can now, it's no longer just regression with numerical things. There are semantic things, there are image things, there are numerical things. So heterogeneous data, how to do prediction, and so on. My son is an anesthesiologist at Newport Beach. He wants to know if there is any chance a patient will go under low blood pressure. He would like to have a warning, a 15-minute warning, so he can be prepared. There's actually a paper that talks about it in Journal of Anesthesiology using logistic regression. So being able to predict, what may happen and so on, I think is a problem 7, and statistics. Biostatistics is an established field, so you all should look into that. Mitigating AI bias. I told you, we found that we were not doing well with females. Here, what I'm showing is a verification performance, male to male comparison, female to female comparison. As you can see, there is a drop, but the bias here is this. Here, the bias is large, right? Same with skin tone. The green is our approach, blue is Imperial College. Imperial College has less bias than ours. And look, same here. We have more bias because we thought by including this additional information, our ID performance will be good. And it is. our identification numbers are better than the Imperial College for a large number of data sets, although they are better on 1 or 2 data sets. Because by including this information, our ID is better, but it's also contributing to bias. So the choice is unbiased, low performance, biased, high performance. And is bias a prior in the Bayesian world? I don't know. I need to think about that, right? So this is, again, bias mitigation we did using adversarial laws and so on. So we reduced the bias here. So there is another paper that is in archive. Okay, so last but not least, this was mentioned by Alan because adversarial attacks. I'm somewhat amused by so much attention to adversarial attacks. If you have read the papers by Doug Martin in the 70s, he was a statistician at University of Washington. He was working on robust estimation, robust spectrum analysis. In particular, his 1979 Journal of Royal Statistical Society Series B paper on robust power spectral estimation will make the point that if you have a time series model, if the outliers are just as small as the innovations that drives the time series models, you are in trouble. Except that nobody looked at the data there with and without time series model and said, oh, this is visually indistinguishable, but then they are creating havoc. What we are seeing now in adversarial is somewhat like that. We have 2 visually indistinguishable parents, but they are sending the classifiers to 2 different ways. So the idea that outliers can create havoc is, there. I mean, we know 3 sigma rule, we know M estimates, GM estimates, and so forth. So this is a thing that we have to look at it. We have to address it. In fact, we developed a defense GAN to, in 2018 ICLR, and Carlini Wagner could not completely destroy it. They destroyed 6 other things, but ours went down to 55. And then somebody else knocked defense GAN down in 2017. But this is what is happening now. The visually indistinguishable thing attacking has now morphed into visually distinguishable thing attacking, right? If you look at the patch attack, most patch attacks, a human can see and say, wait a minute, no, I don't want to bother with it. It's no longer visually indistinguishable, patch attacks. Okay, so, but the methods are, it's going to be a problem. If you have patch attack, your deep learning method won't work. I mean, that is correct, and it should not work, right? So how do you make it robust? Well, everybody is working on it. Alan is doing it. We have a program called GUARD under DARPA. So we are looking at it. It is a hard problem. Outliers are hard. If somebody wants to mess you up, they will succeed. But there are some interesting ideas from statistics coming, manifold. You can take the incoming sample and see if it is in the range of the GAN that you have generated. If it is, then you can smother it. If it is not, you say it's a bad data and so forth. There's another kind of dynamics that's going on. Everybody beats white attacks. So Carlini would argue. I told him, hey, Carlini, you are breaking me because I give you my code. So you know how my derivatives are and you go and mess them up. He says, Rama, cybersecurity 101 says obscurity is not security. Okay, fine. The question here is, if I leave my house key outside my house, you come and open the door and say, Rama, I broke into your house. I don't know. Should I be concerned? I'm not sure. We are early in the game. I have different views about this adversarial thing. Everybody loves it because it's always fun. You can add some noise and make a school bus look like an ostrich. Sure, it's kind of fun. People write papers on that. But I'm not so sure if it is. You know what I think may happen? We all have credit cards. And credit card companies take some hit. They know there is going to be fraudulent charges. And so they actually pass that on to you. That's why the credit interest rates are high, because they are not absorbing the credit loss. They're quietly passing on to you. So if ever deep learning became a household thing, that your blender and your microwave and somebody wants to attack it, your toast became all black, you sue the Black & Decker company, they'll say fine, and they may just give you another toaster or something, because they may just factor the loss. I don't know if that's all may happen, because credit card companies know there is fraud. But if you knowingly commit credit card fraud, you go to jail. So who knows? That may change the way we look at adversarial attacks. All right, I've spoken too much. Conclusions, recent trends, etc., etc. AI stat is already there. It's not like statisticians are not playing a role in AI. I mean, uncertainty reasoning coming from Julia Pearl onwards, it's there. So you guys have a lot to play, and it's still a lot of alchemy with deep learning, but alchemy did not work. People claim they will convert water to gold. They never could. But deep learning, sometimes it happens. I tell you, face verification is good. There are many other things that you are seeing. And my concern is if this continues and we are becoming more and more successful in converting gold from other materials, people won't care anymore. How do you do it? They may just take the gold and go away. So statisticians, you have a big responsibility. You got to make the field strong mathematically and so on, okay? There's no point saying, oh, it's this, it is that, it is not. Jump into it. Hands get dirty, and I think you will help us because I want to have the gold. I also want to know how it is produced so I can produce more gold from everything. Okay, that's it. I'm stopping. Thank you for your time.
Thank you very much, Rama. There's a lot of stuff packed in there. I mean, it's very clear that for younger people, for younger, let's say statistics PhD students, assistant professors, postdocs, who want to learn about these deep learning techniques, because we all read about it in New York Times. So we need entry points. Our younger statisticians, they need entry points to get into these problems. So I'm glad that you sort of mentioned concrete problems to work on, sort of selecting the data set to train on. I think that's a connection from classical statistics. One can build these bridges. And so I think this kind of talk would be very useful. We will revisit it, at least with my students. And I think this will be of great importance to sort of upcoming statisticians to try to go beyond their classical classroom training that we are used to. We don't see those networks and that kind of data analysis in our classes. So hopefully that will do the trick. It will do the motivation for the students and show some pathways. So thanks very much again, Rama. We are a little bit behind time, so we will not take questions, but I'm sure there is a lot one can go with you. We wish we were in the same room and doing these things face to face. I will go ahead and introduce our next speaker. So Yingyan, can you please try to share screen and see if it works while I introduce you? So Yingyan is a professor in Department of Statistics at UCLA. He is a good friend, a very thoughtful, deep thinking type of a person. He has worked for a long time in the area of generative models in computer vision, but more than that, he has also worked in machine learning, computational neuroscience, bioinformatics. The kind of person, the more time you spend with him, the more you learn about things. And so I'm glad that he's here to explain some more new work he has done. So go ahead, Yingyan. Thanks.
Okay, Anuj, can you hear me?
Yes.
Okay. Yeah. First, I would like to thank Anuj for organizing this workshop and for inviting me to give this talk. So I'm going to talk about this latent space energy-based prior model for images and text and also molecules, etc. So this is a joint work with my student, Bo Pang, who's very creative, and Eric Nijkamp, who's on job market and who's very, very capable, and a former student, Tian Han, who's now a assistant professor in the Stevenson Institute. So the papers mentioned in this talk can be downloaded from my research webpage. Okay, so in the first two talks, both Alan and Rama mentioned about generative models, and Alan made a very strong case about having generative models. That is, from probability perspective, we want to like learn a probability distribution, a density function on the training data set. For example, those are the images generated from the learned generative model in our previous work. And they look very realistic thanks to, again, the deep neural network, especially this top-down version of the generator network. And we can even doing the interpolation. So we can interpolate linearly in the latent space, which give us a nonlinear tracing of the manifold in the data space. So you can see a smooth transition from a man to a woman by this type of interpolation. So another model that we studied is this so-called energy-based model, which defines a probability distribution in terms of energy function. So by sampling from this type of energy-based model and adding some diffusion tricks, you can actually generate also very realistic images. For example, those bedrooms. So this model is learned from 3 million bedroom images. And those are the church images. Okay, so let me talk about some details of this type of model, the model that we call latent space energy-based model. So, so in this talk, I will be a little bit more specific and technical. So we define X to be observed image, for example, a 200 by 200 image, and X is certainly a high-dimensional creature. And then we want to expand the image by a latent vector. Say this latent vector may be 100 dimensional. And in order to build a probability model on X, we specify a joint distribution for both the observed X and the latent vector Z. And we write this in the form of a prior distribution, P of alpha Z. So this is the prior distribution that we put on the latent vector. And then the conditional generation distribution, the probability for X given Z. So this certainly is the Bayesian formulation. And we can think of a prior distribution on Z. For example, if we assume a uniform or isotropic Gaussian, like an ID Gaussian prior distribution on the components of Z, then Z follow a known prior distribution. So in the language of Bayesian modeling, which both Alan and Rama mentioned, so we call this type of prior as non-informative prior. And then this Z generates the image through a generator like network parameterized by this beta, where beta collects all the weight and bias parameters. And then this transforms. So you feed this network with this Z, and then this network will output X. And then we assume that X is a noisy version of this generated Z. So this is a Bayesian formulation. And for the image, you can train a top-down network for this G. But for the text, for example, for any sequence, you can also use a autoregressive model because of the sequential nature, where this Z also determines the conditional distribution. So this model may be in the form of a recurrent neural network. But the idea is that this mapping G or whatever this recurrent model map a Z to the observed image, and which means it maps the say a unimodal prior model, say isotropic Gaussian, which is a unimodal prior distribution, to a highly multimodal data distribution. So this is a Bayesian model in the language of Alan. I think there may be some distinction to be made. So in statistics, people say that you are full Bayesian if you also assume a prior distribution on alpha and beta. So here we are not going that far. I don't think Alan will go that far either. So Bayesian, in the sense that we treat this Z as like a random variable, and we put a prior distribution. But we know that in Bayesian statistics, there is also the so-called empirical base. That is, if we have a lot of observations, multiple observations, in this case, say we have thousands or even millions of images, then we can learn a prior distribution from the data. So follow the empirical base spirit, we actually generalize this generative model to this model where we learn a so-called energy-based prior model. So that is this P of Z has unknown parameter alpha to be learned. So it is a informative prior distribution, and it is learnable from the data because we have multiple observations. And as I said, this follows the empirical base principle. And the energy-based model originated from statistical physics. That's where the name energy comes from. So the form is like this. It's from the statistical perspective, it is a generalization of exponential family model, except that here, this function, which is a negative of the energy, is parameterized by another network because of the low dimensionality of Z. So this network F can be much simpler. And we still keep this non-informative prior distribution. So therefore, you can think of the learned prior model as a correction of exponential tilting for this original non-informative prior. And this Z of alpha is a normalizing constant. So to make P of alpha a legitimate probability distribution. And in statistical physics, it is also called the partition function. So this energy-based prior model stands on the generation model or the generator network. So that is after you generate Z from this informative energy-based prior distribution, and then you can map Z to X, the image, through this top-down network. So that's the basic idea of our model. And you can think of this model in terms of this diagram. So where you have latent Z to represent this X through this top-down mapping. So this is a rather big network. And then you learn a energy function. So for this Z, so this is a rather small network. So this G of Z, you know, this X is a high dimensional thing. So this G, this generator network should be vector valued, high dimensional vector valued. But this F is a scalar valued. So therefore, it is very easy to specify and learn such a scalar valued function. And you can interpret this F as a value function, or conversely, the cost function, or objective function. So supposedly this F, actually this energy function, or negative energy function, captures regularities or the rules that in Z that is hard to capture by the top-down model. So that is, if you want to make the model expressive, you can make your top-down network bigger and bigger, but at a much bigger cost. But you can also learn a energy-based model to regulate this Z, which is much easier to do with much less parameters or model complexities. So this type of model, as I mentioned, originated from statistical physics, including the term energy. And it is a form of Gibbs distribution that Rama mentioned. He mentioned the Markov random field model, which is a form of Gibbs distribution. And it is also a random field. But here, we actually move the energy-based model from the data space to the latent space. And because of the dimension reduction of the latent space, so Z is low dimensional. So modeling this Z is much easier than building a random field model or Gibbs distribution directly on X. We did this before, but it is not very easy to sample from because of the multimodality. However, this distribution on Z, this P of Z, as a correction of a unimodal prior model, it can be much closer to unimodal. Therefore, it may be much easier to sample from, and also the MCMC sampling can mix very well. So that's the basic structure of the model. And then in order to learn from this model, if we want to use maximum likelihood, we need to find this marginal distribution, which is the integral of the joint, right? This is not actually in closed form. And then we also should figure out how to sample from the posterior distribution. Again, in the language of the Bayesian, as mentioned by Alan, so we treat Z as random, and given a observer image, if we want to infer Z, we can sample from the posterior distribution. And this is done by just a regular Bayesian type of formulation. Okay, and then we can learn this model from the training data. Suppose you have thousands or millions of bedroom images or whatever, or face images. You have set of training images, and then we can learn to figure out the underlying structure in these images. So this, as Rama mentioned, this is called unsupervised learning because you are not giving a label for each of these xi. And then we can still use the maximum likelihood for unsupervised learning, where we want to maximize this likelihood, which log likelihood, which is summation for the log for marginal for each of xi. And here, a well-known result for learning using gradient descent is that the learning gradient based on this stochastic gradient descent can be written in this form. And it actually has a EM interpretation. So that is, this is observed data log likelihood. And this part is a complete data log likelihood, which does not involve intractable integral, so that it is in closed form. And then you can take gradient, learning gradient on this complete data log likelihood. But here it is averaged over the posterior distribution of z given x. So this posterior distribution plays a role of inference from this based on this posterior of z given x, and it can also be considered as an imputation of the missing data in the language of the EM algorithm, where x is observed and z is missing or hidden or latent. And in fact, you can think of this expectation as corresponding to the E step of the EM algorithm, and this gradient descent on the complete data model after you impute z as a gradient descent for the M step for the EM algorithm. Okay, and then you can actually further pass this learning algorithm where the learning gradient for the prior model with the unknown parameter alpha is like this. For each observation, it is in this form. So here you have this expectation with respect to the posterior distribution. So for each image, you sample this z from the posterior distribution. But this part is a prior distribution to be learned from the model. So the idea of the learning gradient is to match the prior distribution with aggregated posterior distribution, because the learning gradient for each mini batch is the average over all the x, right? So you match the prior distribution to the aggregated posterior distribution. So that is, it is somehow like a adversarial. You actually have a adversarial interpretation. In fact, the learning algorithm for energy-based model is self-adversarial or self-critic, where this energy function, very similar to this Washington GAN, plays the role of a critic, but the model itself also plays the role of actor. You generate this model itself, generate the images or generate the samples, and then you try to update this F as a critic to favor the observed data. Okay, so gradually, then your prior will match the aggregated posterior. You can also think of this from the perspective of analysis by synthesis. So this part is the synthesis. So you try to update your model based on the difference between the synthesis z and the observed z, or the z inferred from the observed data. Okay, so this is a maximum likelihood learning algorithm, and you can, but then you can also you need also to use some like a fast MCMC for posterior sampling. So that is, in order to sample from the posterior distribution, you can use the Langevin dynamics, but you can also sample from the prior distribution, right? You need to sample from both the prior distribution and the posterior distribution. You can use a short-run Langevin dynamics. You start from this non-informative given known prior distribution, for example, the unimodal isotropic Gaussian distribution, and then the Langevin dynamics is actually a gradient descent algorithm and adding some diffusion noise to add the uncertainty for the purpose of sampling. So it's a balance between decreasing the energy and increasing the entropy. And usually we can use a very small k, because z is a low dimensional, and both the posterior distribution and the prior distribution are close to unimodal. So you can easily sample from those distributions with only a small number of MCMC steps. But if you feel that this still you don't want to do this iterative sampling, you can actually amortize the MCMC sampling by learned neural networks for both inference and synthesis. And later I will give you the formulation for this amortized sampling. So, but the pure, so here, in order to keep everything pure and simple, so we do not want to involve other networks, just purely just these two networks for the model. And then the learning and sampling algorithm involve the following steps. So you keep, you take a mini batch by random sample, for example, 100 images, and then you sample from the prior distribution, and you sample from the posterior distribution. And then you learn the prior model, in particular this alpha, based on the difference between this prior sample and the posterior sample. So in order to match them, and you learn the generation model of this parameter beta by reconstruction. You want to reconstruct this X from this inferred Z. Okay, so that's the learning algorithm. It's actually very simple, and the whole code can be fitted in a single page. But then you can also learn actual networks, although I don't really prefer that one, but actually this we have done this for the purpose of efficiency. So you can learn a actual network, a separate network to approximate the prior distribution. And you can also learn a separate network to approximate the posterior distribution. And this is like an encoder or inference model in a variational autoencoder. And the interesting thing is that we can actually formulate the learning algorithm based on this objective function. So the first Cal divergence actually give you the maximum likelihood. And then you have two actual terms, two actual Cal divergence. One is a Cal divergence for this learned posterior sampling model and the true posterior distribution. And the other Cal divergence is between the learned prior sampling network and the true prior distribution. And the learning is based on this min-max thing. So this formulation captures some of the previous results or unifies previous results in a very interesting way. So that is this positive part, this positive Cal divergence corresponding to the positive phase for posterior sampling in a latent energy-based model. And this negative sign corresponds to the negative phase for the prior sampling of the latent energy-based model. And this is the first Cal divergence actually correspond to the variational learning, give us a variational autoencoder type of learning. And the second one, this negative KL, this part gave us adversarial learning. So because we need to have min-max. So this is another maybe alternative formulation of, again, but without learning a classifier. Instead, you learn a energy-based model. And it is also related to this W-GAN, except that it is in latent space. And also the difference between this one, the first term, and the third term is another version of the so-called contrastive divergence. When Alan was my colleague, he did some important work on analyzing the original contrastive divergence. And here, if you look at the difference between this one and this one, you actually have a alternative version of contrastive divergence, which also give you a adversarial formulation for this type of learning. So the idea is that if you feel that MCMC is a little bit too slow, actually it's not that slow because Z is low dimensional. But if you still want to go faster, you can learn this actual network that directly generate or directly output the Z samples from the posterior and the prior distribution. Okay, another method maybe you just learn a inference model here, just like a variational autoencoder, except that when you learn this model, you also need to take care of the prior model. But then you still sample the prior model, this prior model P of alpha using MCMC, because sampling from the prior is a lot easier than sampling from the posterior, because you do not need to back propagate through this top-down, very big top-down network. So MCMC for the prior is really cheap. Okay, so that's all about this formulation, and you can use this model for image generation. So without any GAN or any other elements, you can actually generate very realistic images. And also you can evaluate numerically on different data sets. So for example, SLIP-A and SVHN or Cipher. So I don't really know the details of how you evaluate, but supposedly there's a very popular FID score. Now people use FID, and before that they use the inception score. I have no idea what those scores are, but if you want to publish papers these days, you have to push the score very high to at least approach the state of art. So as Alan mentioned, there's a tyranny of the data, but we have to live with it. And you can also analyze this short-run MCMC for prior sampling. So you see the after only a few number of iterations, you can actually get a very low energy, and meaning that it's close to convergence. And indeed, if you keep sampling, you can still traverse the mode and sample the fraction without much difficulty. So MCMC for the prior sampling is actually quite feasible. And you can also apply this model to the text generation. You generate text paragraphs using a recurrent neural network RNN model for the generation. And again, you can evaluate the generated quality. So with this perplexity and negative likelihood, etc. Again, I have no idea what are those data set or evaluation criterions. Boer and Eric did all the experiment, but supposedly it is quite easy to generate very realistic text using this model, because supposedly this energy-based model somehow capture the grammar or maybe syntax implicitly, all those rules implicitly. You can also do anomaly detection based on this log the joint probability density, so that you detect out of distribution examples. Supposedly you should use a marginal likelihood, but for simplicity, we use the joint likelihood where Z is inferred from this X. And based on that, you can look at those outliers, detect those outliers. It actually get a very good performance. Again, because your energy model capture these regularities in the data very efficiently. Okay, you can also use this model for trajectory prediction. For example, if you drive a car or autonomous driving, you need to predict the trajectory of other cars or maybe other pedestrians. And you can use this model where this energy function now given a certain condition, it tells us the cost of the trajectory. So therefore, you actually treat this trajectory prediction almost like a control or planning. So that is, you figure out the objective or the goal of this pedestrian, and so that the trajectory actually minimizes this cost function. So this is related to inverse control or inverse reinforcement learning type of things, where this energy function plays a role of cost function. So you not just model or mimic the behavior of pedestrians, you actually figure out what's the value, what's the preference, what's the goal or what's the cost function of this pedestrian, so that it can generalize better. And again, because this is in the latent space, everything can be done very easily, and it can also be learned in a very efficient way. And again, there's a performance that I have no idea what the metric they use. And then we can also generate molecules where you can encode a molecule very much like a text, which like this smells type of thing. It's a simplified molecule input line entry system. Not a very meaningful name, but you can encode each molecule by a sequence of symbols, very much like a sentence. And then you can use a language model to generate the molecule. And then this energy function in latent space captures those chemical rules implicitly very easily. So you can get very realistic molecules, and you can evaluate based on different measures, for example, validity and novelty and uniqueness. So this model seems to be very powerful. Moreover, unlike other models, for example, VE type of things, the energy-based model can replicate the probability density almost exactly to the data density. So again, because in latent space, the energy function actually perform this density estimation, very accurate density estimation, because energy is only a scalar, right? So a density is also scalar. You approximate this density very accurately. Okay. And then you can also apply this model for semi-supervised learning. Again, this is mentioned by Rama. So in semi-supervised learning, you have a small number of label data. So I give you some, for example, some digits. I tell you which digit it is, but then I give you a lot of unlabeled data. So this is actually a more realistic scenario. And here we have, in this case of classification, for example, Y is a one hard vector. So you use this type of one hard vector to represent the categories, which is commonly used in classification. And then you have this Z as a continuous dense vector that we used before. And this one hard vector is considered as a symbol. And then we have this symbol vector coupling, and which form a social memory in the spirit of Houfield theme, as mentioned by Rama. So it is now you have a joint distribution that couples this symbolic vector and this dense vector. And then you have this F give you the logic scores for different categories. And the interesting thing is that with this associative memory, the conditional distribution of Y given Z is just a common softmax classifier. That is, you do classification in the latent space. And so to compare the original model with this model, actually you can, if you integrate out Y, sum out these K categories, you can actually get the marginal distribution where this F is in this form of a log sum exponential form. Okay, and then you can use this for semi-supervised learning, where only some of the X are labeled with Y. So for all those X, you use a marginal distribution as in unsupervised learning. And then for those labeled X, where you have Y, you then further add this conditional distribution Y given X, which is a softmax classifier. And then you have this very principled likelihood-based method for semi-supervised learning. It has a good performance on image data, and it actually achieves state-of-the-art performance on the text data and the tabular data. Okay, so the idea for this type of model, just to wrap up my talk, is that the energy-based model in latent space is very, very powerful and captures the regularities or rules very efficiently. And also, if you do this type of classification, for example, using this symbol vector coupling, it may also be robust to adversarial attacks, a topic covered by both Alan and Rama. The reason is that this top-down model can easily explain away those adversarial attacks, or mathematically, you are doing some projection on low-dimensional manifold, which is actually a contraction. But more interesting for me is that it appears that this model, for example, may correspond to different parts for the cortex or the brain, where this symbolic thing may be in hippocampus, and this latent Z may be in itohino cortex, and this the rest will be in the visual cortex or some other part of the neocortex. And also in terms of learning, probably the learning of this F or this thing may be fast learning in the this meta learning thing you learn from small data, short-term experience. But this G of beta, this big top-down network, may be learned slowly over long-term experience. Okay, so I think I spent exactly 30 minutes, and I can stop here, and I will stop sharing so that the next talk can take over. Thank you.
Thanks very much, Yin Liang. Your talks are always wonderful. You seem to sort of weave in from classical, statistical formulation, and you're talking about deep neural networks all in the same breath. I mean, it's amazing what you can do. Let me ask you just a quick question. Both Rama and Alan mentioned about the role of geometry. You know, you have these scenes you are synthesizing with bedrooms with beds in there, and are they done? I mean, faces I can understand, face pictures, but the scene where you have objects, is there no notion of geometry? Are these latent variables somehow related to the pose, the viewing angle? Is there any role of geometry in there?
So currently in this model, we haven't built in the geometry, or in other words, it is learned implicitly in this top-down network. But absolutely, you need to introduce the geometry explicitly so that you learn much simple model. Otherwise, you have a network with millions of parameters, really too much. But with explicit geometry, your model is much more explicit, much simpler. You can learn from small data, and moreover, it is also more robust. So definitely you should build in more and more explicit knowledge in this top-down network. So currently all those neural networks are very implicit. So that's really a shortcoming. It's a black box, still black box. So gradually you want to introduce a hierarchical model. You have a hierarchy of concepts for different abstractions, including geometric concepts that built in. But it may not be just hand designed, so it may emerge. So the best way to have those models is to let the geometric or some other information to emerge, and then we need to constrain the form of the model so that those knowledge can emerge naturally.
Yeah, I think there is a great potential for bringing in those geometric variables in the representation, make it more rich, maybe make it more robust.
Absolutely, I think. I think it's part of Z should really encode the shape explicitly. And in one type of work, we actually encode the deformation for the shape explicitly. And we use a network to generate the deformation. But definitely there should be a shape part, and then there should be an appearance part. So they should be separated. And then you can enforce a model to learn both the shape and the appearance.
Yingyan, as you can imagine, there are a bunch of questions for you in the chat, but in the interest of time, we will just move forward, and maybe the people who have questions can contact Yingyan in some ways privately and chat with him. There's a lot more to absorb from his talk. So I'm going to go ahead. Thanks again, Yingyan.
Thank you.
I'm going to introduce the last speaker for the session, Professor Sudeep Sarkar. Sudeep, if you can see if you can share the screen.
Yeah, let's see.
So Sudeep is a professor and actually chair of the Department of Computer Science and Engineering at the University of South Florida. He has worked in the area of computer vision, human biometrics, medical image analysis. He has many fantastic recognitions, one of which I'll mention. He has been inducted into the National Academy of Inventors, which is a great, fantastic recognition. He's among many things he has done. One of the things that is really remarkable is following Ulf Grenander's work on pattern theory. Ulf did lots of different things, from statistics, computer vision, to image analysis, modeling. But I feel like some of his main ideas about using this pattern theoretic representation have not been really exploited, has not been really understood and used. Even I feel like I have not really understood his main contribution. But I give all the credit in the world to Sudeep for reading about it, and I feel like at this stage, at this moment, he is one of the world's foremost expert in applying Grenander's pattern theory, and I'm glad that he's here to talk about it. So go ahead, Sudeep.
Well, thank you, Anuj. Well, I don't know whether I claim to understand Grenander, but I'm certainly standing on his shoulders, or at least some part of his body, and trying to do some new stuff. Thank you for a morning of very engaging talks. You know, Alan Ewell is the person to blame for making me Bayesian. I am an hardcore Bayesian. I believe in it, and part of that is some of the stuff that I've read of his papers early in my days. And this is another book. I don't know, some of you, if you have seen this book before. This is a very easy reading book. If you are still, well.
Zoom back a little bit, yeah.
So if you're still unconvinced about being Bayesian, this is an easy read. You might want to pick this up. I found it very useful. And Rama, I learned how to be very rigorous in when you do computer vision, not to hack things, right? So Rama is an excellent example of bringing rigor into whatever we are doing. And then Ingnian is I loved his way how he put a Bayesian context to a lot of the deep learning stuff that has been proposed. So he's blazing new fields, a new territory there. So what I'm going to share with you is our journey in using some of the original Grenander's pattern theory. So I'm going to use his old language. So it's like talking in Latin and Sanskrit, right? So I'm going to use his original terminologies and all. So this is a work that I've been doing with Anuj and two of my students, Felipe and Satya. They have since graduated for some years now. So let's see. So the context is events, right? So if you look at a video, right? So the idea is you are seeing certain events here, right? So somebody is playing a guitar, somebody walked into a door, and then in the beginning of the video, there was somebody who walked by. So these are small things that happen. There's certain event that you're interested in, certain events that you're not. And people in cognitive sciences and human perception have worked on, thought through these kind of things. So what is an event? And the definition, one of the definitions that I kind of like is an event is a segment in time at a given location that is perceived by an observer to have a beginning and an end. So it's almost like a story. It will have a beginning, it will have an end. And if you describe an event, you will have to do the 5 W's, like who is in there, what are the nouns, what is being done, right? Actions and activity, where is it happening, when is it happening, and the intention, why is it happening, right? So you would like to describe all of them. I cannot claim to say that we have all the W's figured out, but this is sort of the goal at the end. So what has deep learning done for this problem? So if you look at deep learning 1.0 kind of solutions, right? So deep learning 1.0 solutions will be able to mark for you persons, that the fact that somebody is playing and that there is a guitar in the scene, and they will be able to box it for you, right? So this is deep learning 1.0. Deep learning 2.0 tries to describe this kind of a video snippet with sentences. So person playing guitar, right? So it'll try to produce captions for this video. What we'd like to go do is open world event understanding, right? So what do I mean by open world? Well, I have to be able to make connections to past knowledge and create an event model that goes beyond what I have seen here, right? In the video, right? So can I produce a description that goes beyond what I also see in there? And part of it is you'll see an example here. So what do I mean? So this is one of the kinds of descriptions that we can create, right? So this is a graph kind of a description. The black circles here describe what you see in the scene, person, play, guitar. But then the red circles here also talk about concepts that you actually don't, you're inferring, right? It's not there it's not trained for labeling instruments. It's not trained for detecting music, right? So it's the concepts that it knows about, the system knows, is person, play, and guitar. Music and instruments are not trained for. They are concepts that are inferred. So this is the kind of description that you'd like to build, right? So go beyond what you see. So this is another example. You have a video of a person in the doorway there, walking into the doorway, right? So what you see in the video is walk, doorway, and then floor, indoor space, hallway. These are concepts that the detection system doesn't know about, but it's able to pull it, right? And create a description that goes above and beyond what's there in the image. So that's what I mean by rich open world interpretation. So how can we do open world information inference, right? So one is the source of semantics, right? So where is the source of semantics? Where are the meaning coming from? Typically, most of the meaning comes from the training data. Somebody labels the training data, and that's where the meaning comes from. Or the other source of semantics is in the priors, right? The second aspect is what kind of representation are you using? That's very important, right? Right now with deep learning, it's all continuous valued vectors, but there are richer sets of representations like symbolic representations that we should revisit, because that are those kind of representations and graph representations, right? And then the ability to continuously learn and adapt, right? So as you run these systems, we should be able to continuously adapt to what we are seeing. That aspect here, I'm not going to talk about that aspect in this talk. To give you an example of where the semantics right now is coming from, it's really the over-reliance on annotated data. This is from a very recent data set, big data set, Epic Kitchens. And if you look at the kind of annotations they give you, it's pretty amazing. They mark every object, right, that are involved, and then they mark the timeline of the video in terms of activities that are happening, like fold kitchen roll, pick up tofu, put on kitchen roll. Now, this kind of, if you're given a data set like this, labeled in such a fine-grained manner, you can build a deep learning system. But this is not a scalable solution to new domains, right? So that's the current problem with deep learning data sets. So so what we are said was, well, there's lots of symbolic knowledge bases that are out there, right? Can we use those as priors, right? Source of semantics. So one of the databases that's out there is the knowledge bases that's out there, not database, is ConceptNet. Okay, ConceptNet is it has about what they call about 8.7 million assertions, about 4 million concepts. It comes in different languages. This is a very small snippet of that. So it has representations like egg is a food, at location bowl is a container, right? Plate is related to put, right? Pour is related to put, and so on. And then there are weights for these based on evidence for that weight. And the way they gather this evidence is go through Wiktionary, and DPpedia, Freebase, WordNet. So this is sort of the summary in the web that's out there. So we said, okay, can we not use these kind of prior knowledge to do video interpretations, event interpretations? Okay. There's also, this is in line to kinds of approaches that we are starting to see. These are neuro-symbolic approaches, right? So that's the category of approach that I would sort of say we are doing. We have, in terms of representation, we have a stack of continuous valued vector, which is your deep learning stack. And on top of it, we have a graph-based explicit symbolic representations, okay? The idea is that once you have the graph-based representation, you would be able to use that to generate other things. You can do sentences and so on if you need it. So here's an example of the representation. So at the bottom, you have your deep learning stack, traditional, right? It will produce elementary objects with bounding boxes or actions that are happening, not activities, but actions, right? So spoon, dough, bowl, pick up, stir are the elementary actions. You'd get those labels. And then on top of it, we would have a symbolic stack, which is basically elementary objects and then compositions of that, right? Into larger structures that become the event model. So that's the sort of representation we are trying to build. If you are thinking in terms of like system building, this is what the software or the structure would look like. You have video, you can also have sound, and you can do some sound analysis, and then use that, and the video also, you can do action analysis, object recognition, and you can train these things, right? So you train the elementary object detector, elementary action detector, and sound sort of labeler. And for each instance in the image, we don't look at the best object that has been labeled. We look for the top K interpretation, top K possible labels for each instance. So like bowl, cup, plate represents some object at a particular location in the image, possible labels. So given these possible labels, the idea is to sort of merge them with ConceptNet to create descriptions. And the glue that we have is the pattern theory energy engine. Okay, so if you're thinking in terms of Bayesian things, you have, this is your prior knowledge, common sense knowledge base, and then these are your image information measurements that are coming. Okay, so we sit on, of course, Grenander's shoulders here. This is the blue book, is the big tome that I think Rama referred to, general pattern theory. I have read a couple of pages in there, and that has been enough to spur the ideas in this work. There's tons of ideas in that book. If you are a graduate student looking for ideas to work on, especially in statistics and math, pick up that book. It's a book that's worth spending some time with. This yellow book is something that he wrote towards his later part. I think this is probably his last work that he authored. He co-authored one with Miller also. This book, he actually has code, MATLAB code, and Anuj might have written part of it. It's very accessible. The pattern theory that the formalism that he proposed is very accessible for a non-statistician like me. Okay, and in this book, he talks about how to model human thought. Okay, so he goes above and beyond images, but that's also worth looking at. So here's the sketch of the approach. Pattern theory is combinational, combinatorial in nature. Complex structures will be built from simpler ones, much like molecules and proteins, right, from elements. Symbols can interact with each other to form large combinations. The interactions will be constrained by how symbols interact locally and the characteristic of the overall graph structure, and then your probabilistic structures on representation allowing for expressions of variation. And we will see that his canonical representations actually provides an unified manner for viewing DAGs, MRFs, Gaussian random fields, probabilistic formal languages, and so on. Okay, so what does the canonical representation involves? It involves four things. Basic symbols or generators, a similarity group among the symbols, how the symbols interact with each other, local regularity, and then a constraint on the overall structure, which is the global regularity. What you will see is that the sigma, depending on how you define the sigma, you can get different other graphical representations that you're familiar with, MRFs, Bayesian nets, and so on. Okay, so, and lastly, there's a probability space over these structures. Okay, so generators are basic units of representations, elementary symbols of our generators, and then these generators will be connected with bonds, right? So two generators interact with each other with bonds. Now these bonds can be of different types. So it's not just that you have only one kind of bond. You can have different kinds of bonds, and you can also have in bond and an out bond, right? So it's actually a very flexible model that allows you to model all kinds of graph representations within it. And it's actually richer than a plain old graph because it allows for dangling edges, okay, which typical graph representations will not allow you to do. So here are some examples of generator in the context of cooking, right? So you can have the features that you detect in your image. could be generators, right? So those are your low-level generators. Then you have objects, right? Bowl, cup, pan, plate, whisk. Those are your generators. Actions, elementary actions: flip, put down, pick up, pour, stir, season. And each of the generators will have different kinds of bonds, right? So for example, if you look at the stir, right? So stir would need a stirrer to stir with, food that you're stirring, a receptacle, and a feature that the stirring, this is the grounding feature, image feature, or a video feature, right? So it has 1, 2, 3, 4 kinds of bonds, right? Each looking for different kinds of connections. And then here is for spoon. It could be a starter or a grasper, and then you have features here. So what I have outlined here looks like it's all handcrafted, but we'll see that we don't have to do that. You can actually use the concept net to get all of this stuff. Okay. Then you can have similarity group over these generators. Here's an example of the similarity group. Similarity group is basically objects that you can interchange with each other for functionality, right? So bowl, cup, pan, plate can be interchanged somewhat. Whisk, spatula, spoon can perform similar tasks, right? So you can interchange it. So it enables you to capture that aspect. The similarity groups are important because it will help you control the combinatorics of the search for the solution. And then the bonds, you can also define local regularity. There is more mathematical rigor than just one slide here. You can look that up in his book. And then, so here's an example when these on these generators connect with each other, you end up with a configuration. So here, spoon, stir, pick up, dough, bowl, and then each of the features are grounded in the image. So you have this description completely grounded in the image. And you can have dangling links here. So for example, pick up, it was expecting a grasper, but nothing was detected. If you wanted, we haven't done it, you could take these descriptions and actually go back in the image and look for a grasper, right? Or pick up, they should be expecting a food, there's no label there. So you can use these descriptions to do further search in the image, guided search if you wanted to do. Or you can use these structures to create descriptions, right? So picking a bowl with dough and so on. And Grenander actually has ideas on how to generate sentences from the representations like this in his book. So if you look at the graph structure, underlying the graph structure, if you look at the configuration, underlying the configuration is a graph structure that I have shown you here in red, right? So this graph structure defines the global regularity, right? So if this structure is fixed, if you fix it and say all my configurations that I produce should have this structure, then you have MRFs, okay? Or if you have a Bayesian network, like where all this possible, the graph structure, underlying graph structure is fixed, right? Even an and/or structure is a little bit more flexible. It's not fixed, right? Then you get and/or representations. So for us, we defined what we called a partially ordered set. So think of the symbols in terms of hierarchies, and we constrain the links between the levels, right? So we have a partially ordered set in terms of the constraint. So it is a very general constraint, more general than MRFs and Bayesian nets and/or graphs, right? So so the relationship with, again, to summarize, if it's fixed structure, your MRF, then or you have DAG, or you have and/or graphs, or if you grammar rules and generators, then you get context-free grammar. Okay, so so that's for the canonical representation. Now you can define sort of probability over this graph structure in a typical way. You define basically energy terms. The first is a direct video support, and then you have a prior support from your concept net. So components of the energy will be, you have some energy based on evidence from image, which is the featured links. Dashed links are this is the semantic links, links between concepts. And then you also have an energy for dangling links that hasn't been connected, right? So the problem with this search is that minimizing this is the partition function involves a double sum, okay? Because you have a sum over the possible underlying graph structures, and given a graph structure, what are the possible generators you can place in those graph locations. So it's a double sum. So unlike other kinds of energy minimization, this is a harder minimization to do. And the way you do it is through stochastic search. And we have a double, we have a sort of like a canonical Gibbs ensemble here. And the way we do it is you control the combinatorics is through local and global proposals. And I'm not going to go into detail about it, but basically it's like an MCMC simulated annealing, where you have a global move that sort of changes the structure a lot. And then you have local moves that are morphing the structure. So these are sort of locally Markov moves, right? So, and the way we do these local Markov moves is guided by the similarity of the generator structure, right? So, and the knowledge base, right? So here's an example of the representation, right? For activity here, put, plate, egg, and it pulled in food and chicken from the concept net. The system was not trained. So if you look at this system, it was trained with the label put, it was trained with the label plate, it was trained with the label egg, for the label egg, right? But it was not trained for food or chicken. Also, it was not trained for combinations. So it was not trained for put, plate, or plate, egg, right? Those combinations, it didn't see it in the training data, right? So the links and all are all inferred. Food and chicken are also inferred. So the training needs for this is very minimal, right? It's just for the initial labels that you have. So here's another example, fix hair, right? So it found these labels, fix hair, and your typical deep learning computer vision things will output fix hair, right? However, we'll be able to output this whole structure, which is, you can see, gives you more semantic understanding of what's going on. Prepare, groom, comb, this is also pulled in, right? It's a much richer, this graph is a much richer description of what's going on, right? So here's an example where the deep learning output labels were in error, right? So read and brownie box are the correct labels. However, the deep learning algorithm did not return those as the topmost labels. They were further down, but this inference is able to pull it out because it found deep and brownie are more consistent with each other, even though individually they were low probability of being in the image. Okay, so read, brownie, recipe, container, food, right? They're all pulled out. So here's another example where the initial labels here, put, plate, and egg, were wrong, but it was able to pull out the correct labels into the description. And then food and chicken, of course, are not trained for. These are all pulled from the concept net. So here's an example where the label is actually wrong. So pour is correct, eggs is correct, but it did not get pour eggs on pan. It got pour eggs on bowl, right? And liquid was pulled in, which is correct. However, if you look at the description here, it's wrong in that sense that bowl is, well, it meant pan, but it got bowl. But semantically, it's not bad, right? It's not like totally wrong. Then another example where instead of add salt and pepper, it got spoon, salt, and pepper, right? Okay. it's technically there's an error there, right? So it'll count against it, but overall description is still okay. It also works for egocentric videos, right? So here's the spray butter pan, and this is the description it got, right? All of this work is in this paper that we published in 2019 in the Quarterly of Applied Mathematics. This was a special issue in honor of Ulf Grenander, and we were honored to be part of it. There are other excellent papers in there that you might want to look at. So same thing here on other egocentric videos: pour, pan, bowl, liquid, kitchen, black are pulled in from the concept net. Okay, so here's an example of person play tennis, and the sport is pulled in from concept net that gels everything together. Here is a tidy cabinet, and then descriptions of organization, storage, and container are pulled in from concept net to build a coherent representation. Okay. So how does it compare with other graphical approaches? So we have done some benchmarking of those. This is on the breakfast action data set. It has 1,000 recipes. Our approach, this for HMMs, this is context-free grammars, RNNs, and these two here, PT, are our earlier version of our algorithm. This is the most current one. We get pretty good performance on that. MSVD is another data set of videos from YouTube, and we compared this one with deep learning algorithms that were actually training on that data set. So these deep learning algorithms were training on sentences, right? So probabilistic factor graphs is of course old one. LSTMs, various versions, Google Net 3D CNN, hierarchical RNN, and this is our approach here, 42, about 43, and the other ones are, right, the maximum was 43. Remember the hierarchical RNN is actually training on sentences. We are not training on sentences, okay? So here's another one on the Charades data set. This has about 10,000 videos with 157 action classes. Again, the last one is ours here. The second last one, PT, is an earlier version of our work. We are doing pretty well, right? I don't know, Charades might have a better performance now, but when we published, we were the best one at that time. But the key thing is here, we don't need to do extensive training. Okay. The formalism that we have outlined here is easily extendable. So object clutter, if you have lots of things going on in the video, not just one event, but many events. In a kitchen, you typically have a lot of utensils, right? How do you ignore some of those? This formalism can easily handle it. And in our IJCV paper, we showed that just by introducing one kind of bond, special kind of bond called spatial proximity bond, you can handle that. Simultaneous events, same way, right? Activity sequences, just introduce temporal bonds, right? And so the neat thing is that the underlying formalism is pretty solid. And we had trouble with CVPR reviewers because they thought, well, most of the work is the same as the old work, right? So what's new? Because you just introduce a bond, but that's the power of the representation, underlying representation. Again, so thank you. I think I'm within 30 minutes.
Yes, thank you very much, Sudeep. Excellent presentation. I think we will not take questions. It's, I think, worth you mentioned it. It's just worth repeating for audience, especially from statistics, is that there is this data, video data. There are these mathematical representations, which is such a rich theory that Grenander has left for us. But now there is a need to make it a problem of statistical inference. So we can talk about not only learning these things, but estimating these things, putting confidences. And I think all the material is there when you talk about probability distribution, these energy-based distributions, one can actually talk about actual inferences, not just give answers to the scene, but also provide estimations, provide confidences with these estimations, talk about posterior distribution, sampling from the posterior and so on. And so I think this is a clear roadmap over and beyond just some sort of neural network, but actually provide an interpretation to the scene, which is so important in science, in biology, in chemistry. People are not just looking for discriminatory tasks, like is this phase 1 or phase 2, but actually explain the science behind it. And I think these are such rich set of tools to be able to do that. I think it's fantastic direction of research for younger people to learn from.
Yeah.
Okay, with that, go ahead.
Yeah, no, just wanted to point out that, you know, we are, the statistics community might want to think about, you know, statistics of graphs, right? So right now we are inferring just one representation, right? But we should be able to output distribution over possible interpretation, right? I think it's doable. I don't know the mechanics as a computer vision guy, but this is the community that can start looking at those kind of problems.
Okay, thanks very much again, Sudeep. Thank you everyone for the people who spoke at this session. Thanks to the audience for your patience and sticking through this session. We'll take a break. I think our schedule is still manageable. We are planning to regroup at 1:15 Eastern time. So we'll come back online maybe 10-15 minutes before that. So everybody, I don't know whichever time zone you are in, go ahead, enjoy and take a break and see you in about 1 hour or so. Thank you.
Thank you.
4, 38, 51. Ninety-one, 107, 135.
Rama, your microphone is on.
Oh, sorry, I'm reading something. Sorry.
Yeah,
Okay. Is Sudeep there?
yeah, I'm. Yeah.
Yeah, Sudeep, we have this big program called Viva. Okay, so we have data sets, and it's a very challenging. I told you, right? The performance we have.
Yeah.
So let us talk. I'd like to see, because the phase 3 we have surprise activities.
Surprise activities. Okay.
Yeah. So, and they would specify them. The protocol is they will give us some samples. And the samples could be video, text, or text plus video.
Okay.
So that's why we are looking at bird, video, bird, and things like that, right?
Okay.
Now, the challenge I see with your approach is that our people are very small. You know, it's
Very small. I see.
and also there is a scale variation both spatially and temporally.
Okay.
You will have a big car coming and taking a left turn, and then there is a small person walking towards the trunk and putting things.
Yeah, I think I've seen that. So have those activities been segmented out, or
No. You are just given the full picture.
full video? Yeah.
Yeah. Okay. So it's we have written some. I'll send you the papers we have written.
Okay.
Okay. This was a WACB paper last time, and this time a workshop paper. And Mubarak is actually doing better. He's my partner in that.
Okay.
But it is the reason in phase 2 they just gave no annotations. Just this data, you do whatever you want, and then test it. And then the 37 actions. In phase 3 we have same actions in a new place, so that people are not on the place. Right? So we are not. What we do, we generate proposals, moving things, and then we agglomerate them into giving action. Right. The problem is the spatial as well as temporal scale variations. Some action will be several minutes. Somebody will be carrying something, walking in the parking lot. Somebody will the trunk, put it, close and go. So it's, most challenging problem. I had to admit that. So I think I would like to try, I like formal methods. I also like them to perform.
Yeah.
Finally, right? Eventually, performance matters. So why don't we talk? I'll send you papers. You get back. I'm happy to get on a Zoom call with you and my guys. And if there is an IARPA is okay with bringing, software from outside and testing it, they don't care. Or you can try it and put your results. Okay, if we help you, run it, then you put your results as an outsider in the leaderboard. That's fine.
Okay. Yeah, this is good timing. This is something to read over the winter break. So yeah, send me the paper. So and then I can see how 2 ways to look at it. One is independent solution, and other is, can I incorporate these ideas into your approach?
We can probably give you the proposals, the things that create after we cluster them, and then maybe you can reason with
use that. Yeah.
Things like another thing. I don't know if Anuj is still there, but I met Ulf in 1986 when I visited Brown. He had a lot of respect for signal processing people, and he said, "Oh, they're okay because there's math."
Yeah.
Not like Asriel. Because Asriel is a mathematician by training,
I didn't know that.
Yeah, but his method was more like heuristic, he was kind of, Asriel, In fact, they invited Asriel to give a talk and then asked him to contribute a paper for the book. Asriel wrote a 4-page prose. As usual, he was saying linear Gaussian models are hopeless for computer vision and so on. Okay. So David Cooper approaches me without ceasing to ask, Rama, we have a problem. We really can't put that as a chapter. Can you please make it nice. I said, okay, sure. Then I threw in some Markov random fields and this and that and made it a 12-page thing. And so it's interesting how Grenander and Asriel saw each other. Although we got Phil Thrift. He is Grenander's PhD student as a postdoc. For a year or two, he was with Asriel. He was not very effective because Asriel's way of thinking was, when he was right. He said, if you don't do hierarchy, if you don't do nonlinear, if you don't do non-Gaussian, you have no business in being vision.
Yeah.
And I couldn't shake him off that. He thought everything else was just guys writing papers, right? He said, so I told him, Asriel, you've been saying this for 20 years. Why didn't you do something about it? That's a good question. Yeah. But Asriel was not trained in probability or statistics.
Yeah. No, I think he had the right sense. I think the hierarchy is important.
Yeah.
Without hierarchy,
Asriel had a great thing about discrete geometry group and all of that stuff. He would write paper. When we went from Bangalore to Mysore, he wrote a report. Okay. And right, sitting in the back. I saw him doing that. I was sitting next to him and his wife, and he just keep on writing. I said, Asriel, what is this? And with the potholes and this and that, he just wrote the paper. So he was a brilliant man, but he was not trained in statistics, and he felt bad about that when people threw. Like when I went to work with him in spring '79, every Friday we'll have a group meeting, and he said, anybody wants to give a talk? I said, yeah, I'll give. So I gave a talk about time series, sufficient statistics, classification, all of that. And he was very happy because he said, you explained to me these things that I always wanted to learn. Oh, he was very happy. But then I realized Kashyap was a better researcher to be with because Asriel was very high level. And so I told Asriel.
He was like I think Asriel is like a banyan tree, right? And Kashyap was also like a banyan tree.
So I told Asriel, I told our style is not matching. I want to go back to Kashyap. He said, okay. And he felt, okay, then, but see, he didn't get upset. I still remember we were talking to him as he go down the steps. He likes to get his soda and he looks at it, puts it, okay, this is what I'm going to do. You can go back to Purdue, do a PhD, but I'll make you a faculty research assistant here. You come here during the breaks and work with me on some things. Okay, look at the generosity. Most people say, get lost, you stupid kid.
Yeah.
After 4 months, I said, I'm not going to stay. So, but it was difficult navigating the two giants, and I was in the middle. So I made a decision in July 1979. I'm just going to work. 16 hours a day, 7 days a week. Maybe these two guys will see it, then leave me alone, right? That's all I did for 2.5 years. I was done with the MRFs and so on. So I'll write papers, I'll bring them as reports. I did a clever thing. First, I'll bring as a report in Maryland because Asriel will edit that. Then I submit it as a paper. No problem. So I learned. It's like, as I told you, two parents, divorced parents, how the kid manipulates to get what, say daddy is nicer than you and then mommy gives candy. That's exactly what I did. I figured out. So I will tell Kashyap, Asriel, he puts students' name first all the time. So Kashyap had to put my name in a couple of papers. Otherwise, he always had Kashyap this, Kashyap that.
Okay, I see.
Papers he put my name. But I kind of started. First, it was difficult. They were both, because they have never worked together. And also, Kashyap didn't want to be seen as being too close to Asriel because Fu and Asriel were,
okay.
And Kashyap and Fu were very close. So I saw all of this interesting. Every time I go to Purdue, Fu wants to know how much money Asriel has, how many people does he have. Then Asriel would like to know, tell Kingston to accept all my PAMI papers. I was like the Hanuman, between the two groups. Anuj, I was just talking, I don't know if you heard everything I said. I met Wolf in 1986. We had a meeting at Brown, Wolf, Stu, and Don, Don McClure, Don Gieman, and some night vision people and so on. And at that time, Wolf expressed respect for signal processing people. He said, they're okay, he said. But he was not too pleased with Asriel. He said, Asriel, math is not or something, Although Asriel is a PhD in math from Columbia, his work in computer vision was of a different kind, discrete geometry and so on. That he will generate theorems left and right, but it was not the same what was needed. And Asriel regretted that he didn't get a formal training in probability and statistics. He felt that. He felt that Grenander had an edge on him because he is, is structure as well as, Grenander is the one who was able to put probability on structures. That is not an easy job. If put vector, no.
But if you read, if you look at this book,
I have that.
Book, it says, in the introduction, it says it does three things. One of the, it talks about structures.
Yeah.
But then it talks about probability on structure. That's one of his bullets.
Yeah.
That's what this book accomplishes.
To me, that was very, very inspiring. And and then there was a meeting, they invited Asriel and they wanted a book chapter out of him. Asriel wrote a 4-page prose. Oh, they were very unhappy. And so they didn't want to offend Asriel. They contacted me, Dave Cooper. Rama, can you make it a little longer and put some equations and so on? So, okay, I put time series, I put Markov random field. It was all Asriel's name. I didn't put my name on it. I still remember that. But it dawned on me, statistics has problems with hierarchy. Although Alan Wilsky did a paper on scale and MRF, but he imposed a very artificial scale just to maintain the math, okay? So that was not really like what we are doing in terms of convolutions and subsampling. I have a book chapter. I'll see if I can Xerox once I get to the campus and so on. Multi-resolution time series analysis. I have a book chapter. I discuss how when you go from AR to you put a pyramid, it becomes ARMA, and then there are multiple values. I wrote this is well known in econometrics. They have data at city level, county level, state. But so I was trying to come up with something that will challenge Gabor filter from at the time. Remember, early 80s we had Stefan Mala, Dogman. They're all doing Gabor. It was very easy for them. Scale and orientation, they'll get features. So I tried that, and the inverse problem was hard, given that ARMA, going back, it's impossible, So then I left it, and then we wrote a paper in transaction image processing, multi-resolution GMRFs. It is not a strong paper. It's hard. That's when I learned statistics has issues with skyscrapers. It works well for ramblers. Not for a top, right? So, and then of course you throw nonlinearity. But I think this is an opportunity.
Yeah, I mean, with the computing we have, if you're adding layers, it's in some ways just a computational burden. Conceptually, it's just repetition.
That is true, but there's also a correlation, right? This guy depends on a bunch of guys here. The correlation structure gets complicated.
Yeah, I mean, these fully Bayes, I mean, they have this layers, priors and then parameters and then priors on parameters and then.
But I'm talking about 20 layers. See, they are all shallow, 2-3 layers. Because as you know, if you propagate little probabilities and multiply them everywhere, they become smaller and smaller and smaller, like the vanishing gradients. It'll be vanishing probabilities.
Yeah, the equivalent problem.
Yeah, it's like that. That's what the problem was. We couldn't train taller networks because of vanishing gradients. If you have a taller Bayesian graphical model, they are vanishing probabilities.
But I think this is a good discussion to have because, when I go like to a statistics conference versus a computer vision, sometimes it's the same sort of fundamental problem being discussed in a very different language.
Yeah.
And so it's good to be able to tell them that these are the issues.
Yeah. So I, I felt when models get difficult, Bayesian depend on Laplace approximation. To me, that's a little.
Well, now it's.
I have to tell you about this. The way I learned about Laplace approximation of the Bayesian integral was Ulf gave me. There is this book by Szego and Polya. It's a book on, these are two mathematicians, pure mathematicians, and they have a handbook on a set of exercise problems in mathematics for math students. So he just came to my office. At that time, I was at Brown and went to that chapter. And he says, this question, I'm having some difficulty sort of proving it. Can you do it? And it's very simple. You just take the Fourier expansion and you stay up to the quadratic, you throw away everything else, it becomes Gaussian, you have closed form expression. And I in Gango's style, I walked into his office, I said, yeah, I can do it.
Yeah.
Here it is.
So
and
then, I learned it.
No,
Yeah.
but the thing was that he would never say, go use Laplace approximation. He would say, can you help me prove? Of course, he knows how to prove it.
Yeah. So
But this was his way of saying, maybe this is useful in what you're doing.
yeah, when Kashyap did for auto regression, the likelihood is much simpler. And so he'll have an inverse gamma, you'll have a Gaussian prior for the parameters of AR and then inverse gamma for variance. It was easy to integrate, and he used the same technique for an information theory paper. But when you have ARMA, the likelihood is messy. So I was asked to develop a BIC for an ARMA model. And so then that's when he said, Rama, you can take the Taylor series expansion. And then he gave me Erdely's asymptotic expansions. So I went and read, and actually this is discussed by Dennis Lindley in a 4th Berkeley symposium. You know, they used to do those things. So Dennis Lindley has used it, and he called it maybe a different name. So anyway, interestingly, one of my students took a large deviations class, Kevin Zhu. So he was saying, oh, we are learning a lot of interesting things. I said, so what are you learning? And then he showed me this Laplace. I said, are you kidding me? I did this as my PhD student, and I threw him the paper I wrote. So I said, there's nothing new under the sun, kiddo. Don't. Anyway, so that is, to me, Bayesian methods that are there because of the ease of mathematics. They're not, so it's that, I don't know how you square all of these things. But anyway, this meeting is very interesting, Anuj. I mean, it's.
Yeah, we'll see. We have some people from the other side. I'm hoping Bin Yu can make it. The next speaker. So there are some very strong statisticians.
Yeah.
On the schedule.
I came across 2 people at Hopkins in biostatistics. One of them is a young person. He's from UCLA, I think. Akihiko Nishimura, Bayesian hierarchical model. He's very bright, very bright. Variational Bayes and all of that is a very young person. Scott Ziegler, he's a biostatistics person. So,
yeah. They have a very big department in biostatistics.
Yeah.
In fact, the history of this particular section in ASA, so this is a section in imaging. The history of this section is it was started a few years ago by the people who primarily do neuroimaging data analysis.
Yeah, right.
And those are at, and some of them are at Hopkins Biostat. They started this section.
Yeah.
Ciprian and Martin.
Yeah. I have not been to campus. I only went 2-3 times to pick up my computer and so on because we are on the online thing. So I have not met many. I have not actually met Mike since I joined Hopkins. It's all Zoom calls. I have not met him in person. My office is Mike's old office in Clark Hall.
Oh, okay.
Yeah,
so
yeah.
Is he in some ways your house boss?
No, he is not in Clark. He is a director now, so he is an administrative building. That's where they want them. I have his office. They redid it, and I can send you a picture of my office. But I have not actually been there more than 2 or 3 times, just because maybe not before next May, assuming vaccine works.
I mean, it just almost feels like there is just too much center of gravity at Hopkins. When I was looking at the people I wanted to invite for this workshop, I had to stop because it just felt like too much Hopkins. I mean, Laura Yunus, Michael Miller, Ciprian, Martin, all the people who are either associated with this section or doing imaging and statistics, and Alan and you, and I said, come on. I mean, it's going to be a Hopkins show. And so I had to, it's just a lot of, suddenly there is a lot.
Yep.
I mean,
Don Gieman and I are talking.
Yeah.
Don is an amazing guy. Yeah, he's still very active. And I'm having dinner with him and Mike Miller And suddenly Don says, Rama, is your 1983 information theory paper part of your PhD thesis? I said, yeah, chapter 4 and 5. So, the guy is just remembering that much. That's the one where I did that estimation, choice of neighbors and all of that, spatial interaction models, we call them.
Well, I'm amazed at your memory because you could tell the years of all these interactions you have had. I mean, 70s, 80s, 90s, you're flowing in and out during your slides.
Yeah, Rama's memory is like a computer memory. He never forgets.
Yeah, it's amazing. You could remember.
Yeah.
I mean, I'm within a decade.
No, it is a gift and a curse. I'll tell you why. I remember all the stupid things I've done too. And I rehash and I say, why the hell did I do that or say that? I mean, really, you can go into a psychological loop, because I remember everything. And I have not always said the right thing. So I said, my God, suddenly I'll say, why did I say that? And my wife says, what happened? What happened? No, I'm thinking of something I said to him in 1978, on this occasion, and suddenly it came to me. So it's a curse. But it's a gift because I can tell the students, go and if they see something and I say, come on, go and read that, So it's both. Asriel told me, you are where you are because of your memory. I said, Asriel, I wish you had said you are where you are because you're intelligent. He said, Ram, it's all the same. I tell you, hey, Anuj, what people don't realize is the gift we have when we work with such brilliant people. I mean, you had Mike and you had Grananda.
Yeah, no, I mean, it's amazing.
I had Kashyap. I worked very closely with Asriel as a student and then as a colleague for 13 years. And you have to say that these people were not where they were. They were there because they were amazingly brilliant and generous. And when I think about that, I came across Slansky, as I told you, the positive interaction. I read a book. I said, Jack, you missed a point. You mentioned conjugate prior. You mentioned sufficiency. You didn't link them. It will be nice to have a section, Bayesian learning using conjugate priors, how sufficiency is there. You have the conjugate prior and you can do it. First, he was not sure. He said, what is this kid, a third-year PhD, telling me? But he said, okay, send me. I sent it. And he included it. He thanked me in the introduction. I think he did not have done that. That was amazing. And Tom Huang, of course. And Fukunaga was a brilliant teacher. I took his class. He gave 5 exams. And then he asked me, do you want to work with me? I said, I'm with Kashyap, so I can't change now. Yeah. That is a gift to be able to spend some time with these big shots. Amazing.
Yeah, no, I agree with you. I think Miller says that about Ulf too,
Yeah.
He says it's so fortunate that we crossed that path.
Yeah. No, definitely.
He says we would have been doing completely different things.
Yeah.
We would have been inverting matrices or...
Kashyap was doing time series and then he was still thinking in terms of 2D causal extensions. I came to him with Besak's paper and I said, no, we can just go to non-causal. Why do causal? And he actually wrote a book chapter. We had a image modeling workshop in 1979 and he had a paper there on that. So basically I brought my own PhD thesis topic to him and I returned from Maryland to Purdue. So next 2 years, I was just doing that. I wish I had read Kinderman and Snell a little bit more detail. And I was pretty close. I didn't know simulated annealing, but I did formulation of map restoration. And then we just did the usual steepest descent gradient. There's a paper we wrote. And then suddenly the simulated annealing showed up. I said, holy cow, that's interesting. But okay, let me ask you a rhetorical question. Simulated annealing has 24,000 citations. People mention. Is it being used anywhere really in operationally?
Yeah, I don't know.
I mean, at least in academic circles, you surely see it. I can't say for sure in practice.
Yeah,
in industry.
Okay, that's the first question. Particle filters, same. People are using salt.
That's a touchy-feely topic.
I know. But all I'm saying is, It was great. You guys did it. And then, Zard Blake, etc. But people are now using just salt, because finally we can't wait. So when I'm teaching image understanding now at Hopkins, I told them, any solution that requires iterations, no go. SVD, everybody likes, because you put something in, it gives something out. So see if you can produce an SVD-based solution for what you do in computer vision, you'll be fine. Deep learning is okay because training is separated from testing. Training you can spend all your lifetime, but testing is just an inner product, whatever, right? It's almost the same way. If you have to do the same iterations for a test, deep learning wouldn't survive.
Although Rama, there's a new architecture that's coming, computer architecture, or quantum annealing.
Yeah.
So there's a company in Canada that's actually selling time to do quantum optimization using quantum annealing.
Yeah.
So I don't know if some of the simulated annealing stuff can be mapped there or not.
Right. Yeah, it's a special purpose hardware. I agree.
Yeah, it will be special purpose. Yeah, but in real world, I mean, yeah, you're right. I mean, I'm thinking I haven't seen any solution that's out there.
Yeah. So my question is, that is the most cited PAMI paper, and normalized cut also. I mean, it was very elaborate and so on. I don't think anybody can use that. So I want to write a rhetorical question. Why are the best cited PAMI papers are not being
used?
Particle filter, simulated annealing.
Maybe they ran through their course, and that's it. I mean, it was a good 5-10 year run. Is a good run.
But all I'm saying is FFT is still there.
Yeah.
I mean, SVD and FFT.
Yeah. So when I teach, I told my kids, you see, I did the structure from motion, extended Kalman filter, blah, blah, blah. I told them, I did all of that because that's the first time we did that. But then factorization theorem, Kanade watched it and he said, wait a minute, orthography is fine. I'm going to do it. I'm going to give an SVD-based solution. And it took a big jump, right, Tomasi Kanade, because the inputs are exactly what I need. And I'm going through a particle filter, Kalman filter. He sends it through SVD, and there is shape matrix, there is motion matrix. Yeah, it's not perfect, but it looks okay. And I said, that's Kanade's genius. Yeah.
I mean, to have an idea which survives for eternity in our world.
Yeah, SVD, right? So that, and I told them many examples like that, how the first attempt from vision tries to solve the problem in its entirety, and then some people cleverly watch that, and then come, even normalized cut is one more step than what Wu and Leahy did in 1993. Instead of min cut, they did it. And I told my students, for 5 years, that paper was sitting there. I was actually on that kid's PhD committee, but I never paid any attention to what that was. And then Jambo Shi comes, and then he links it to spectral graph, and immediately it becomes such a beautiful paper. So I tell my students, when you read a paper, every paper has ideas that you can work on. If you don't see it, that means you have not read the paper properly. The example is this. She looked at Wu and Leahy. I said, holy shit. They said they're having problem with small segmentation things. How can I fix it? Let's normalize it. It's a pure intuition, maybe over a cup of coffee. After that, the mechanics comes, right? But so research is, that's why I say every paper has ideas. So you got to just look for it, because nobody has a complete solution for anything. So I'm teaching machine perception at Hopkins in EC. I finished it. And so it's this kind of, now I teach mostly from papers, so I can have these kinds of conversations with them. The top-cited papers, Canny, normalized.
I think that would be a good class or a seminar.
Yeah.
Just the history of these papers.
And LBP. I tell them LBP is ridiculously simple, but look at the longevity of that thing.
Yeah, I mean, there are times you don't read a paper anymore because you say, well, that's too simple.
Yeah, SIFT the same way. So I do SIFT, Canny, normalized cut, LBP, and then, all of the factorization theorem and so forth. And of course, AlexNet. If you don't do deep learning, they want to call the course History of Computer Vision. So anyway, so when are we starting? 1?
1:15 is our
Okay.
start time, but I'm hoping the guy who is host.
Okay, I'm going to grab my lunch and I'll be back.
Yeah, go ahead, take a break. We'll be, in about 20 minutes, we'll come back online.
Okay.
Sounds good.
Hi, Lucy.
Hello. So I made you the co-host, so you should be able to share screens. So we are waiting to hear from, I think Bertrand is there. Let me just check. Bertrand, maybe he left. He came in and left. The third speaker. Actually, we're waiting for all the three speakers.
We still have 10 minutes.
Yeah, that's a good thing that we have 10 minutes. But I was hoping they can actually check, you know, test their presentations before they go on. So you will have to introduce the speakers. Would you like some summaries from me? And shall I send them the bios to you? Short bios? Or you think you can?
I'll be very brief. I believe, yeah,
it's fine.
Yeah, because I believe we will have questions from the audience. So
yeah, that's fine.
Yeah.
And whichever you feel comfortable with, and I mean our schedule has some gaps, so if we are running a little bit late, that's fine too, but not too late.
So, Luigi, what's your plan for coffee break? So we still stay or
we will leave. No, I think people can go. We leave the session on, so people can leave on, and I think Al is here, so maybe let me make sure. I will make Al a co-host. This way he can test. Yeah, so I think we will just leave everything on. So anybody who wants to just take a break for coffee is fine.
Yeah.
Al is still connecting. I hope his connection is fine. Yeah, Al, do you hear me? You should disconnect and then connect again.
Anuj, thanks for organizing it.
Hey, well, how are you?
I'm okay. Ting Ting, how are you?
I'm okay.
Very good.
I like your virtual background.
Oh, thanks. It's brain.
Is it your brain?
Oh, no, somebody else's brain. Anuja, I'm actually interested. You have a paper on the elastic graph matching. Is it published now? Where?
We have it submitted, but I think it should be on archive.
Oh, okay.
We have it for brain networks. There was the application.
I'm gonna mention it briefly tomorrow.
All right, thank you. Yeah. No, there are several, it's an exciting field. There's a lot happening there. So we have some new ideas too, but I think some version of that paper is still in review.
Okay.
Yeah, I look forward to your talk. I got your email, so
Okay.
it's going to be a good session. Ting, do you have any way to contact Bin Yu?
Yeah, that's I think let's email her.
I have not heard from her today. I mean, I usually get very quick reply from her, but I just want to make sure there is no issue in logging in for her.
Is her room link the same as mine?
Everybody gets their own, and I don't know how it works. I think everybody gets their own link in some ways.
Yeah, so
maybe not. I think this, if you give the link and they can come in, then we have a process of admitting them in.
Okay.
As it so happens, none of the three speakers are here at the moment.
Still have 3 minutes time.
But I'm sure you can step in as needed.
I know you will be sweating, but still.
It's very cold outside, luckily, so the sweating part is okay.
I'm not so sure the link is correct, but it's a very long one. So,
Anuj, I'm also wondering whether there could be confusion about time zone.
Well, we have written Eastern, that's for sure. I think I told for Bin Yu for sure. I told Eastern. I think she asked me specifically, and I said Eastern. It's on the schedule also. We have written it.
Let me see.
said I can actually go in and invite somebody. Do I invite somebody? I don't see if I have to invite somebody, how to find out the address.
Just send an email to Bing. So hopefully,
Okay.
yeah.
I'm going to call Al just quickly. Hey Al, are you? We just want to make sure you are being able to share your screen.
Oh, okay. That's a great point. Let me see. Let me try to see if I can do that here.
Because as things stand, you are the only speaker present for this session.
Ah, okay. Well, good. I'll take advantage of the fact that you're complete and absolute attention. Can you see my screen?
Yes, it just came up.
Table, yeah.
Great. Okay, fantastic. Great job, Anuj, so far. Really, really fantastic lineup.
Oh, thank you. You know, there's quite a bit of range we are covering. So the hope is that it hits somebody. Everybody can find something to like.
Yeah, let me say hello to my good friend Al.
Hello, Rama. Great to see you. Great talk this morning.
Thank you.
Yeah, it's too bad you're not in person because you know, some of your off remarks are better appreciated, you know, fresh and not filtered through this small internet tube we have. Has been our
I didn't say anything nasty about anything.
Not about me. So.
Well, yeah.
I'm not so sure the link I sent to Professor Yu is the right one because I use my link. So.
Oh, yeah, that's a good question. But she should have her own link, and maybe you know, if she's having some struggle with logging in, I hope she sends an email about it.
She just replied. She said she thought it was tomorrow. So maybe we will see her soon.
Oh.
Because the link they sent it's mentioned is on December 5th actually. Starting from December 5th, the link.
It should be both days.
Yeah. But on the yeah, now she's using mine. Let's see whether she can. Yeah, she's here, but she's under my name.
That's okay. She can give a talk under your name.
Hi, sorry.
Hi, Professor. Yeah,
I have it on my calendar tomorrow, so I'm so sorry. But at least good thing send me an email. I'm not too late. I hope.
No, that's okay. You can take your own time.
Yeah, I have it on my calendar tomorrow for some reason.
I hope we didn't mess it up by giving you the wrong.
We can figure that out later, I suppose. But okay, thank you. Sorry, I'm a bit late.
So we haven't started yet, so maybe we can start in a minute. So Ting Ting is going to be the session chair, so please go ahead and get us started.
Yes.
Okay, maybe 1 minute. So starting.
Oh, I'm even early. Wow.
In 1 minute, yeah. Okay. Okay. So yeah. Okay, I guess we can start. Welcome back, everyone, and welcome to the first session in the afternoon on high-dimensional data analysis. We have 3 wonderful speakers in this session. So first, before we start the talk, I want to mention that if you have any questions, please leave them in the chat box so we can address the questions at the end of the session. Our first speaker, also the plenary speaker of the session, is Professor Bin Yu from UC Berkeley. And I believe most of us have read Professor Yu's work before, and he has a very long list of achievements, including being a member of the National Academy of Sciences and the American Academy of Arts and Sciences. And we all are eager to hear her work, so I don't want to take any time from her talk. So let's welcome her to present her recent work on theoretical data science. Okay.
Thank you. So how much time do I have?
45 minutes.
Okay. Thank you. Thank you for having me here. And it's really great to talk to people who are interested in imaging data analysis. I think it's really one area that we should really make all the statistical training students really familiar with imaging data, which is just appearing everywhere as a basic form of data. So what I want to share is that the first part is actually a general framework me and my group have developed over the last 10 years called PCS. We put the umbrella under theoretical data science. Theoretical means truthful, so coinciding with reality. And the project actually I will share related to images is one of the motivating projects that have been going on for the last even 7 or 8 years that really helped to form this framework. So a lot of my interest developing in this PCS framework really started 20 years ago when my late colleague Leo Rahman really encouraged me to get into machine learning. And then in 2001, almost 20 years ago, he published 2 important papers. One is the 2 cultures, the other is random forest, which is a separate talk. We've been following on that to add stability and to make a random forest interpretable. And this is just an overview of machine learning. And you will see that all these different areas can be, or statistics, used this framework of PCS, really marrying machine learning with statistics more tightly. A lot of my group's work in the last 10 years have been in biomedical problems. And now there's also like a more hype name, which is AI, and just affecting everything in life. And underneath the hood of AI is really machine learning and statistics. And I agree with Bill Gates, who said that AI is like nuclear energy, both promising and dangerous. So it's really how can we make things trustworthy, reliable. And data science is really a key element of AI. Data science has 3 components: computer science, math and stat, and domain knowledge. And there are 2 complementary approaches for trustworthy practice or reliable practice. One is we share best practice to maximize the promise and being preventative. And the other is really risk management to reduce the danger through intervention. So the approach I'm advocating in this talk is really share best practice, best concept, best principles to maximize the promise and do good work before things go wrong. One area I can see what my group has been working on are called scientific machine learning. It's really used machine learning for scientific research, from extraction from data, discovery theory, and knowledge, and also builds scientific principle, domain knowledge in machine learning algorithms. And you iterate in between the 2 steps, and then it's a high standard. I think that machine learning validation is subject to scientific standards. I like to think that we have to consider data science lifecycle as multi-step, multi-module, and multi-phased process. I think we have to look at it holistically, and with also people involved, and we're making human judgment calls. So it's domain question, data cleaning, collection, cleaning. Data collection is not like you have choices. What type of data, multimodal data you use? Image, text, if in precision medicine, I'm going to use doctor notes, medical imaging, and also genomics data and demographic data, medical record. So all of this is you have judgment calls and make perturbations. And then you go to the more traditional data visualization, data modeling, and you can easily have 20 or 100 models, right? How do you navigate this proliferation of models? What's missing, I think we need to agree on some quality control and standardization of process. And of course, these steps are not completely linear. You go back, you do data cleaning, you realize your question cannot be answered by the data, so you go back, reformulate the problem, and you do modeling, you realize data cleaning was not done right, you go back, reclean the data. So all of this has a lot of interaction back and forth loops. It's not just one linear circle. Veridical data science we define as extract reliable, reproducible information from data, and with an enriched technical language to communicate and evaluate the empirical evidence in the context of human decisions and domain knowledge. So we need to have a goal, it's human decisions, or you generate knowledge to go into a textbook, but we need to emphasize empirical evidence. And we need to enlarge our technical repertoire to communicate what the complex problems we're facing. We cannot just always stay with the traditional statistical terminology. It's just not enough. So for the rest of the talk, I'm going to share with you the PCS framework we developed for veridical data science. I see veridical data much bigger, and PCS is just one approach to achieve that, or towards that. I shouldn't say achieve that. And the second, I'll share a neuroscience project that we have images and to work with, and use deep learning. We call some deep tune to characterize V4 neurons, which is a very difficult human visual cortex or primary visual cortex. And if time allows, I might not have the time, we talk about interpreting deep learning models. So the PCS framework for veridical data science, the paper finally came out, took many years to write. And in the end, I invited my former student to join me to finish. And this is just came out actually PNS 2020. It's really taking predictability from both machine learning, actually also statistics, and computability from machine learning, and then expand on statistical inference and certainty perturbation idea to the whole data science lifecycle. It bridges Leo Breiman's two cultures. And the PCS framework really connects science and engineering. I see data science as both science and engineering. And predictability and stability embed two important scientific principles, prediction and replication. And computability is not just scalability, risk of convergence algorithm. We include data-inspired, well-designed simulation to help argument the lack of data in many complex problems. I started getting on the path of stability about 8 years ago. This was actually my 2-key lecture for Bernoulli Society. At the time, I was working on LaSue with neuroscience problem with fMRI, trying to interpret the model. And then it occurred to me that if my collaborator, Jack Galan's lab, collected like 10 minutes less, I don't want to end up with different kind of interpretation for the model. So the idea of data perturbation came. And then I was trying to connect with 2 keys work about robust statistics. So I put it together, put perturbation, both model and data perturbation, and advocated stability as a minimum requirement for interpretability, reproducibility, and more recently for scientific hypothesis generation, or I'll call scientific recommendation system for intervention design toward causality. So the idea is that use predictability as a reality check. Stability comes after predictability. Constants are very, very stable, right? It doesn't really do anything. So you need to check your model captures reality, and then you seek stability. You can think of stability as shaking every step of this data science life cycle. Usually the shakes come from human judgment calls or perturbations, and you make sure the system doesn't break. That's quality control. And we have to, the shaking exponentially explode. For every step you have 2 possibilities, So usually we do more marginal perturbation, fixed S and at least perturb 1, 2 data cleaning methods, 2 graduate students. Would you get the same result? We take 226 people now at my talk, give us the same problem. Would we end up with 226 different recommendation for a domain problem? That's called researcher to researcher perturbation. So all that question, I think we need to be forthcoming and transparent and write the documentation about it. There's no magic, but we can be more transparent than what we are. The PCS workflow really try to incorporate the 3 principles into every step of the data science lifecycle. P in the domain formulation as a stand-in for future. We never do data analysis just because we care about this data. It's always about something else. In the future, we have new patients, we have new samples. There's always something that we don't have and we generalize. So that's P stands in for future. So even for problem formulation, you want to think about that instead of, oh, I only care about the data I have. Never even in my work that you only care about the data you have. It's all about something else that you hope to extrapolate to or generalize to. And computability is always there. And I do think we have underutilization of good data-inspired simulation in statistics in particular that we can really take more advantage of. And then stability, even linguistic stability, when how multidisciplinary teams work together. The same English words don't mean the same thing. I talked to a cancer biologist who in her theory about microenvironment of cancer organization, she used the term matrix. Over dinner, I tried to tell her that my matrix is different from her matrix. It didn't work. So if I work together with her, then I'll have to make sure that her matrix and my matrix, we have to find something else to really differentiate the 2 meanings of the matrix. So even at the very basic linguistic level, when you formulate a problem, you have a stability issue. And then data cleaning and modeling, all of that. And which subset of data you choose to do visualization, what plots you choose to convey your main message, right? There's a book called How to Lie with Statistics, right? That's basically saying that you choose the particular angles, you get different conclusions. I think we need to do stability and then to make sure we minimize these unintended consequences by judgment calls. And then we're also expanding PCS inference, PCS to inference, have perturbation intervals. And this is very much still in development. We have some very good results from understanding epistasis in genomics. And this is just an example where they have video data, right? This is a survey of adult skills, which is OECD PIAC organization. And they actually go interview people at different countries. And they're now collecting data, which is video recording of them answering questions, right? So, and they test literacy, numeracy, and problem solving. So this is something used to be by questionnaires. Now it's video data, right? And then you transcript this information, maybe to some form, but the original data is video or images. For this, even in this video data collection, you have the choice of video versus audio, who is the test taker to record, and what's the angle you can take the video. So all these are perturbations of human judgment calls. Would you get the same conclusion? And choice of models, how you precision your recording equipment, and transcription method by whom, and choice of topics. So all of this, we're making these judgment calls before we even have data. And this, I want us to have a documentation and to know the process is well documented. And these are the factors that we should do some perturbations to make sure the conclusion doesn't change. There's traditional data perturbations, which I'm putting under the umbrella of PCS, like cross-validation. This is all implicit assume at certain level ID or independent, weakly dependent permutations are okay. And the more recent one I want to put under the umbrella is the data model choices. This is also a perturbation, completely legitimate under the PCS framework, but we don't need to build a probability model. It's just much more complex. It's a perturbation, and just see very engineering-like. You do this perturbation, would you get the same result, like in and out, like the system. And also PDE produce synthetic data that can also be viewed as a legitimate form of validation if you have a perturbation, if you have a good documentation to argue why that can be viewed a legitimate way of perturbation. Then you don't have to develop another pipeline of analysis to put this synthetic data in. That's a way to integrate information from the PDE. Another way, of course, you can put the PDE model as a mean of your stochastic modeling. That just takes more programming and more work. So this has a very easy access, transparent, modular flavor, which is, I think, desirable. And people have been also using invariance of stability under different environment as like step towards causality. And differential privacy, which is being implemented for 2020 US Census, is a form of stability. And the well-known adversarial attacks to deep learning models, right? All these medical images, if you just do some adversarial attack, the diagnosis flip, right? This is pretty easy to do. So it's a stability issue. Another well-known example is actually about 10 years ago, Harvard economy wrote a very well-known paper called Growth in a Time of Debt. And it was used by people in Europe and UK to argue to support austerity policies. So their conclusion was that high debt GDP ratio is bad for economic growth. 4 years later, 4 other economists from I think University of Michigan and Amherst corrected some cleaning problems and coding errors and invalidated the conclusion. There were 4 data points from New Zealand was somehow just missed, not used by the early paper, and there was some coding error, and then you get a different conclusion. So this is really consequential. That should have done maybe by 2 different teams, the same analysis. For important conclusion, replication or stability analysis has to be done just for the reliability. As I said, I really started this PCS building on 2 kids' work of robust statistics and putting together with sample-to-sample perturbation. And there are many other forms of the model perturbations, right? You can have, I said, robust statistics. You can regenerate the SU, which one you use. You have sensitivity analysis. I'm putting it, unifying them in the same framework of perturbation. And then the researcher-to-researcher perturbation, right? So we have well-known 9 climate models from 9 different teams. And if you try to predict the global temperature in 90, you have a range of prediction from 1.5 degrees to 5.5 degrees. So this is good. We're looking at together. This is really a form of perturbation interval. So to summarize, we make so many human judgment calls in the process, and we need to be transparent and documented and perturb the human judgment call. We don't know which one's better. Then we do at least 2 versions, keeping everything else because that's more doable, and we have a linear possibilities to basically redo the analysis double the times. If you do every possible combination, that's an exponential explosion, can be quite costly computationally. As I mentioned earlier, right, you have reality and you have models. Models are constructs. They use mathematical symbol. They don't have correspondence with reality unless you make it. Is it a bridge or not? It's your job, our job, to make sure there's a bridge between the two, not just look like a bridge. With quantitative and qualitative narratives in a reproducible documentation put on GitHub, say Jupyter Notebook or R Markdown, and we document our judgment calls. This way, it helps you to be more clear thinkers and help others to trust your analysis or not to trust. Otherwise, we're not on solid foundation in our enterprise. People ask me how to choose perturbations. It's a very, very good question. You will never finish the job if you try all possible perturbations, right? You just keep doing it. But if you pledge to stability principle, then you want to be very careful to choose your perturbations and argue. You do enough, but not more than enough. So you document, you think it's enough, but you don't overdo it. Because cherry picking is really encouraging you do as much possibility and you pick the best result. But if you pledge to stability principle, because if you try too many, some are not legitimate, you end up with nothing, because stability set, you should really, after you pass the predictability check, you should try to look for consistent and stable result across different methods. And documentation is a big part of PCS and should really be taken seriously. So I just started implementing PCS documentation in my group. OR project has a PCS documentation now. And for my class. We also extended statistical inference under the PCS framework. I think if you look at what we do, we provide data evidence as only one source of evidence for domain expert to do decision making. We don't have the power. So p-value less than 10 to the minus something, then we proved it. We don't have that power. We don't have the evidence that we have that power. So we want to provide our data evidences in a transparent manner. And but it's not really p-value's fault, as our colleague Benjamin said. It's really how we use it. Often have very small p-value because we use normal approximations, which are not legitimate when you look at such a long tail, like heavy on the tail. And we also want to think harder about when we use a random variable. It took me 25 years to realize that when I write down X, I did for many years. Now I don't. In my first class teaching statistics, it's assumption. Now I introduce random variable halfway through my class and introduce very, very carefully. Why? Because you have data set, you don't need a random variable unless you can imagine another situation where the data can be collected, can be viewed as another realization of the same random process or same random variable. Otherwise, you don't need the random variable if you only care about this data set. Therefore, implicitly, assuming there are two physical situations, data can be collected and be tied together through this random variable notation. And that's a stability assumption. When you don't have stability, when you don't have your probabilistic assumption substantiated, supported by empirical evidence, how can we talk about p-value? What does that mean? And often p-value measure model bias because all our p-value most of the time derive assuming the model structure is correct. And often they're not. I'm really against using true model, even often slip using true model in my class, because it's very confusing for beginners, for students. You tell them there's a true model and later you have to say, actually the true model is not true. I think it's better we just talk about approximate and postulated models. And also the PCS framework, we want to go beyond probabilistic model, like the 9 models, climate model, they are not a probabilistic model, they're often PDE models. So, but under the PCS framework, we expanded the statistical inference so that we can talk about such model called perturbation intervals. If everything's kosher under probabilistic models we used to do in classical statistics, everything needs to go back to classical statistics. So this is not, it's really expanding on classical statistics to take into account the reality that what we do in the whole process. The PCS framework for inference in a nutshell is really look at stability at different levels and add important prediction screening for reality check. If you have two hypotheses, you want to compare them first in terms of prediction to make sure the model you're going to test actually fits the data relatively well. Otherwise, you don't need to do p-value, just they're both rejected by data. So you don't have to choose one. Try to avoid the situation. You're choosing two horrible models, neither fits the data. But because of the Neyman-Pearson framework, you choose one and you think you proved one. So use prediction screening to remove that situation. If neither fit, that's it. You don't have to choose one. They're both horrible. And then you can look at different perturbations and you argue appropriateness through documentation and end up with perturbation intervals for the target value. And this is a case that we did using PCS inference for feature selection and compare with, so the wrong method without consider post-selection inference, and then the one with post-selection inference with lasso, and you show that PCS, actually the wrong method worked pretty well in terms of ranking the features. So this also brings up the point that what matters is also the metric. The PCS inference is really a general framework and can deal with important features selection. And the post-selection inference with adjustment under lasso is pretty narrow and pretty heavy computationally. And one thing was surprise to me too, that if you just selected the useless zoo and then you do confidence intervals without worrying about that, for ranking, it's fine. It's not bad at all, which is the green curve, I think. And then the blue curve is actually post-selection, which is a very refined mathematical kind of correction. So the metric matters, and then this so-called, so the heuristic, what's happening is that usually the post-selection correction is try to adjust for the conditional on the selection. If that property is kind of constant, if you rank them, things don't matter. And in my work, a lot of time, it's really the ranking, not the FDR. That's the concern. Okay, so going back there, saying that we already have this, people already doing perturbation interval, I will call under the PCS influence because of the 9 climate groups. So for the second part of talk, we'll share this this project, which has been one of the motivating projects for the PCS framework. This has been going for almost 80 years. Now we have one archive paper, and the other paper hasn't been put up yet. But even though the publication we're still doing more work on this, but has been very instrumental for the PCS framework. So this is a work with the lab, my collaborator for 15 years, Jack Gallant, and led by my 2 former students, one now at UCSS faculty, 1 year and joining Duke, and Adam is now in Google, Mike and Ben Wilmore were Jack's lab, and Ben, who was a postdoc, actually the data was collected 15 years ago, took Ben 2 years. Ben is now at Oxford. So what we're facing, this is started working with Jack on this problem almost 10 years ago. We try to understand this V4, which is on the word pathway for visual cortex. V1 is the edge detector orientation frequency, and V2 is kind of similar to V1. And V4 is before IT, which is object recognition. It turns out to be a very difficult and elusive area to study. On the other hand, for the last 10 years, deep learning really took off, especially convolutional network. And if you look at physiology, this very famous work by 2 Nobel Prize winners posted there, that they figured out how V1 works, that the V1 neuron care about location and also orientation and also frequency. And what you'll hear is the neural firing. And the data you see on the video will be the stimuli on the screen. This sleepy cat with eyelids popped open was looking at. And so what you hear is the firing. They're looking for the location where the neuron cares. And then they found it. So induce a firing, causality, intervention, proven that this neuron cares about this location, right? So there are other things I won't have time to show. So this is, people figured out V1. And if you and I or everybody here has the same data, we probably would have figured it out too, right? You just do it, something, so this neuron cares about this location. So the data was synthetic, it's a dot shining on the screen. But for V4, people realize they care about complex shapes. So people have designed very elaborate geometric shapes, try to probe V4 neurons. These very delicate, artistic looking shapes. And to say, does V4 neuron fires? First, it's very labor intensive. Second, it's we might miss a lot of signals of V4 neuron cares that we didn't design because we didn't know how to design it. So there's problematic. And people also went with the very laborious design of different shapes of curvature and said, yeah, V4 neuron cares. So people learned use this synthetic stimuli, care about texture and curvature, but the shapes are very geometric. So Jack's lab, when I started working with them 15 years ago, they were actually the time pioneers to use natural stimuli. Now it's very accepted because I want to lab, everybody use natural stimuli. But at the time, it was still a lot of synthetic stimuli. So Ben collected 71 V4 neurons. They have fixation, all of that, and from 2 behaving macaques. And we didn't see a difference, so merge them together. And with the old black and white image database called Coral, and random selected. and to feed and to observe the average firing rate. So I started working on this almost 10 years ago. We started drafting the first paper. You can see 2013 with two of my best people. Julian Merrill was my postdoc, now leading the computer vision group at INRA in Grenoble, and Yuval Benjamini back to University of Hebrew University in Israel. So two of my best people, one applied statistician, one computer scientist, to work on this problem. And we built our own neural network, use sparse coding and also sift features from computer vision. And we got the state-of-the-art performance. So let me define what's the state-of-the-art performance. So state-of performance means we have predictive correlation performance. That's the metric used in physiology, because it's very hard to predict the magnitude of firing rate, but you can predict the up and downs. That's correlation is the prediction accuracy measure. And we compare what we got from V4 to V2. V2 is an easier predictive region for prediction. So we match that. So that's what I mean by state-of-the-art. We get the same performance as some earlier visual cortex. And Jim DeCarlos at MNT was on parallel paths. They were interested in IT. They're putting objects on top of the natural stimuli, and then they were building predictive models. And then they published a paper. We try to go for understanding. And I'll come back to some of the more recent ones. So we end up pursuing of something we call deep tune. So the question we ask ourselves, how do we characterize if our neuron in the spirit of physiology experiment I showed you, can we find stimuli that excite a particular neuron? That's what we call characterizing a neuron. And then what can we say about this new convolutional network? Do they really resemble brain function? So in a nutshell, we developed a deep tune pipeline, which can be used for other scientists too, to understand neurons, that we get state-of-the-art performance. So I have two of my best people work for 2 years, get this predictive performance. And we use deep learning as a feature extraction. Other people feed AlexNet and ImageNet. And then we use linear model, lasso, and beat our own earlier models. So that's why I jumped into deep learning 5 years ago. And then we had the problem. We end up having 18 different models give very similar prediction performance. How do we interpret? So that's what we feel. We was pretty slow for a couple of years, just like struggling with these 18 different models. So this is, I would say, in the broader sense, transfer learning. We take AlexNet, feed color images of ImageNet, 1.2 million images, 1,000 categories. And we take the first two layers as feature extraction, fix the weights, we didn't fit it, and just use it as extraction. So the idea is that if these first two layers capture early visual cortex processing of primates, then we can use it to process for us before we connect with higher visual cortex. Why I say it's transfer learning, because we have black and white images, an image never saw, we just make 3 channels the same, we didn't do anything different. And then this is human data, ImageNet, and we use this macaque data. And then we connect with neural activity, very low level, and not the task-driven like cats and dogs. So it worked really well. And this is performed, you can see not just the second layer, third and fourth all work pretty well. This is average performance across 75 neurons. And the Gabor-like, the first layer of deep learning doesn't work. You see a drop of performance in terms of predict accuracy, in terms of correlation. So this is the AlexNet with, I think, with lasso. So if you have now this model, fits pretty well. If you follow the same physiology, use the model as a surrogate for a real neuron, you will try to see what are the images that maximize this model neuron. And this is inspired by the deep dream work in deep learning, we call deep tune. So we maximize the fitted neuron model instead of the task-driven. And then we get this curve out. And then we altered another work. We remove a lot of the nodes, like to 70%, you still see this curvature. So this conjecture, this neuron cares about curvature or curves and this particular direction. And we went back to original data, black and white data set, and see what are the neurons within this set of images that was used for experiment that the model neuron gets excited. And that's the mass that tells you where the model really cares about, drive the prediction. You see curvature or curves again. But you said this is an artifact of a model. That's completely fair. Now we went back to original test data. So for Jack's lab, they have replicates, 10 replicates for test data. And this is just the averaging. We didn't fit any model, and you look at all the images that excite this firing rate, average firing rate, you see curves again. So this is a validation thing that what we suggested with the deep tune image has reality, because there's no model. This is just average replicate images, maximize the observed images, observed responses. So we have Alex Nice with Lasso. And then we also have, at the time, we didn't try some of the newer networks, GoogleNet, VGG, and you can have layer 2, layer 3, layer 4, and you have Lasso and Ridge. So this is 3. They give very similar performance. All the color curves are different versions of the very different number of parameters, kind of different architecture. But the first few layers all act pretty well as surrogates of early visual cortex processing. So we end up with 18 models, right? We also have Lasso and Ridge. We have 3 models, 3 layers, 9 times 2, we have 18. And they give the correlation between the prediction 0.92. So we were stuck for a while. So for a while, I was going around showing, I already showed this to you. So going back to the stability principle. So first I was going around giving talks, have these 18 different deep tune images. The initialization doesn't really change very much. So the same model, you start with different random initialization, get something very similar. So that's not a problem. But the 18 different models do give you different looking images. This is suggestive of what this neuron care about. But there's a commonality for most of them, is this curved, this shape. So the details like GoogleNet, you see that deep dream images too, these eye-like things are artifact. And the spacing actually is also artifact of the models. But the shape is not, and it's common. So for a while, I was just showing you 18 different images. And then some audience, when I gave a talk, I think it was a Banff workshop a while back, people really pushed and said, oh, it would be nice to have one image. So we called on stability principle. First, I suggested that let's just average and just you don't get it where. So we have to really build stability in the algorithm. So when you maximize the different 18 different, we actually do a little regularization. Surfaces, you have 18 different gradients. So in the end, we seek the lowest gradient for the 18 gradients. And then that's how we build in stability. We call consensus deep tune. And this is from neuron 1. This is 10 different initializations. You basically get the same thing, very close to the same thing. So this way, we have now a representation for each neuron. It's called consensus deep tune image. Now we have a good representation for each neuron. We can actually group them. And you can see that just shows a much richer diversity of what these visual neurons might care about, right? On the right is this contour-like, curve-like contours, and a lot richer. Remember the geometric design and the complex patterns, people haven't really designed like that, and you have more like texture. But this clustering, the cluster, actually they don't separate very well. This is really artifact because we do hierarchical clustering, we cut it. Actually, that's what we're adding to the paper, is that we really cannot say they fit into 1 or 2 modes. Some of them actually care about both texture and the curves. And this is a new thing, people haven't put them together. So all of it come naturally from this analysis with natural stimuli. Even I put into 4 categories, they don't really fit naturally. They are really pretty much spread out. It's really the diversity of the 17 neurons show us. And the outlier is really like a V4 neuron, but with a bigger receptive field. It's really an edge detector. So DiCarlo's group, they have physiology, and Jack put up a physiology, so we couldn't put it back. This really become our scientific recommendations. These images can be fed back into the closed loop experiments, and then to induce this firing, which you saw in the video I showed you. You heard it when the location is found, the right location is found, you hear the firing. So these images can be fed back into closed loop experiments and really prove. And DiCarlo's lab actually did that with their own versions of a pipeline, but the regularity actually is artificial. So we don't want to use the whole thing. We want to crop it into a more small bits and do randomization. And as basically modern experimental design to help people to zoom in to figure out what neuron does. The challenge is really actually when you have population neurons simultaneously measured, 75 neurons not simultaneously measured, you need to find like idea about how do you understand with this, maybe it's a movie or something will really excite a population of neurons. So the proof of concept is already done in DeCarlo's work, lab work from last year. We visited them and they were on very similar path. So to summarize, the PCS framework is really a best practice framework, conceptual framework. There's a lot of detail you still have to work out towards trustworthy data science or trustworthy AI, or reliable, responsible, transparent. We can have many descriptives. And documentation is a huge part of this framework. There's no magic. It's just you just have documented, help you think, help people to evaluate. So we have a whole community of people together. We can do more reliable data science work. And I showed you the case study. And we have also very good process, use something called iterative random forest for genomics. We were part of the BioHub trying to figure out about what are the genetic drivers, heart diseases. And I hope you'll find the PCS framework or parts of it useful for your project. And I cannot emphasize enough the importance of domain knowledge, right? For us to work with Jack's lab, and also for the genomic project work with the software lab is very, very crucial. So for the genomic project, we felt a decision tree matches thresholding behavior at the molecular level. So that's a better match. And for genomics problems, for a neuroscience problem, cognitive, our processing pipeline really match with the hierarchical processing of neural network level. So to come back to the question about does convolutional network capture something on brain function, I do feel like the early layers to capture a pretty good surrogates of visual cortex. That's why it works very well also for medical imaging. People usually start from the ImageNet architecture and do some fine tuning to do tumor detection. It's because I think the early visual cortex pretty well captured. I mean, since we went to the single neuron level, right? I was blown away at how well it worked compared, because we have a benchmark with two of my best people work for 2 years. Of course, we had less data. This is indirectly, we had access to the ImageNet data through the feature extraction black box from AlexNet or other versions of DeepNets. So to finish, who can make the vertical happen? Other people. So my group will actually try to solve problems, and then you need algorithms, critical thinking, communication, and relevant theory. We're actually coming back to deep learning to do theory, deep learning, and also random forest. We have some really nice results to show that you can extract interaction information from random forest, the tree ensemble, and under a particular discrete Boolean type of model, we recover the interactions. Under independent feature assumption as a first cut. So iterative random forest really can work as a nonlinear model selection. And the papers are at my website. If you go to Google me, you will see a lot of my vision papers are at the first page. And then the deep tune, we still try to do more work, still on archive. And last but not last, this guiding principle PCS will be the guiding principle of the textbook. We have a contract with MIT Press, with my former student, current postdoc, Rebecca Butter. We hope to finish early next year. We'll have a free online copy for everyone, and MIT will have a print copy, probably take another 9 months to finish. Yeah, the last plug is that Berkeley, we're really doing great with data science. We have new provost, Jennifer Chase, our classes, data 8, and now also data 100. I was on the team to teach data 100. Now there's also data actually 102. And we also have a vision report about the organization change. So we're having a new division called CDSS, Computing, Data Science, and Society. And statistics department is in the process of moving into that division. ECS, I think we'll have a quantum state with college engineer and the new division, I think, but I don't know how far they have gone for that. and other units are moving into the new division. Thank you.
Thank you. Actually, we have time for one quick question. I have a question about those the fitting the neural network for the neurons. So the fit is for the data from all the neurons simultaneously, or just one neuron?
Just one neuron. The neurons will not measure simultaneously. So if they are stable, we should be doing some simultaneous, but for this data, it's just one at a time.
I see.
Because they were not measured simultaneously.
Okay.
Yeah.
Thank you. Because of time, I guess we can directly move to the second speakers. And if you have any questions for Professor Yu, please leave your question in the chat box.
Oh, you can email me, being@berkeley.edu. Thank you.
Thank you. Wonderful talk. So our second speaker is Professor Alfred Hero from the University of Michigan. Professor Hero is a John Holland Distinguished University Professor of Electrical Engineering and Computer Science, and also the Jamison and Betty Williams Professor of Engineering at the University of Michigan. Professor Hero is also a fellow of the IEEE and also the Society for Industrial and Applied Mathematics. His research interest includes data science and developing theory and algorithms for data collection, analysis, and visualization. So today he's going to present his work on high-dimensional imaging data analysis. So let's welcome him.
Thank you very much. First of all, does everyone see my screen? Do you see my screen? Great.
Yes.
Thank you. And thank you to the organizers for inviting me to this very inspiring meeting, a meeting of many different disciplines, all involved in statistical issues that underpin imaging problems, which have very high complexity and tend to lie in high dimensions. And I'm going to talk today about a particular type of imaging problem that lies in ultra high dimension, where you have multiple domains, multi-way tensor valued imaging. And so we're going to take the point of view of sparse covariance modeling, basically in the matrix normal type of sparse modeling framework. And I'll show you some of the types of methods that are both scalable, statistically principled, and interpretable in terms of physics models that underlie the process that the imaging is imaging. And so, of course, that's applicable when you're imaging natural types of phenomena. And one of the phenomena that we're going to be concerned with here, in fact, the principal focus of my talk is going to be solar space weather imaging. So the principal references for those who want to follow up on some of the things I'm talking about are listed here. And my research has been supported by various agencies. These are my current supporter agencies, and the NASA NSF Solar Storms and Terrestrial Impact Center is going to provide the data that I'll demonstrate the methods that I'll be talking about. Just as motivation in terms of this solar imaging problem, space weather problem, it's been known for many years that space weather has a significant terrestrial impact, and this impact has been realized, appreciated since at least the 19th century. The largest solar storm on record occurred in 1859, which created dangerously powerful electromagnetic pulse events, EMPs, that short-circuited telegraph wires and so forth. And then as recently as 2015, we had a major a space weather event caused by a solar flare, a mass ejection event that resulted in electric power blackouts and rerouting of commercial flights and a closure of airspace in Europe, parts of Europe. So space weather, this is imaging in the sun for predicting weather on the sun is analogous to predicting weather on the Earth, and the consequences of correctly predicting the occurrence of a flare with adequate warning, which 24 hours is enough to be able to close down electrical systems, open circuits so that you don't have catastrophic currents that are induced, and turn satellites so that they're facing away from the sun, their solar panels are facing away from the sun. And so imaging for this problem that I'm going to be speaking of in particular involves basic satellite imaging of satellites that are circulating the sun in the Solar Dynamics Observatory, data we've with our collaborators have been working with. So this just shows another snapshot of space weather's importance in the FEMA 2019 National Threat and Hazard Identification Risk Assessment Report cites space weather among the top 5 threats, and in fact, the third most threat, really the second most threat after pandemics. So we all know that the pandemic threat hit a few months after that report was issued back in July of 2019. So space weather is not far behind. So hopefully we won't be caught with similar lack of preparation.
Yeah, I was going to say not. I was going to say not this year.
Excuse me.
I was going to say not this year.
Yes. So predicting and identifying these solar coronal mass ejections is a really important problem, as you should appreciate by this point. These coronal mass ejections occur in various intensities. Flares occur with various intensities. B class, C class, M class, X class for extreme events. And data that's collected for imaging and predicting whether these events occur is basically a tensor valued multi-array. So you have a data that evolves over time, wavelength, many different wavelengths are collected from the SDO satellites. And just showing a video here of sort of the challenge that we're facing. This corresponds to the several active regions, which some of which produce flares, others are quiet, occurring over a period of about 2 months. And extreme flares, there's maybe a dozen per year. Class C or B flares occur every day, but we have to segment these active regions away out of the disk of the sun, and then evaluate to develop a statistical predictor for generating an accurate prediction of whether an active region will, in 24 hours or less, produce a flare. So that's sort of to motivate things, and I'm going to jump into the modeling paradigm that we're on, that I'm very excited about. We've tried deep learning and we've tried other types of methods, and the main issue with deep learning methods is lack of interpretability and lack of an ability, at least my ability, to convince the physicists, the solar physicists, that the predictions are meaningful, that they're really learning something from the structure of these deep networks with hundreds of thousands or millions of parameters. So what we're going to focus on are multi-way data representations that can be based directly in the physics of these phenomena of active region flare production. So we have, in a very general sense, to learn a low-dimensional representation of multimodal data, low-dimensional in the sense that we are going to want to describe this very high dimensional data cube with a few parameters, with either a statistical model or not. And common traits of the data cube, as it's a k-way tensor, dimension d with mode dimensions di, respectively, is that the indices index over different types of modes, such as in the solar dynamic observatory, with different spectral bands, and some mode dimensions may be much higher than others. So it's a very unbalanced a tensor, if you like. And data cube may be sparse in some modes and not so sparse in others. And it may have a sparse low dimensional approximation. So first order representations of tensors of this type basically boil down to learning the mean, right? So you have a number of active regions that you've collected in a database, and then you want to find over, say, the M class and the X class and the C class respectively, what's the behavior of the mean over time, right, of these active regions that produce those class of flares. And one can then apply different types of direct product or Kronecker product or sum product types of representation. Second order representations go one level higher to try and learn the covariance or the spatial dependencies, spatial temporal dependencies, and spatial temporal channel dependencies within the data set, as opposed to simply trying to describe the mean. And so, of course, we all know as statistically oriented individuals that second order representations are necessary for building a predictor. Dependency describes the structure that relates the forecast to the present data used for forecasting. So multi-way data structure in terms of the covariance implies a pattern covariance, which is very useful, turns out, for developing different types of low dimensional approximations. And I'll be introducing something called Kronecker product PCA in a minute, which is based on this concept. So if you take a set of these time snapshots for a single active region, and we have hundreds or thousands of these, and you form a vector which vectorizes over the two space dimensions and over time into a vector that then has a covariance matrix that is patterned in the sense that each block, d2 by d2, if d2 is space, that is width times height, each block is a spatial covariance lagged by a time lag I minus j, right? And so a simple model for this pattern matrix is this model, the Kronecker product model, which says that spatial covariance that lies in blocks of d2 by d2 is constant over all those blocks, except for a time correlation scalar, A12 in this case, in the 1-2 position, the lag of order 1 from time instant 1, that scales the spatial covariance. Very simple and maybe arguably overly simple model. This is described in terms of a matrix representation as the Kronecker product A Kronecker B, where A is the set of A is the matrix consisting of the AIJs, D1 by D1 matrix, and B is a D2 by D2 matrix, leading to a D1 D2 times D by D1 times D2 covariance. So this might, as I say, seem overly simplistic, and in many cases it is. And so one can ask, does this relate in any way to any kind of physical ground truth? And it turns out that this is actually a quite general representation that applies to many types of random processes over time and space, and perhaps also wavelength, whose evolution is governed by a PDE, a partial differential equation of elliptical, hyperbolic, or other type, where you can isolate on one side the influence of derivative of t with respect to t of this random process u, or this random field. And on the other side, you have the spatial coordinates that in this case we have a second order operator with a random disturbance. So this type of PDE, there's a differential operator equivalent equation because of the locality of second order derivatives. We have sparsity in these differential operators that are shown here as Kronecker products. And if you discretize this random field, you end up with a Kronecker product time-space matrix equation that it emulates in discrete time this continuous time and space equation. So a discrete domain consists of a Kronecker product of two differential operator matrices, d of t differentiates in time, and d of z, which differentiates in space x, y. And that can be described equivalently in terms of a matrix of time and space in the rows and columns respectively, with a left and right multiplication of these differential operators equal to a white noise matrix, a driving matrix W. So if you consider the variance or covariance matrix associated with this process, which is discretized, it's very easy to see that the covariance of both sides of these equations, of course, are equal. And so as are these equations. And so you can then come up with this very simple relationship. Inverse covariance matrix is equal to, up to a scale factor, the Kronecker product of these two differential operators. So Kronecker products play a role in describing these different diffusion equations. And one particular diffusion equation is the so-called dissipative magnetic induction equation that is widely used in modeling coronal mass ejections and solar active region wavefronts, magnetoelectromagnetic wavefronts. Okay, so this is just showing how you can generate these sort of synthetic flares using these a simulation model with these Kronecker products. One can also generalize these Kronecker products through the so-called Kronecker product expansion. And this type of expansion is analogous to the PCA expansion, except that it's based on Kronecker products. And we have a separation rank, just like you have an algebraic rank for a PCA representation, equal to the number of Kronecker product components that form this sum. And these Kronecker product matrices are normalized so that they have Frobenius norm equal to 1. And the sigma I can be looked at as coefficients, just the same way that the eigenvalues of the PCA representation leads to a set of coefficients lambda I. So the advantage of KPCA, this Kronecker PCA versus PCA, is obvious when you look at one of these Kronecker product representations, for example, of this diffusive process that I showed before, the magnetic induction process. And so you basically have perfect representation of the entire covariance matrix with a single component in the KPCA spectrum, whereas the PCA spectrum, you have only 2% representation in that component. So a much higher compression ability of the KPCA for these types of spatiotemporal processes that have Kronecker product representations. If you look at the sample variance, as is usual, you have a skirt of noise spectral values that is due to the fact that finite sample variations in the sample covariance, but you still have more than 80% concentration in the first component of the KPCA, but only 1% in the PCA first component. And so you could apply this to this dissipative magnetic induction process, and you can see that we're a true covariance that looks like this, that the PCA does a really poor job with rank 1 PCA, whereas the rank 1 KPCA is basically denoising the sample covariance and giving something back that's much closer to the true covariance. Okay, and then it just shows the components that allows you to look at things like the Toeplitz tridiagonal nature of the time inverse covariance, which corresponds to that differential operator over time, which is Toeplitz, and the pentadiagonal nature of the spatial differential operator comes out directly too. And then you can look at histograms, bivariate histograms leading to conclusion. You have a much better reconstruction by looking at the histogram of a KPCA reconstruction, rank 1 versus sample covariance than for the PCA, for a single component. Okay, so, but it's inverse covariance is what really is sparse in these problems, as opposed to the covariance itself, because the PDEs are implicit, right? They're implicit equations where the sparsity comes from the discrete locality, the sort of local message passing component that exists in the PDE, which is being applied to the random field U. So it's the inverse covariance that's much more natural to model as opposed to the covariance itself, and that's what leads to, of course, modeling or estimating directly the inverse covariance instead of the covariance itself. And so penalized maximum likelihood estimators are a method of considerable acclaim, and many statisticians have introduced sparse estimates using penalized maximum likelihood estimators. In this case, it's in the matrix Gaussian matrix normal framework. And I'll be very briefly discussing in a couple of minutes that I have left the Sylvester G lasso and the Terra lasso, tensor G lasso. And so in a nutshell, what differentiates these methods is the penalty, the form of the penalty is manipulated in the KG lasso, the Kronecker lasso, so that the model omega has this Kronecker product form. The Terra lasso, we have a Kronecker sum form, and the Sig lasso, we have a Kronecker sum squared form for the inverse covariance. That's in a nutshell the differences between these three. And I'm not going to emphasize this, but this sort of shows the difference between the Kronecker representation of, here we have a covariance, which is the Kronecker product of these graphical models where the edges exist between two covariates. If the corresponding entry of the covariance factor is non-zero, so you basically multiply these three matrices that correspond to these graphs together to get this Kronecker product. And the total number of edges is much larger than in the case where you use a Kronecker sum, simply because there is no multiplicative effect on edges. Here, each edge is multiplying another one and propagating it or magnifying it into the overall matrix. So it's a more parsimonious representation. Terra lasso, which is a method that uses a penalized maximum likelihood with with an iterative soft thresholding a type of algorithm, optimization algorithm, can by virtue of the sparsity of the Kronecker sum be able to estimate with considerable accuracy covariance matrices, inverse covariance matrices with on the order of 1 billion elements. That's just all this shows here. The Sylvester G lasso is a different approach, recent approach that we've developed, which adopts a generative interpretable model for the inverse covariance. So the Kronecker product is interpretable, generative interpretable, in the sense that you can generate processes simply that obey this covariance model, Kronecker covariance model, simply with a simple equation that involves the Kronecker product of the Koleski factors of A and B. The model that corresponds to this Kronecker sum is not a generative interpretable model, whereas the Sig lasso that I'm going to propose here is, and it's called the Sylvester G lasso because if Z is our discretized differential equation generated random field, then it satisfies, instead of AZB equals W, which if you recall was the Kronecker product representation, Z solves this Sylvester equation of AZ plus ZB equals W, a white noise component. And so this exploits this Cartesian structure of differential operators. For example, the Laplacian operator, which is described by a direct a Kronecker sum between the two second order derivatives in the X and Y direction. And so that naturally leads to this Sylvester structure in the differential operator actions. And so you can look at this sig lasso as lying somewhere between a Kronecker product representation of the inverse covariance and a Kronecker sum representation, because of simply the square of the Kronecker sum of A and B is a Kronecker sum of A squared B squared plus a Kronecker product. So it's kind of a compromise between the two. I'm not going to discuss this. This just shows that the recovery under model mismatch is stable under the sig lasso model, even if the true model is a Kronecker sum or a Kronecker product instead of being a Kronecker sum squared or the inverse being a Kronecker product directly. So I'm going to finish with this application to solar active region data, which I started with. So we have videos of active regions over a 13-hour time period, 1 hour cadence, that is 1 hour sampling period. For B class and MX class flares, we're going to group these into two categories. And the observations are, again, multi-way arrays. We have 7 channels. We have 100 by 50 segmented active region bounding boxes on the surface of the sun, as I was showing with that rotating solar image before. And then we have, as I say, 13 time points. And so we're going to try to accurately estimate the inverse covariance matrix that is associated with this process under this 4-way Sylvester model, which in a special case would be a multi-channel magnetic induction equation type of model, where these are differential operators that we're going to estimate without any kind of differential operator constraint, using a sig lasso proximal alternating linearized minimization algorithm, SG-Palm. And model validation is a standard thing. You split the data set into the train and test set of videos. You train a one-step linear predictor, or we're going to use a QDA predictor under the matrix normal assumption to classify the B versus MX flares. And the goal is always to predict the 13th frame from the first 12 frames. So that just shows what we're doing. HMI channel up here, the AI channel, one of them down here. This is what we want to predict, and using the 12 previous frames. And so this shows simply that the normalized RMSE improves with the sig lasso model relative to other types of models, like the Terra lasso, the tensor lasso, another model I haven't talked about. There are some examples, some actual predicted examples. This is a very simple pixel by pixel lasso approach used to predict each pixel individually. You can see that doesn't work very well, as might be expected, because there's no spatial covariance component whatsoever. It's all temporal. We can also do things which interest the solar physicists we're working with, and that is looking at the value of using particular channels. So HMI, which is a helioseismic magnetic induction channel, does that add to the AIA channels? And you can see that it does. It basically improves performance by a factor of 20 for a B-class flare prediction of that 13th frame, and about greater than about 9, factor of 9 for the MX class. And then finally, we show here that if you use the estimated inverse covariance in a QDA, right, in a quadratic discriminant analysis classifier, which is just a likelihood ratio test, with the inverse covariance under H0 and H1 replaced by the corresponding MX and B flare estimated inverse covariances, using SIG lasso, we obtain significantly better classification error than relative to these other methods. And we argue, or I would argue, that this is due to likely due to the fact that we just have a better fit with this SIG lasso model, this generative model, to the actual underlying physics that generate this data. I'm not going to describe EEG data. I'm just going to go right to the conclusion. We applied this to several different types of multi-channel data. But the main takeaway here is that we really propose that people be much better aligned with the mathematical physics in designing their models, whether those be deep learning models or relatively simple models like sparse covariance estimates. And the rest of these points I've already made, so I won't take up your time due to lack of time. So thank you for your attention.
Thank you. It's very interesting to see this relationship between this canonical representation of tensor data with physical diffusion process. So I'm just wondering whether this connections is this strong connections is because of the diffusion process. So can this be generalized to any other physical processes?
Yeah, very, very good question. The SIG lasso representation is restricted to processes where you have this type of what's called Cartesian structure, right? So if you have a PDE where you have, for example, a diffusion where there are time-dependent components, derivatives on both sides of the equations, like you have a joint derivative between t and x, right?
Mm-hmm.
Then it won't work. And then that won't work. But most physical processes do not have that property, and so it's we believe that it's very highly applicable to cases, well, at least when the physical process has a Bayesian, an elliptical, or hyperbolic type of PDE.
Okay.
Thank
you very much. Yeah, wonderful work. Yeah. Okay, because of time, we need to move to the third talk of this session. We can open the floor at the end of the session. So our third speaker is Professor Bertrand Tivran, who is a leader of the Pareto team in INRAEL Research Institute in France. His research interests include machine learning, brain functional imaging, and statistics and artificial intelligence. So today he's going to talk about the high-dimensional statistical inference with application to brain imaging. So let's welcome Professor Tivran.
Thanks a lot for the invitation. Can you hear me well?
Yes, very well.
Great. So let's get started. So let's get to statistics. So I will start with an application which is reminiscent of the talk of Binu that included some analysis of brain data. So here we want to study cognition, cognitive neuroscience, that is how our cognitive activities are affected or controlled by neural circuits in the brain. And today in humans, we tend to use functional brain imaging to address these questions. So the way science, cognitive neuroscience proceed is by probing some cognitive theories, by organizing a set of stimuli into an experimental paradigm, an experimental protocol. And then you take the fresh brain of a 20-year student and you put him or her in the scanner during 1 hour. You get images of the brain that represent brain activity while you presented the stimuli. And then you have to analyze the data, which means to find the correspondence between the stimuli you presented and the brain activity. So at the time of analysis, we can consider an encoding schemes in which you will try to predict the brain data based on the stimuli. I think that what Binu presented was a kind of encoding analysis. But you can also do decoding analysis, which is given brain data, predict which kind of stimulus was presented. Now, if we start formalizing the problem, you call X your brain data, so a set of brain scans associated with the label Y, which represents the condition, the stimulus that was used in the experiment. And so you want to infer which brain regions, which part of X is useful to predict Y. And this is a difficult problem because the brain images are big objects. So these are 3D images, so pretty large. You've got typically now hundreds of thousands of voxels in these images. And actually, resolution increases steadily thanks to technological improvements. And currently, we in our typical acquisitions, we have maybe 400, 500,000 voxels in a volume, but we are going towards millions and tens of millions because resolution keeps improving. The point is that in the same time, the amount of data that you acquire remains limited because it's related to the number of subjects that you can scan or the length of your experiments. So N is limited, but P increases. So performing inference in a setting where the number of samples remains limited while the dimension increases is, of course, more and more difficult. Still, we can play this game, and here I'm showing you an example that we ran a couple of years ago, in which we could reliably find brain territories that are predictive of the occurrence of a certain cognitive content, so either a visual stimulus or auditory stimulus or a motor task or different types of tasks. I'm not going into details here. I guess it's not your field. But the idea that this was made possible thanks to good inference schemes. And so based on public data, more and more public data now, we can build functional brain atlases that show which brain territories are important for different cognitive activities. And we could also do the same, like to predict diseases, of course. Okay, now let's get back to statistics. So brain activity decoding is a predictive problem with small n, large p. The SNR of the data is pretty low. There is no translation equivalence in the data like we have in most computer vision tasks. And this explains why, for instance, using a convolutional network, a convolutional architecture is not useful in this kind of field. And it has been observed repeatedly that nonlinearities in the classification model would not help. So simple linear models are still state of the art to classify these data. And so this is why I will focus tonight on this evening, because it's I'm in France, so it's the evening here. I will focus now on linear models and doing inference on linear models. Okay, inference on linear models, you all know how to do that, at least when the number of samples is large. So you can do ordinary least squares, which means obtaining an estimation of your vector of coefficients W. You can estimate the covariance matrix with the standard ordinary least square equations that come from Gauss, and then, for instance, compute a t-statistic that will give you the significance of the different coefficients. And this works as long as X is well conditioned, because otherwise estimating W is hard and the covariance becomes degenerate, it becomes infinite. And we also have the issue, the known issue, that we have a multiple testing problem with non-independent statistics. But things completely break when P becomes as large as or even larger than N. So here, just take N equal 100, P equal 95, even using a nice IID Gaussian design, you know, the simplest possible model, then you can no longer recover the correct estimate. So the ground truth is the red value, your estimate is the blue value. But the confidence intervals are crazy because your covariance matrix is close to singular, and so you have a huge variance. So your estimator becomes useless. So you all know that in that case, we should regularize the estimator to obtain a good estimate. But can we still do statistical inference in that case? Which means finding for which features the weight Wj is non-zero. And there are solutions for that. So recently in the literature, the knockoffs filter has been proposed by Barber and Candes and many other colleagues. Or the desparsified lasso is another solution proposed by several groups, Zhang and Zhang, Montanari, and others. There are other solutions that I'm not going to discuss tonight, like the multi-split or corrected ridge models. So I'm going to focus on two cases. The first case is when P is as large as N, or maybe slightly larger, but not much larger. And I will discuss the knockoff solution. I will propose some improvement upon it by using an aggregation technique. And then I will get to the P much larger than N setting. And I will show that then you need to have a more aggressive dimension reduction of your problem to be able to perform inference. And I will present some solutions for that. So let's start with a discussion of the knockoff filter. So the idea was introduced 5 years ago by Barber and Candes. And the approach consists in creating a noisy copy of your initial design matrix. So let's call X the design matrix. And you create a novel a noisy copy of the design matrix. What is important is that essentially you have a correspondence between the columns of these matrices, and essentially swapping columns from X with the corresponding columns from X tilde does not make any difference in terms of distribution. So you are sampling the same distribution whenever you swap the columns of the design matrices. So this is what you need to do. And you need to sample the X tilde independent from Y given X. So essentially, X tilde is just a function of X. It's a noisy copy of X, but it's generated independent from Y. And if you do that, so first of all, to generate the knockoffs, there are many different ways. You can use some deep learning solution, variational autoencoders, etc. But there is a simple solution, assuming a Gaussian distribution. You can sample X tilde from a given Gaussian, and there are some explicit terms for that. So it may be slightly expensive, but it's pretty simple overall. I'm going to use this kind of Gaussian knockoffs tonight. Then once you have created the knockoff matrix, you can concatenate the original matrix X and the knockoff one X tilde into a larger matrix, and then run some logistic regression or linear regression with this larger design matrix. And of course, with a regularizing penalty. So typically an L1 penalty because it has better recovery properties than an L2 penalty. And then the important thing that you will compute is the so-called lasso coefficient difference, which is the difference between the coefficient J corresponding to the first design matrix, the J's column of the first design matrix X, and you compare it with the coefficients of the J's coefficient of the second design matrix. So the beta hat J plus P, because it corresponds to the second design matrix. So you take the difference of the absolute values of these coefficients, and this WJs gives you an information of how much more important the primal variable is with respect to its noisy copy. So intuitively, you expect that what I call here the WJ statistic, the lasso coefficient difference, will be large whenever the variable is a truly predictive variable. Well, it can be positive or negative, you don't know, whenever J is not a truly predictive variable. What you will observe in practice, so is some distribution, empirical distribution of the WJs given your data. And what you will typically want to do is to threshold this distribution to only keep the WJ that are larger than T, than the threshold T. The point is that you would like to control the rate of false positives. And so the rate of false positives would be given by the null distribution of Wj for your model. So if you knew this distribution, you would be able to measure the proportion of false positives that you will sample by thresholding at the value of t. And then, for instance, you could control the ratio of false discoveries among all discoveries, which will be the false discovery proportion. And that is a quantity that people typically want to control when they do statistical inference. Problem that you don't know the null distribution, but what you, given the hypothesis we injected into the model, we know that the distribution of this lasso coefficient difference should be symmetric, about 0, because when a feature is non-predictive, Wj could be positive as well as negative. So it's a symmetric distribution. And so we can actually estimate the rate of false positives by looking at the left tail of the distribution, which provides you an estimate of the number of false detections that you have for a threshold t. So given that, you can compute an empirical false discovery proportion for any choice of a threshold t. And the nice contribution of Barber and Candes has been to show that controlling this empirical false discovery proportion actually controls the expected value, which is the false discovery rate. And this is why the knockoff have this nice, very nice property. Well, this is great, and actually we could check empirically just by simulating data. You simulate the design matrix, the coefficients, and then y, and then you look whether with the knockoff inference you can actually find the correct support. And what you see here, it's with about 100 draws of such an experiment. You'll see that the false discovery proportion, the real one that because you have the ground truth, will vary a lot. So its mean value, which should be close to the false discovery rate, is indeed 5% as required by the model. So we indeed control in average the false discovery rate, but the false discovery proportions varies quite hugely. It can be as high as 0.2, 0.25. And it can be 0 also in many experiments. And then on these same experiments, you see that the power can be pretty decent with values as close as about 0.7, 0.8. But in about 30% of the cases, we did not detect anything. So there was no threshold t for which we could control the nominal FDP at the desired level. What I mean here is that the knockoff filter, it's a random inference technique because it depends on the draw of random x tilde. And so sometimes you will be lucky, sometimes you won't be, and it's pretty bad. You want a more reliable technique for inference. And so what we proposed was to fix that. And to fix that, we took a slightly different approach, still inspired by the knockoff approach by Candes and colleagues. We just consider that indeed comparing a certain value of Wj to the values observed in the left tail of the distribution is a kind of p-value measure. It gives you how likely it is that you would have observed such a value under the null hypothesis. So exactly the definition of a p-value. And we can formalize this property. For a given Wj, we can define a corresponding p-value. And then what you are going to do is to repeat this experiment a certain number of times. You will draw some bootstraps and repeat again and again and obtain different p-values for each lasso coefficient difference that you obtained based on your experiments. So now for each feature j, you have a set of p-values, say maybe 25 such p-values. And then what you can do next is to aggregate these p-values to obtain a representative one. And you can do that such that the rate of errors is controlled. Here we use a quantile aggregation of Meinshausen and Bullmann, which is just taking the gamma quantile of the p-value distribution you obtain and correcting by a factor 1 over gamma. Then, based on that, you can, for instance, control the false discovery rate of the procedure by using a classical Benjamini and Hochberg statistical test. When you only have one bootstrap, this is exactly equivalent to the initial knockoff procedure. So it's actually generalization of the knockoff procedure. So we call it aggregated knockoffs. And the nice feature of the aggregated knockoffs is that we solve the instability observed previously. So doing exactly the same experiment on the original knockoff and aggregated knockoff, we see that the FDP, the empirical false discovery proportion obtained, concentrates around the nominal value. So it's much more stable than the original plain knockoffs. And also, you are no longer in a situation with no power. You always make a detection. Of course, there remains some variability, but it's at least much better, and there is no catastrophic case. So we have done several validation on genomics and the brain imaging. Here is an example on brain imaging. Actually, in that case, you see that predicting some behavioral data from knockoff or aggregated knockoff would yield a similar solution, but aggregated knockoffs is still closer to another estimator, which is disparsified lasso, which is completely independent in the way it defines the solution. Actually, repeating the experiment among many different conditions and on a relatively large sample of data, so we are rather confident on the results, we see on the right side that the aggregated knockoffs yields a solution typically much closer to the disparsified lasso one, which is possibly a sign that it behaves better. It has also, of course, a reduced variability, which is a desirable feature. So this is an ICML paper that we published this year, so you can look at the reference for more details. Doing these experiments, I have quickly introduced the disparsified lasso without introducing it. I apologize, and I won't have time to introduce it in detail. I'm sorry for that. So remember that when we're in the case where n equal p, essentially, and if we try to do ordinary least square, it's a complete collapse. We have a crazy estimator. But if we replace the ordinary least square estimator by the disparsified lasso estimator, which will provide an estimate of the effect and an estimate of the variance about this effect, we obtain a much more reasonable, we actually recover pretty well the ground truth. So the disparsified lasso works perfectly well for this type of setting. So it's a generalization of OLS to high dimensional settings. So at that point, we have introduced the knockoffs mostly, which is a versatile technique because it can adapt to many different loss functions. Now with aggregation, it works even better. It's more stable. Maybe it's not optimal in terms of power, especially if we want to control the family-wise error rate. On the other hand, we have the disparsified lasso that is powerful. It's a deterministic approach, so I think it's a good feature, but it's only for linear regression, which is a limitation. So are we done? Well, not completely, because in my previous example on brain imaging, I actually, sorry, I went a bit fast, but I actually reduced the dimension of the data from 200,000 to 1,000 just to make inference possible. It would have been impossible to run inference with the knockoffs on the 200,000 dimensional data, and we would be powerless. And same thing with this disparsified lasso. Actually, we can simulate this situation. Just take a case where P is much larger than N and you still want to make inference. Your ground truth is in black, your estimate is in blue, and I present the confidence intervals. You see that here the disparsified lasso completely fails to detect anything because we are powerless. We are overwhelmed by the dimensionality. And what you can do then to solve the problem is to say, when data are high dimensional, they are probably structured. So you could, for instance, group nearby pixels and make inference on groups, not on individual pixels. So let's replace pixels by superpixels. So we do some dimension reduction and do inference on this reduced representation of the data. So this is what we propose to do for brain imaging with very slight modifications. So we start by clustering the data. So there are different ways to generate these superpixels or supervoxels. here we use word clustering. There are many alternatives to that. Then once you have generated this compressed data, you can run the estimator you like. It could be despecified lasso. It could actually be knockoff or anything. And you can work with that. But then we have a problem, because you will present a result, and the result will reflect the clustering that you have used. I'm going to illustrate that next. And this clustering is, of course, arbitrary. For most problems, like in genomics, like in brain imaging, medical imaging, there is no ground truth. You don't know the cluster. You can infer some kind of reasonable clustering, but you don't have an absolute solution. There remains some arbitrariness or chance in that choice, and you want to get rid of that, of course. So a solution to get rid of that is to do that several times with different clusterings and ensemble these different solutions using an aggregation approach, exactly the same, actually, the same quantile aggregation approach that I discussed previously. And here is an illustration. You can see, for instance, a case. It's just the same problem, but we try to solve it with different clusterings. And you see how variable, it's crazily variable, the solution. Just varying the way you cluster the data will generate completely different solutions. So you don't want that. What you want is a solution that is a kind of consensus across possible clusterings. And this is where the aggregated at the bottom will provide a much more reasonable solution. It will be the consensus, and actually there's a good face validity in that case. So the whole procedure is to cluster your data, so to reduce your data by clustering, by creating local averages of your signal, do inference on these local averages, this is illustrated here, and then ensemble your solution to obtain a better estimate, a consensus estimate about the significant regions. What we can show is that with this procedure, we can control not the family-wise error rate, because we are not making inference on each particular location. We are making inference on a given neighborhood of a given brain location. So what we control is a spatially relaxed version of an error rate. Here we consider the family-wise error rate, so the probability of making one false detection overall. And what we can control is, for instance, the probability of making false detections at a distance more than 2 of the true support. So you take the true support of the activation, you dilate it by a certain number, delta, which will be typically the size of the cluster that you use in the clustering. And you can actually show that you're not making too many false detections at a distance greater than delta from the true support. And it's actually the case. We have verified that on different simulations that were like brain-like. And we show that the so-called ECDL, for ensemble of clustered despecified lasso, control the family-wise error rate at a nominal rate. And if we now apply it on real data, on a relatively large sample, the Human Connectome Project data set, we obtain some brain maps with a good phase validity, so predicting the occurrence of certain cognitive conditions. In terms of precision recall, also this procedure has good properties. It actually behaves better than more standard solutions that would do some permutation or bootstrap analysis on the data. I think it's time to conclude now. So my main messages are that doing inference in a high dimensional, so large P case, brings challenges. One of them is computational cost, and I did not discuss that, but actually the solution I propose is very cheap in terms of computation, because once you have reduced your data to a small number of clusters, then running the estimators is much faster. So actually the solution is not only good for inference, it's also efficient computationally. But statistical inference is difficult, and anyway, in large P settings, we would be powerless if we don't do anything. So the solutions is to rely on compression. Here, compression was clustering, subsampling, so not taking all voxels value, but only local averages, and then ensembling different solutions to make sure we don't have any arbitrariness in the modeling choice. So you can see the solution I introduced as efficient stochastic regularizers. And of course, we can also extend that towards causal reasoning. Okay, all these things have to be implemented in software to become useful to people, and of course, open source software. And that's what my team is dedicated to doing. And with that, I would like to acknowledge my colleagues, especially Binnen Nguyen and Jérôme-Alexis Chevalier, who are the PhD students who did the experiments I presented, and my co-workers from the team, and other collaborators with whom we work on that, especially Joseph Salmon, Sylvain Arlot, and Mathieu Leral. And thank you for your attention.
Thank you. Any questions from the audience? I have a question about the, so you use it, essentially you use task-based fMRI, right? So in this
Yes.
person. So if you mentioned you use like 900 subject data, imagine that if the results are reproducibility, so if a result very similar, if I just use like 100 subjects or 200 subjects data and do the same thing, will be the same?
Yeah, that's an excellent way. So it's typically a good thing to do some small sample recovery experiment where you try to reproduce your results based on a much more limited number of samples. Still, in that case, this would not work well. You know, maybe I did not insist well enough, but what you're trying to do is really hard. If you just try to repeat that with 100, n equal 100, then it will behave quite poorly, because the lasso estimator, or actually the disparsified lasso estimator that you are using, has a large sample complexity. It needs a lot of samples to work properly. So going towards like 100 samples, I think we did it actually in the because one reviewer asked for it in our latest publication, but I really dislike it. I don't want people to use it that way, because it's too easy to draw biased conclusions by applying complex machine learning tools to small sample data. So I'm quite worried about that. So the point is, if you were using small sample data, then you need to use fewer features. So you need to decrease the number of clusters that you use to represent the data. If you essentially keep P as large as N, essentially you're right. But making inference on a 100-dimensional brain is a bit ugly, but you could do that.
Yeah, so I think they imagine that you have 500 subjects, but instead of focusing on the most high spatial resolution data, you actually look at the lower spatial resolution data. If the results are the same, you should see a huge overlap in the brain regions, right?
Yes. No, sure. No, but I agree with you that looking at the stability when you reduce the number of samples is a good thing to do, and we typically do that always because it's a good practice. And yes, essentially, you get it right. What we do is what to propose is to make inference easier by downsampling, by reducing the dimension of the data, and so losing some resolution, of course.
Okay. We also have seen some questions. I think we have quite a few questions. So the first question from Guo in Emory, he asked that, are you concerned that clustering workflow will reduce the resolution?
Yeah, absolutely. So there's no free lunch, okay? If you accept that it's not possible to do inference on super high dimensional data, then well, you need to lose some resolution to be able to still perform inference. And I don't see any good any way to get out of that. And yeah, so of course you can be clever in the way you do it. For instance, you could do your clusters that respect, for instance, the layers of the cortex or the brain regions if you don't want to mix signals from different brain regions. So, of course, you can still be clever doing that. Frankly, in neuroscience, people are always reducing the dimension of the data. They are always using brain atlases to simplify the data. They do that all the time. So I think it's not a big deal.
Okay. Our second question from Jolie Beer. How do you generate different clustering?
The different clusterings?
So I guess you use different clustering method to generate the cluster.
Oh, so yeah, very good point too. So there are two possibilities. Either you use a non-deterministic clustering method like k-means. So simply by changing initialization, you would have some entropy in the results. But what we do, we use a deterministic clustering, which is a word, but we train it on a random fraction of the data. So this creates some randomness. And so we can create some clusterings with enough entropy, with enough variability to make sure that we are not always sampling the same thing.
Okay. Okay, I need to stop.
So I think I gave my email address, so I'd be happy to answer more questions if needed.
Thanks. Thanks very much, Bertrand. Thanks to all the speakers in the session. Thanks very much, Ting Ting, for keeping us on track. We have about 15-20 minutes break. We want to give everybody a break. Bertrand will go to sleep, but maybe other people can have coffee and come back. So we will start our next session at 3:30 Eastern Time. Hopefully you will all stay engaged and awake and come back and see you. Take a break.
See you in 15 minutes. Thank you for your talk.
Merci beaucoup, Bertrand.
Thank you. Thank you for the invitation. Very nice. The presentations are really great. Thank you.
Yeah, we are trying to hit many different topic areas, so everybody gets something.
Yeah.
From this. So your talk was a perfect blend of we want statistics, we want high dimensional images, so it fits all the right.
It's a very timely thing. I see, for instance, at NeurIPS this year, there are lots of papers working on different flavors of inference. I think that high-dimensional inference is a quite hot topic at the moment here.
Yeah, absolutely. I think images are just an excuse for doing it. If you have some techniques, it could be used in every data. Every data can be made high-dimensional very easily nowadays.
Yeah. Well,
ultra high dimensional.
Ultra high dimension.
Yeah.
Yeah, but in genomics, truly, we have this issue.
But what is nice about you guys at INRIA is you not only write papers, but I think it's maybe you are forced to write the codes or forced to write packages. Maybe it's part of your paycheck.
Yeah, I think it's really, I think as researchers in applied math and in computer science, we always need to think, are we useful to the practitioners? And if we just, publish paper at NeurIPS or ICML, well, that's great, but the practitioners won't read these papers, they won't use the methods, so is it useful? So I think it's important to make sure that what we propose becomes usable at some point by actual users.
Yeah, no, I think the providing code is the simplest, easiest way to ensure that. I think we are in the time where people sometimes ignore the theory because there is no code.
Yep. Yeah.
Theory. So,
but it's true that maintaining code is expensive.
Yeah.
It's a big effort.
But I think at INRIA isn't it part of your goal or aim in your group that you have to have industrial component and you have to provide packages and you have to have some software deliverables?
Yeah, so it's a, well, not everybody does it. Some people do it, and we are quite committed to that. That's true. But I think the motivation is also that we do, I think, to some extent, better science when we have a good software and where we, for instance, we started scikit-learn 10 years ago. And for us, it was a huge gain at the end because people contributed methods that we would never have been able to do ourselves. And so at the end, this doing software is a way also to gain a lot and to meet great people. So
yeah, I think it's a contribution in its own, and sometimes that can pick up much more than the paper, a good paper.
And
sometimes
also for students, it's important for the students who are going to work in industry. For some of them, I think it's important that they know to implement well software. So it's a good education component.
I hope my students are listening. It's a good deal. Okay, thank you very much.
Yeah.
Take a little break.
Thank you for the invitation.
You're welcome. Thanks for coming.
Anuj, I have a suggestion. If you are still there.
Yes, I'm here.
Actually, I think that it would be great if we can have such these breakdown groups, maybe in the coffee break, maybe tomorrow. It would be a nice idea if just split it into different groups to have a discussion friendly. And yeah, that was just a suggestion.
Having a breakout room. The issue is, firstly, the manpower to manage those rooms, because one of us has to be present there. The way the rules are for this Zoom is we have to do it manually. Every person goes in, every person goes out, has to be done manually. So we need manpower. The second thing is we didn't ask permission from the speakers that they will actually stay for the whole thing beyond their own session. So we can announce that if somebody is interested in staying back, we can create a breakout room for the speakers to chat with the audience. But we didn't plan it, we didn't organize it, just lack of manpower.
Okay, thank you.
As it is, we have about, we have 200, 250 participants, and every time somebody leaves and enters, it is manual process. So it just adds on to the, and then it will be the same for the breakout rooms. The idea is very good, but we just decided to do
in practice doesn't work. By the way, thanks for the nice organization. It's really enjoying and wonderful workshop. I enjoyed a lot, and thanks for everything and the other organizers.
Okay, thank you. So let's make sure we have the speakers. Let's make sure the speakers know which day we are. Let's see. I think David came in and out.
Yeah.
So Marina, you will be running the show now.
Yes, I'm chairing. I sent an email to the three speakers as a reminder.
Okay, that's a very good thing.
And I think I've seen Rebecca and Shao on the call already.
I have seen all the three of them during the day sometime.
Okay, okay.
So that's good news. And as soon as they come back in, I will make them the co-host so they can share their screens and stuff. one of the difficulties of these virtual conferences is you don't see people there physically, so you're not sure how far they are from joining. I'm told that we are actually being live broadcast on YouTube. This is a little bigger than our original plan. And something called Bilibili, which I don't know much about. That's the Chinese version of YouTube.
Could you share that link, the YouTube link?
Okay, let me see if I can find it. I'm going to copy it in the chat. This is David. David?
Sorry, I was muted. How's it going? To make sure.
Good, good. How are you?
Good.
To have you.
I'm a zoo. Put a bunch of windows and make sure my share screen thing works.
And maybe try to share that window. Now you should be able to do it.
Okay, do I have sharing ability?
You do, yes.
I think I just did that, so you can try it. Give it
Okay.
a shot. I did.
Share screen. Share. I made PowerPoint slides, so which I'm not used to you doing anything with.
Then if you go to full
I just said to go to full screen. It didn't.
full screen,
Yeah, I just told it to, but it okay, let's
Right at the bottom.
Yeah, usually there's that thing at the bottom of this. Okay.
Yeah.
That's good.
yes, this works
Yeah.
nice.
So it wasn't on a high dimensional. It was sort of neuroimaging. So apologize.
It's okay.
That's fine.
That's the only
Nobody's
imaging
gonna
thing I have.
complain.
Until we figure out how to analyze 500,000 pictures of insects, then it's neuroimaging.
Let's see. I think Becca was there too. So if let's see if she wants to test her system.
Yeah, I'd be happy to.
Okay, David, can you not share, unshare for a second?
Okay. Yes.
Yep.
How's that?
Perfect.
That was cool.
All right.
That leaves Shao.
And Shao, perhaps?
Shao
Yeah.
is there. Yeah, Shao is here.
He's here. He might be on a break.
So, I mean, when I say he's here, may not be here. He's just logged in. One of the difficulties about running this sort of thing with large audiences, we have been asked to maintain all entries manually. And so we are ranging between 200 to 300 people at any time. And it's just manual. I mean, if somebody's signal goes out and they come back in, it's an entry.
That's ridiculous.
It's the university, somehow they said that if you reach beyond a certain number, then you have to screen people.
I apparently have emission capabilities because I just admitted someone.
You did?
No, it popped up and I said admit, and then it went away. So.
Yeah, no, for all of us, since we are all co-hosts, we'll all see that process continuously. We have, in terms of total registered numbers, the last check, I think yesterday, was 860.
Oh, wow. Geez, that's huge. Yeah, for a Zoom conference, arguably too big.
Yeah, so I think this keeps us on our toes.
Maybe I'll share my screen again.
Yeah, now you can go ahead. I don't see where Shao is.
Can you see that then?
No.
Yeah. Oh, there is Shao. Shao, you want to quickly test your presentation just to see if it works? share your.
Okay. So I share my screen?
Just share screen, yeah. Let's make sure that is
okay.
All good. Yeah, that was good.
So you can see my screen. Okay, thank you.
All right, David, give it one more shot.
Okay.
Yeah.
Works. Okay, let me just stream it.
Should we start?
Yes, please. There's one more piece I want to quickly check that we are recording. Aditi, can you hit the records? Okay. All right, go ahead.
All right, so I think we can get started. Welcome back, everyone. So this is the session on high dimensional data analysis part 2, I guess. And my name is Marina Vannucci, and I will be chairing the session. As we have been doing throughout the day, just remember to type your questions in the chat because you cannot unmute yourself. So just write questions in the chat. Okay, so our first speaker is David Danson, who is the Arts and Sciences Distinguished Professor of Statistical Science at Duke University. His research interests are on the development of novel approaches for representing and analyzing complex data. A particular focus of his work is on methods that incorporate geometric structure and on probabilistic approaches to characterize uncertainty. And the title of his talk is slightly different from the one on the program: Multi-Scale Graph Principal Component Analysis of Brain Connectomes. And David, you have a total of 30 minutes, up to you whether you want to use a couple of them for questions.
Okay, yell at me at with 5 minutes left or something like that, and I'll shut up.
Okay.
Yeah. Thanks a lot for the invitation and the introduction. And so this is very applied work, and so we're really interested in structural brain connectivity and brain connectomes. And so we have a grant from NIH with Zhengwu Jiang as my collaborator on this. And we've been interested in structural connectivity, which is the pattern of anatomical links in the brain, not to be confused with functional connectivity, which is something that people study, I think, a lot more than structural connectivity, which is more based on statistical dependence and activity in different brain regions. So structural connectivity, there's actual physical connections. Okay, and so one of the motivating data sets is the Human Connectome Project, and this just shows a picture from the Human Connectome Project, a visualization of the connectome. And so you can see there's all these little fibers here. And so we'd like to kind of infer that type of geometric object. It's a type of image, you could say, or you could represent it often as a network. And we can get something like that for maybe thousands of different subjects, about 1,000 in the Human Connectome Project. And then we would like to statistically analyze it. So we'd like to relate this brain connectome to other variables, to age, to neuropsychiatric disorders, to behavioral traits, to exposures, things like that. Okay, so that's the game we're trying to play. And this type of data necessary to get brain connectome information like this is now routinely collected and really not all, but very many brain studies, and some examples of large studies that have data like these that can be accessed with, if you get permission, or the UK Biobank and the ABCD study. Okay, so we're doing diffusion imaging, and so we're really interested in connections in the brain. And so if you zoom in really high resolution, then we would have all of these types of axons or neuron cells. And we can get images of that using like EM connectomics. If we had like a fly brain, and you can get these kind of nanometer slices in the brain, and then you can try to reconstruct pieces of the brain on the individual cell level. But in terms of live humans, we can't do that unless we kill them and chop their brain open. So we try to avoid doing that. And so if we instead are relying on diffusion MRI. And so diffusion MRI, what it can pick up is more at a macro scale. So it tends to be that these neurons are tightly bundled into these kind of pathways or highways for neural connections and activity in the brain. And we can get that. We're trying to infer those kind of fibers, which are many of these neurons that are tightly bundled together in a kind of highway. Okay, and so how we do that is sort of indirect. So we're relying on the fact that diffusion in brain tissue is different depending on whether you're in gray matter or white matter. And white matter is where these kind of fiber tracks are living. Okay, and so in gray matter, the diffusion tends to be unrestricted, kind of in all directions, where in white matter, the diffusion tends to be restricted, which you might call anisotropy along these kind of fiber tracks. Okay. And so, so the game is based on imaging. You can kind of get indirect information on this. So at each voxel in the brain, we might want to infer some sort of orientation and magnitude of the diffusion. It's usually done in a couple of different ways. Classically, a lot of people did inferences on diffusion tensors. And so they would take at each voxel in the brain, they would get this sort of positive semi-definite matrix. And there's a lot of statistical work kind of trying to relate that to covariates, like separately, maybe for each voxel in the brain. That often doesn't give you much signal. So there's a lot of noise in that data, and it's given the whole DTI imaging data kind of a bad reputation as not giving you a lot of signal. Another kind of approach is to take this kind of more hardy approach where we're looking at orientation distribution functions. And then we can define a type of stochastic differential equation to try to do fiber reconstruction. And so fibers are all these little tendrils here in these images. Those are hopefully tightly bundled neurons, and we're indirectly recreating those. Okay, that's the game. Okay, so here's the type of thing we'll get for each person's brain. And Zheng Wu, really my collaborator, is really talented at putting in geometric information and developing algorithms to get objects like this, I think, in a real state-of-the-art way that with less measurement error, less distortion than in other methodology. But then the question we have is, okay, we have something like this. Well, how do we relate this to see how that varies across individuals, both randomly and also systematically related to covariates? Maybe one covariate might be whether it's a normal individual or a diseased individual. And the data are really enormous. If you represent them like this or represent them in different ways, the data for each subject are really huge. Okay. So what usually is done is to take something like that. So initially we do this kind of pre-processing of the data to do this kind of learn these fibers. And then we might try to turn it into something that we can do statistics or machine learning on to look at relationships between the brain connectome and covariates. Okay, and usually what's done is we try to define some types of regions of interest. So we can break the brain into regions, and so we could take this whole thing, break it into a bunch of regions of interest. They're usually volume based, and so we have some sort of Euclidean region. Okay, now we have another Euclidean region. Well, that's maybe that pair of regions might be. You could write that as a cell in an adjacency matrix, and then you might put in that cell some sort of measure of the connection. So that might be the number of fibers connecting those two regions of interest, volume-based regions of interest. And if you do that, then you'll get one of these things called a connectivity matrix, okay, which is a type of graph or network data. So each node in the network is a region of interest. The edges are weighted edges, often denoting the strength of connection between two regions of interest in the brain. Okay, and so usually when you do this kind of tractography to try to recreate these connectivity matrices and define regions of interest, you do it in this kind of volume space, which is not really the right way to do it geometrically, and then as a result can create some distortions. Because what actually happens is that, the white matter in the brain is on the cortical surface. And so the cortical surface of the brain, you have two hemispheres. You can say that you could map it with really little distortion to a pair of semi-sphere, the half spheres, okay? So you could actually represent it geometrically as two, you take two spheres, chop them in half, and then, okay, well then really the cortical surface can be represented that way. And so if you just view it Euclidean in terms of defining these volumes, you end up getting a lot of distortion. And so what Zheng Wu has been doing is instead utilizing this, what he calls a white surface, which is the surface, the cortical surface, and then take into account that these white matter fibers are living on the cortical surface and doing the reconstruction. Okay, and so then you can define what you can call a surface-based connectome map. So you do sort of seeding of these differential equations to define a surface flow, to define these fibers on the surface, the cortical surface, okay? And then if you do that, it really gives you an ability to even represent the connectome in a continuous manner that allows us to avoid doing gross scale regions of interest, and allows us to then, we have this continuous representation of the connectome on the cortical surface that we can represent as two hemispheres, the product space of two hemispheres. And then based on that, we can then reconstruct the region of interest representation at any scale, okay? So we do start by putting a fine mesh grid on the surface. Okay, so this is our sort of pre-processing. And so once we do that, we do this surface-based connectome mapping, we can do sort of like on that surface, you can do a type of Delaunay triangulation of the surface to get a very, very, very high resolution representation of the connectome. Okay, and so now we have extremely high resolution data, and then we can use that high representation to represent the connectome at any coarser scale that we want in a kind of coherent, seamless way. Okay, and so this sort of shows that a little bit, and so so we have the high resolution. So this just zooms in and shows, okay, well, here's a representation of the connectome if we put it in this adjacency matrix form between regions of interest. But we can really consider a multi-scale formulation. So if we zoom in, so that we're putting the red square here around the frontal lobe of the brain, and now we can zoom in and look at the connection structure within the frontal lobe of the brain. Okay, and we've been thinking about ways to like even try to use some type of geometric wavelet method or something to be able to represent the data on all scales, but I won't be talking about that today. Okay, this just shows on the bottom the what we could do in terms of, well, one atlas to represent the brain that's very popular is the Dessicon atlas, which does breaks the brain into 68 regions of interest. Okay, and so if we do that, we could call that our 1-1 specification. So that's lower left hand, and it would show one individual's brain in terms of an adjacency matrix representation. We get this this matrix on the lower left. Okay, if we then break each of the Dessicon atlas regions into smaller regions, then we can get this finer scale representation that's the middle of these three matrices on the bottom left. If we can do whatever we want, then we could also say, well, let's break it into higher resolution on in one hemisphere, and so then we could get this 2-4. So on each part, in the one hemisphere, we would be breaking each of the Dessicon regions into 2. In the other hemisphere, we break it into 4. And we found that actually, when we use multi-resolution statistical methods to summarize the brain and relate those summaries to human traits, that we did a lot better if we included not just all symmetric representations, but we also included asymmetry. And so by asymmetry, I mean that we're we're representing the brain at a higher resolution in one hemisphere than another. Okay. Okay. So so what I wanted, the main theme of the talk today was on multi-scale graph principal components analysis. And so basically what we have is we can get at any variety of scales, we can get this kind of matrix representation of the brain for each individual in a study, and you might have 1,000 or thousands of individuals in your study. And so what I'd like is to somehow get some type of graph embedding where to make the statistics easier. And so we might, the original object we had, so if we go back, was this thing in the upper left. It's this incredibly complicated thing. So this all these millions of fibers in the brain that are in this intricate geometric pattern. I'd like to get closer to being able to define statistical machine learning methods to directly characterize changes in that. For now, what can we do? Well, what people usually do is they just represent it as a single connectivity matrix. But what I'd like to do is represent it as a series of connectivity matrices at different scales, and that should encode more information about the original beautiful geometric object than if we had a single scale. And then if I have all that information across scales, can I come up with a single embedding where I'm turning that information into a single real valued vector of trait, the scores, something like principal components for each individual. Okay, so then I can take your brain scan, I can take Marina's brain scan, and then represent it in this way, go through some number crunching, and then spit out maybe a 30-dimensional feature vector for Marina, which is summarizing her brain structure, okay? And I could do that using just a single scale, but that's not gonna work as well, we find empirically, and it's sort of obvious, I think, but then if we used a whole variety of scales, and then had a single set of scores summarizing Marina's brain across those scales, okay? So that's what we're gonna do. And so we call this multi-scale graph principal component analysis, and it's really not very complicated. Okay, so so we're going to be motivated. I'll show some results for the Human Connectome project. And so a nice thing about this project is we have data, these imaging data that we can use to do these structural connectome processing for over 1,000 subjects. And we also have a really rich information on traits. And so demographic information, behavioral traits, cognition, motion, personality measurements, substance use, et cetera. Okay, so we looked at, in our analyses, 175 different traits. And so these are different attributes of the people. And we also have their brain information, okay? Okay, and so for each subject, so you end up with like a tensor, because for each subject, if we stack their different weighted networks together, we're going to obtain a sort of three-way tensor of dimension V by V. V, if this is just a one scale, say. V is the number of regions that we have, that we're representing the brain, we're coursing the brain into V regions of interest. And so then we get a V by V matrix for each measure of connection between pairs of regions, okay? And so here it shows, we could just have a binary, that would be A. That would just say, we might just say, okay, well, if there's any fibers connecting the two regions, we get a 1. If there's no fibers, we get a 0, okay? We could also do a count, just the number of fibers, take the log of that. We could do a cluster number. We could cluster the fibers. We could do an average fiber length. We could do a variety of things. Max fractional anisotropy, mean fractional anisotropy, connection surface area. So you get different features measuring the connection between each pair of regions. And then we get a tensor, okay? But now that's just for one individual. And so then if we stack n subjects together, we're going to get a four-way tensor, which will be V by V, that's different regions. M's the number of features, measuring connection strength, and N is the number of subjects, okay? Each of these tensors, to create a little bit of a headache for us in trying to develop algorithms, each of the tensors is semi-symmetric because you know, if you're looking at two regions of interest, there's no directionality between the two. And so if we look at any one of these matrices, they're going to be symmetric. Okay, so we have this kind of symmetry constraint that we need to deal with. So it doesn't matter whether I'm like region I and J or J and I, it's the same. And so, Okay, so then we do like just a kind of vanilla tensor decomposition. So for people who are used to tensor decompositions, we use a CP decomposition, but we have to make it semi-symmetric, okay? And so we could say, oh, if I have some tensor X, I can represent it as approximately in some sort of low rank form in the CP sense, where I'm writing it as a sum of from little k is the number factor index to capital K. So I like factor models, and so I like these models a lot, as it's sort of a factor model for tensors, okay? And so, things to say about this is dk might be just a scalar, you know, a vk or a vector of network modes. They're going to be specific to each edge of the brain, features of each region of the brain, I mean. And that what we're interested in, particularly in some sense, is the subject modes. And so UK is going to be subject for each of the n subjects. It's going to be a score for that subject, providing a sort of weight on the kth subnetwork in some sense. And so we're taking the brain, we're writing it out as a sum of k subnetworks, and then each individual has different weights on those subnetworks. Okay, so this would be just on one scale. So if we were doing a one scale tensor factorization, we could use this type of approach. Okay, and then we can, in order to certainly ensure identifiability and sort of in a PCA type way, we can enforce orthogonality among the U's, okay? And so this just gives a kind of a flavor. If we look at just the V, like V.V, V1.V1, well, that's going to give us what we might call a subnetwork. And so that's one component representing variation in the brain. We're going to have K components. It might be certain individuals load more on certain components than other individuals. And that's how we're representing variation across individuals in our sort of hierarchical model. Okay, and so what do we do? So we had a paper in neuroimage a little bit ago doing this kind of single scale, we called it tensor network PCA. It tends to work quite well. What we're doing, I'm talking about today is, well, we actually extended it to multi-scales. And so here I'm going to say, well, now instead of having one tensor, we're going to have R tensors across R scales. The J, little j, is indexing the scale, okay? And what we're going to do is everything in the tensor factorization, our CP tensor factorization, is going to be scale specific, except for the subject scores, okay? And so everything's scale specific except for what common part across scales are the UKs. And so those are like the subject's principal component scores. Okay, that's what we're using to represent or summarize that individual's brain connectome in really a very interpretable way. You could imagine, oh, I could extract these components, and now let's say that relative to Marina, Marina has a higher value of U1 than I do. Well, we could see exactly what the impact that has on the brain. So we can map that back onto the brain. You might also relate these components to traits. Oh, it might be that U1 is higher value of U1 means that you're more likely to binge drink or something, more likely to have binge drunk or have smoked marijuana or something. And so then you can map that back and see what the effect of that is on the brain. And so it becomes a very interpretable approach, okay? And we're sort of anchoring the fine scale to coarse scale data. And that also has an effect of really reducing the effect of noise in the data. So even if we've done simulation studies like this, so let's say that all of the information was on one scale about, you know, the components, and so like the one scale would be fine. But let's say I add some measurement noise, but now if I'm going to actually put data on the other scales, I might just be using those to get a better representation at a single scale. So you're sort of borrowing information across the scales to improve inference on a single scale. That's one nice feature. Okay. Also, you can show that it's actually not restrictive, and so if you blow up K, you can have arbitrarily huge changes in structure across scale. So it's very flexible in that way, okay? But we need, in order to fit this, so we have a lot of big data sets. We need like an efficient way to optimize. I tend to be Bayesian and define likelihood-based approaches, but today we're just going to try to define some type of efficient optimization algorithm. Okay, and so our idea, or really this was work of Stephen Winter, who's a fantastic master's, hopefully soon PhD student of mine, is to minimize the squared error within each scale. Okay, and so that's a sort of obvious thing to do. And so we have this kind of tensor X, and we're looking at, well, what's the difference between that and some sort of K component CP factorization, and take the L2 norm. And that now we're going to put constraints. The reason that we need the D at all is that we have some sort of norm 1 constraint on the U's and the V's. We also have this other constraint. And then we can write this as a series of rank 1 maximization problems with the n-mode product. Okay, and using some sort of tensor representation, do a bit of tensor linear algebra, and we can write this as equivalently to this kind of maximization problem subject to these constraints. And so here, the P's I have here are the projections onto the orthogonal complement of the V's, okay? It looks somewhat complicated, but really it can be written entirely in terms of dot products, okay? So
5 minutes roughly.
Okay, awesome. So our rank 1 multi-scale problem is that you have the sum of squares of single scale problems. And you can just use this very simple block coordinate ascent, iteratively updating in this way. And you have this kind of nice eigenvalue property. And it's really interesting that if you look carefully at the multi-scale modeling is actually combining spectral information across the scales. Okay, so I only have a few minutes left. It would be nice to have time for some questions. And so we tested it on some initial data from the HCP. We had some multi-scale representations that we fed in. And what we looked at is here is like, let's look at all these different traits and look at which proportions show an improvement in out of sample prediction using a multi-scale versus a good single scale method. And you can see the blue is like the improvement. Well, no, this is the percent improvement right here, the plot. And so the blue is relative to the desiccon, and the orange is relative to a finer scale representation where we do a higher resolution within one region. And we can see that overall, this percent improvement is pretty remarkable, actually, relative to using just a single scale method. This is 0 to 50% scale. And this just shows all the improvements that we get across different traits. And so you really got a lot of improvement. And it was really remarkable, I think, the ability to actually predict a substantial proportion of a good proportion of the variation in the trait from the brain connectome. There's a lot of signal in the data. Okay, and so we wanted to look at group differences. I'm kind of out of time, but we could actually obtain interpretable results. We looked at one interesting variable as worst lifetime binge drinking. And we can get these type of network results. And so we can put our results back onto the network and show which regions, which connections are related to a particular trait. And we can do this in a single scale way or a multiple scale way to get really interpretable results. Okay, and I'll just stop there and with this slide, and then just kind of actually put up my collaborators, Zhengwu Zhang and Stephen Winter.
All right, great. Thank you. Very nice talk. And we do have a few questions in the chat. I'll read them for you. First, from Aaron Scheffler, do you find that one scale of the many scales drives the subject mode scores?
That's a really good question. I mean, I think that, you know, it's not going to completely drive it to the extent that even if we cherry pick the best scale, like say the finest scale data, and we just use that, you're going to get different results than if you use across multiple scales. And we get noticeable improvements in things like prediction of the traits. And so I think that even though you might get 80% of the way there with a single fine scale, you get a lot of gain by adding the other scales.
And another question from Yupin Wong. Can you identify common connectivity network among multi-scales?
Yeah, that's exactly what we're doing. Yeah, that's interesting. And so, yeah, so I mean, one thing you can do is, I mean, common connectivity network across multiple scales. So, I mean, if so you're actually taking the scores and you put it in that way, you look at the covariate effect, and then you project it back on the brain on a given scale. So you can look across scales, and then that's a really actually interesting question that we don't have exactly a method for, is to say, okay, well, what's the commonality or link across the scales? And can we even have say a generalization where we explicitly link across the scales? Because now we're not actually explicitly tying the V's together. And so what we would do is we would look at different scales, and then we could like do inferences on just look or summarize the results, but we don't have an explicit tie across the scales.
And finally, from Joanne Beer, do you think these methods will translate well to functional connectivity?
That's a fantastic question, and I would say yes. And we are looking at that right now. I have a student looking at that. What we'd like to do is do it for both functional and structural, but I think already you can do it directly for functional. We haven't tried it, but that would be really interesting to try. Yeah.
And finally, while you unshare perhaps, and Rebecca is going to come on, how many PCs and factors, big O, would you recommend using?
Yeah, I mean, so we can actually do that. We have a couple of different criteria. The one would be, oh, well, just a usual PCA criteria. Let me unshare while I'm doing this. Usual PCA criteria where you like look at some elbow plot or something, but we can also do it based on predicting the traits. And then you'll often not get a tiny number. It might be, because the brain is really bloody complicated. And so if you did it from start, I might even use 30 or something like that.
All right, thank you. Thank you very much, David.
Oh, thank you.
All right, perfect. So Rebecca is on. So next speaker, Rebecca Willett, a professor of statistics and computer science at the University of Chicago. Her research interests include signal processing, machine learning, and large-scale data science. A particular focus of her research is on methods to leverage low-dimensional models in a variety of contexts, including high-dimensional data and missing data, as well as data that arise in ill-conditioned inverse problems. And the title of our talk today is Model Adaptation for Inverse Problems.
Great, thank you very much for the introduction, and thank you also for including me in this really cool workshop that's bringing together so many different people from different backgrounds and perspectives. So the work that I'm going to tell you about today is some recent work that I've been doing with my graduate student, David Skilton, and former postdoc, but now assistant professor, Greg Anji. So in general, we're interested in trying to use to solve inverse problems in imaging. And I mean that in the following sense. So we're going to think about X as being the image that we're ultimately interested in, but we don't get to observe X directly. So rather, we observe some linear projections of X, or we observe Y, which corresponds to some matrix A times X plus epsilon. So we can think about A as representing somehow the imaging system that we're using. So for instance, perhaps it's inducing some blur, or we're getting a lower resolution image than we'd like, or we're taking MRI case-based measurements. And so what we'd like to be able to do are to take these measurements Y, and from that, figure out what X is. So this is a problem that's been well studied for a long time. More recently, people have been examining how we can learn solutions to inverse problems. So we've been collecting huge databases of images that people have been using to train neural networks for things like image recognition. So we have access to huge numbers of images. And the question is, instead of saying ahead of time that we've got prior knowledge about what structure might be in the image, so that it's smooth or that it's sparse in some basis or that it has a small total variation, instead, why don't we think about these training data sets as somehow being samples drawn from the distribution of images that we care about, and try to learn a system that will map these distorted measurements Y to images X based on the information in these training data sets. So often we can think about these systems in sort of a generic way, where we've got this sort of machine learning system that we're going to train. Its input is some observations Y, the output is an estimate X hat, and that depends on some parameters. So first of all, we've got this phi here, and phi we can think about as corresponding to all the weights of any neural network or whatever system we're using. And potentially, frequently in fact, these learned systems will also depend on A, the forward model that we're using to generate the Ys. So here's an example of this idea, one of many that are out there, called unrolled gradient descent. So the idea is this. Imagine that we wanted to find a good estimate of the image by minimizing, say, a squared error loss plus some regularizer that you could think about as corresponding to a negative log prior. So if we knew what that prior or that regularizer was, then we could try to find a good image X by just applying gradient descent to this objective function. So with unrolled gradient descent, the idea is that we kind of think about a series of, say, B different iterations of gradient descent. And within each iteration, which I'm representing by one of these blocks with dashed lines, there's kind of two things going on in parallel. One, we're taking a step that depends on the forward model A. So we're trying to push our estimate towards something that's a better fit to our observations. And then there's, in parallel, something that corresponds to the gradient of our regularizer. And so what people have done then is they've said, well, let's take this basic structure framework, but replace the gradient regularizer, or I'm sorry, the regularizer gradient with a neural network and use all of our training data to try to train the weights of this neural network. And so in the end, we've got a system like we have up here, where there are some learned weights, the phis, that are telling me something about regularizing my estimates. And then another component that depends on the forward model A and kind of connects the images that we care about to sort of the physics of the sensing system. So this is just one example out of many different approaches that have tried to use machine learning and neural networks in particular to try to figure out how to solve inverse problems in imaging. And down here at the bottom, I even have two kind of tutorial or review papers that might be interesting. But today I want to focus on a related but slightly different problem. So we've already seen many examples where we can train systems like I just described to estimate an image from the measurements Y. But what I want to consider today is, well, what happens if we train for one forward model, let's call that A0, but then when we actually deploy this, we have data corresponding to a different forward model, A1. And we call this phenomenon model drift because the forward model A has somehow drifted or shifted a little bit between when we did our training and when we're actually going to use this. And this is actually a real world problem. It's not just something that we invented because we like doing the math, even though that's fun. So for instance, we could think about MRI. So with MRI, when you set up your scanning system, you have to make all kinds of choices. You have to decide whether you're going to do Cartesian or non-Cartesian case-based sampling. You have to decide by how much you're going to undersample. You're going to have to take into account coils and sensitivity maps and inhomogeneities within the magnetic fields, et cetera. And so all of these different, setups for how we do sampling in MRI correspond to different forward models or different versions of this matrix A. And there's been evidence in the literature showing that if we were to train one of these systems for a certain forward model and then even slightly change it at deployment time, everything just sort of crashes and burns. There was even one really interesting example where they trained for 4-fold undersampling But then they deployed it on a system that was doing threefold undersampling, and everything broke down. So they got to, they were collecting more data, richer, less undersampled data, but they hadn't trained for that. And so the reconstructions were worse with more data. So what we want to do is we want to be able to correct for this phenomenon. And you might just say, well, why don't I just retrain a new network every time I've got a new different forward model A, or every time I've got a new different setup for my MRI scanner? But that's generally going to be infeasible. In particular, you could imagine a setting where somebody were to train a particular system and a particular common setup using a bunch of ground truth data, and then they release their algorithm for reconstructing images, but they don't have permissions to release all of the personal MRI scans of people that they use to train the system. Okay, so we want to be able to figure out how to correct for this model drift without assuming that we can just start over from scratch every time the model changes. Now, the naive approach that I'm sure many of you have already even thought of is to say the following. Well, when I started off, I told you that these learned systems often incorporate knowledge of the forward model, like A0. So why don't I just plug in my new forward model A1 and work with that instead? Would that work? And the answer is no. I'm going to show you some examples of how bad that is in just a second. But it's pretty clear to see why that would not work very well. And for me, what's most intuitive is to think about this from a null space perspective. So a learned reconstruction network that's trained with data that corresponds to one forward model, A0, is essentially learning how to fill in images or fill in the null space corresponding to A0. So if we thought about A0, for instance, as corresponding to, you know, the upper left part of the image being blocked or missing those pixels, then what we're doing when we train is we're figuring out how to fill in those missing pixels. So then at deployment time, we have a new forward model. We're missing a totally different set of pixels. Then we won't have learned how to fill in those pixels. We've learned how to fill in a different set of pixels. And so if we were to just kind of, you know, take this approach that I was describing here and say, instead of plugging in A0, plug in A1, well, it doesn't really solve the problem, because the learned component, this neural network that's embedded in our system, hasn't really learned to represent the information in images that lies in the null space of our new forward model A1. Okay, so this is the general idea of the approach that we're going to consider here. So we want to train a reconstruction network for a known forward model, say A0. And we're just going to assume that that's a solved problem, and we've got that. And now what we want to do is adapt to a new forward model. And we want to do this without assuming that we've got access to ground truth images, so we can't just start over from scratch. And we might even want to have this work without knowing exactly what A1 is, without being able to fully calibrate our new deployed system. Okay, so a little bit more mathematically, this is our basic setup. So when we train, we're going to have a collection of samples corresponding to X, Y pairs. And I've got the little 0 superscript here to correspond to the fact that these pairs all correspond to this first forward model A0. And A0 may or may not be known in general. But then at deployment time, when we're actually going to be getting measurements of the form y equals A1 plus x, times x plus epsilon. And this is what we want to correct for. And so what we're going to have at our disposal in order to do this correction is a bunch of calibration samples. So a whole bunch of yi's, but not xi's. Okay, and so the question is, how do we figure out how to adapt to this new forward model using just these yi's? So before I move on, I want to kind of put this in context relative to some other issues of drift that show up in machine learning. So you might have seen some papers that talk about distribution drift. And so we can imagine that there's some joint distribution underlying the XY pairs. And with distribution drift, we assume that that changes, that distribution is changing in some way between when we train and when we deploy. So that's in contrast to what we're studying here, which is model drift. So with model drift, the assumption is that what's changing is the distribution of the Y's given the X's. And even if we don't know exactly what our new forward model is, we still know that there's somehow this linear relationship between Y and X, and it's that linear relationship that has changed. So it's sort of like a constrained form of distribution drift. Now, on a related note, there are models, or there are methods in the machine learning literature on things like domain adaptation. And there, the idea is that you would first train with a whole bunch of samples from one distribution, and then you would want to adapt to a new distribution using a small number of samples. So for instance, you could imagine trying to train an image recognition system using iPhone images, and then you want to somehow use that learned neural network in order to adapt to a slightly different domain, say infrared images, where there's some things in common, but it's just not exactly the same. So what we're talking about here today is model adaptation, which is somewhat different from this domain adaptation setting. We first train with many different samples from a nominal original distribution. And then our goal is to adapt using a few samples from the new distribution, but where we only get to observe the Y's, we do not get to observe the X's. So this is a somewhat more challenging problem than domain adaptation because we have less information at our disposal when we are doing the adaptation. So before we get into methods, let me just show you some nice, pretty pictures. So this is an example actually from MRI. So here's the original image. And here's what we can accomplish if we were to train for one forward model and then nothing drifts, nothing changes at deployment. So this is sort of the baseline best case scenario. This is what we hope to be able to accomplish. In contrast, this image on the lower left is what happens if we train for one set of, say, k-space measurements, but then at deployment, we use slightly different k-space measurements. So in this case, we're doing no model adaptation. This is just sort of the naive approach that most people would consider. And it's dark and there's lots of really weird distortions and errors that are in here. And in contrast with model adaptation, we're going to get reconstructions that are much more on par with this sort of baseline of what we would be able to achieve if there had never been any kind of model drift. And this is a pretty general purpose approach, so it works on other problems as well. This is an example where we had an image corrupted by motion blur. So again, here's the original. Here is sort of the best case scenario where the motion blur that we trained for is exactly the motion blur that we have to test on. This is what happens if we don't do any of this model adaptation. So if we train for one motion blur and then at deployment, the motion blur is a little bit different. And there's tons of artifacts here that are not present within our model adaptation framework. And because we're on Zoom, I'm just going to make these huge so that you can kind of see the differences in the images and how many more distortions there are on the left if we don't use these model adaptation approaches I'm describing. Okay, now, some of you might also say, you know, why do we need specialized methods? Why not use generative models? So with generative models, you can think about this as saying, taking your training set and just trying to learn a distribution over the space of all images. So when people talk about learning generative models, those generative models are basically a representation of that distribution. So if I've learned that distribution, or if I've learned this generative model, then I can potentially use it to do reconstruction. So if I were to know what my new forward model is, for instance, then I can just draw a bunch of images from that generative model, and I can multiply each one by A1 to get sort of simulated observations. And then I could just train a reconstruction network based on that. So it sounds like a totally sensible approach, which is why you might wonder, like, why don't we just do this? But the fact is that it really works very poorly. So here on the first column, we've got a collection of ground truth images. And the result of our method with this model adaptation, both for deblurring and for super resolution. And in contrast, the result of using this generative model-based approach. And ultimately what's going on here is that these generative models, although powerful, are just not good enough to learn the distribution of images to the degree necessary to really do well in this problem. Okay, so now we can finally get to the approach that we're proposing. And in fact, we've got two different approaches. The first one is perhaps the most direct. So what we're doing is we're saying we've got this basic model that we've already trained using our old forward model. So we're going to plug in our new forward model A1, so parameterize our, using A1. But in contrast to some of the naive approaches that I described before, we're also going to allow ourselves to use the calibration data to perturb our neural network parameters. So not only are we going to use the new forward model, but we're also going to take these calibration observations to somehow update our neural network weights. And so we can pose this as an optimization problem where we say, let's take all of these calibration samples. So remember I said we just have some example, say K-space measurements in an MRI setting without knowing what images they correspond to. And what I want to do is I want to figure out the perturbation delta that's going to be small, but which is also going to ensure that I can adequately reconstruct images corresponding to this calibration data. Okay, so we're going to see how that works in just a second, but I also want to present a second approach. And to get at that, I think it's helpful to look at this image here. So in orange, we've got this space of what I'll call ground truth images. So you can think about these as like the MRI images that we care about. And what we're actually able to observe is either in the purple space or in the green space. So we're either collecting, say, K-space measurements for the first MRI scanner setup or measurements for the second MRI scanner setup. And so what we've been talking about are trying to learn mappings from Y to X. So we've got our original reconstruction network, F0, that goes from purple to orange. And we're trying to come up with a new reconstruction network, F1, that goes from green to orange. And this is sort of what this method I just described is basically learning. So the second method says, well, let's imagine that I could actually map from my new MRI measurements to the MRI measurements I might have had if the scanner had been set up differently, as I had trained for. And once I do that, then I can leverage the fact that I've got a really good F0 here that can get me to the orange space. So I'm going to kind of take this shortcut through the purple space in order to try to get good image estimates. And this is the basic idea behind our second approach, which we call condition incorrect. So inside here, we've got our original reconstruction network that we trained for with our original training data. So the first thing we're going to do is condition. So in particular, remember, we want to take our measurements from the new set forward model and map them to what we think the measurements might have been with the old forward model. And the particular way we're doing this is we're taking our new Y, we multiply it by the pseudo inverse of A1, and then we multiply it times A0. So that's our conditioning approach here. Now, this isn't going to be perfect, and the reason it won't be perfect is because of this sort of null space issue that I referred to earlier. And so what we're going to do is then we're going to correct that initial reconstruction by training a neural network to just correct whatever mistakes are being made by the top branch. And so we can, again, cast this as an optimization problem where we try to learn the parameters theta of this correction network that, again, ensure that we have a good fit to our calibration data, our measurements for our new forward model, and that ensures that we're not, overcorrecting or, doing something drastically different. Okay, so here's some numerical results. So we're trying here 4 different methods. First is just this baseline where we trained for exactly the right forward model from the beginning. And then green is sort of the naive approach where we trained for the wrong forward model, and we're going to ignore the fact that we ever trained for the wrong forward model and just blindly plow ahead. And then we've got our first method, parameterize and perturb, and our second method, condition and correct. And so what we're seeing is in these bar plots results for the PSNR results for a number of different problems. So first we have got motion blur, and we tried 2 different ways of learning how to do the reconstruction, one using a UNet and one using a method called modal that's considered among the state of the art for MRI in particular. In addition to looking at motion blur, we looked at super resolution and MRI reconstruction. And what we can see kind of across the board is that these model adaptation methods that we're proposing are nearly as good as what we could get if we knew the right forward model right from the start. And often that's significantly better than what we could achieve if we ignored the fact that there'd been some model drift. Okay, so let me show you a couple of pictures just to give you a little bit of anecdotal evidence. So this is an MRI reconstruction problem. And classical methods in this space would include just taking an inverse Fourier transform or doing some total variation reconstruction. And you can see with both of those classical images that you get, or classical approaches, that you get really large residuals. There's a lot of error and distortion in here. So here for that same problem now, we can see what we're able to achieve with these learned networks. So again, I'm trying both a UNet and modal, and then I'm showing residual or error images just to kind of highlight where artifacts might be. We've got sort of the best case scenario where we train for the right forward model from the beginning. We've got the naive approach, which is absolutely terrible. And then we've got R2 approaches, which yield significantly smaller errors.
Okay, you have a few minutes left.
Oh, great. Yeah, I'm almost done. These methods can be generalized to optimize for an unknown new forward model. So everything I've shown you assumes that we know it, but it's pretty straightforward extension to having it be unknown. And the same kind of things occur in terms of the numerical errors when we learn A1. I also just want to kind of briefly mention another sort of approach that maybe some of you are thinking of, which is to say, why don't we just try to use data augmentation? So if I know I'm going to do deblurring, for instance, but I don't know exactly what blur I'm going to have to cope with, why don't I just train for a whole library of different blurs simultaneously? Wouldn't that work? Like, do I really need to learn something specific for a specific blur? And the answer is that, yeah, this augmentation approach really does not work well. So in this plot here, what I'm showing is, first of all, the straight lines correspond to the performance of our methods with this model adaptation. And the green and the orange correspond to these data augmentation approaches. And we can see that almost uniformly, doing data augmentation gives you much worse errors than if you were to use these model adaptation approaches that I'm proposing here today. And if we go back to this null space argument, you can kind of see why, right? So the blue is sort of what we originally trained for. And so when we're sort of now having to figure out how to solve problems in the orange space, well, we only have to kind of figure out how to handle problems that are not in the intersection, the purple. Whereas in contrast with model adaptation, we just have to learn to do everything all at once. And that takes quite a bit more data. So with that, I'm going to conclude and just open it up for any questions. Thank you very much.
Right, thank you. Thank you for the very nice talk. If we have questions, something in the chat. No, it's an old question.
And Marina, I have a question. Maybe I can just go ahead instead of typing it in.
Sure.
Becca, thank you very much. Wonderful talk. If you're going to go the sort of the learning route, is there a reason for restricting to linear mappings, linear forward maps? So can you make it open to some nonlinearity?
Yeah, that's a great question. So in general, yeah, you can make these things work with nonlinear mappings. And in fact, there's a whole community of people who are studying things like using neural networks to solve PDEs. And we can kind of think about that as sort of a nonlinear inverse problem. We had focused on the linear models in part because in some of our earlier work in this space, we were really just thinking about how to do the reconstruction without this model drift. For the linear case, we were able to actually prove some things about what was happening that we weren't able to do in the nonlinear case. So we thought it was a pretty interesting case study that gave insight to a lot of good practical problems. Now, all that said, when you start working with nonlinear operators, I mean, depending on how you set up your problem, things can get kind of trickier, especially as you try to figure out how to do the back propagation and make that stable and that kind of thing. So there's some kind of practical challenges that arise when you start working with nonlinear models that we also did not have to grapple with here.
Thank you.
All right, thank you. Thank you again, Rebecca, for the very nice talk.
No, thank you. And thanks again for the invitation.
And I think we can switch to the last speaker, Xiao Wang, Professor of Statistics at Purdue University. His research interests are in artificial intelligence, machine learning, non-parametric statistics, big data, and reliability. And today he's going to talk on challenges in generative models and latent variable models. Welcome.
Okay. So first, I would like to thank Anuj and the committee for the invitation and organizing such a wonderful workshop. So in the morning talks, there are already a lot of fantastic introduction on generative models. So in the first part, I would like to add a little bit more details. So hopefully it can attract more statisticians to get into this field. That's whether you believe deep learning or you don't believe deep learning. The generative model is an interesting topic. First, the purpose of the generative model. So given the training data, generative model basically is like, can you propose a model which can generate new samples from the same distribution? For example,
Now, are you advancing the slides? Because we are still seeing the cover page.
Oh, I already go to the second page. What happened?
Try maybe to unshare and share again.
Let's see. Can you see the second page?
Yes, now we do.
Okay, probably I don't need to use the full screen. That's probably. Okay. So the left panel is the original MNIST data. So this is the training data. So you're supposed to get a model. So in this model, if I do sampling, hopefully, so your sampling images will be similar to the training data. So that's the purpose of generative model. This is nothing new to statisticians. This essentially is a density estimation problem. Okay. So, but for the density estimation problem, we need to be careful. There is an explicit density estimation problem versus implicit density estimation problem. So for statisticians, we are more familiar with, for example, kernel density estimation. So that belongs to this category. Okay. Usually for more complicated high dimensional data, actually implicit density estimation is more favorable. So the Nobel Prize winner, Richard Feynman, that's famous said, "What I cannot create, I do not understand." I think that this also can serve as a philosophy for our statistical data analysis. So for example, if I give you a data set, I mean, if you try to understand the data set, the easiest way is like, can you reproduce this data set to build a generative model? So for in statistics, this is also related to high dimensional data analysis. In particular, nowadays, the image data, they're all high dimensional. Now for generative models, they belong to unsupervised learning. So for this talk, let's not related to the label information. Okay, just observe the information about a random variable X. Another feature is like a latent representation. So this is related to latent variable model. This is how to do dimension reduction or embedding. Okay. On the other hand, the generative model can solve a lot of challenging tasks. So that's quite interesting. Okay, so many challenging tasks can be solved by generative model. For example, the artwork. I think these days they're already selling like the GAN generated artwork in eBay. Okay, also super resolution, the NLP, also cyber security. For example, for this picture, I think it's get from the deep fake. Okay, essentially they can produce the video with anybody's face, speaking anything. Okay, how to detect this kind of fake video or images or news? That's a very serious problem now. Okay, so this is randomly generated like a bedroom image. This is another famous data set we'll talk about later. It's called a Cerebral A data set. This is a generated image. So the current generative model framework. So I summarized there's 3 main frameworks. So they're called generative adversarial network. So again, this is variational autoencoder. This is flow models. Of course, there are other models. Okay. So this picture doesn't mean GAN is more important than other models. That's not what I mean. So that basically means most current literature, they are talking about GAN. Okay. Also, there are a lot of interesting work belong to this category. For example, our friend, Professor Yin Wu, has a lot of interesting work on energy-based model. Now, let's briefly mention what's the idea behind each of these generative models. Okay. For example, the GAN, this model, I think the idea behind it is very smart. Okay. It's not that statistics, I can say. Okay. So they changed this estimation problem into a 2-player game problem. So I have the training data. I have the generative data. So the generative data, how to generate data? As the input is a random noise. Usually is a standard normal distribution. You send a standard normal random variable into a neural network. You get a generated sample. Okay. Now you try to build a discriminator. So discriminator try to make a difference between true samples and the fake sample. So this discriminator try to compete with this generator. So that's essentially the idea behind the GAN. Okay. Another popular method is VAE. So this method I think is more statistics, let's say. Okay. So for this model is built on top of likelihood inference, essentially. Okay. So this model, they introduce something called the encoder. So encoder means what? My input is X. I will send this X to the latent space. So in statistics, what they are trying to do, they're trying to approximate the posterior distribution of Z given X. Posterior distribution of Z given X. But for VAE, they fixed this approximation to be normal. So fixed to be normal. So that's a VAE method. Another method is even more statistics. It's called the flow-based method. The flow-based method, my input is standard normal. Again, standard normal. This standard normal is transformed by a serious invertible neural network. So hopefully, after this transition, my distribution is similar to the data distribution. So this is the idea of this generative model. Now, a little bit math here. So for the GAN model, my data has a distribution, let's say PX. Okay, so I have a generative model. So this is GZ. So Z follows standard normal. So GZ follows some PG. So this is a generated distribution. Now, for most GAN models, they needed to define a divergence or distance between these 2 probability measures. So it's PX and PG. So this formula summarizes most divergence. Okay, so this, for example, includes the GAN model. It's called the Jason-Shallon divergence. Also, we will talk about the Wasserstein distance. Also, is included in this formulation. Okay, so I try to minimize with respect to this G, minimize this divergence. Okay, this is the definition of the divergence. For the VAE model, the problem is like they are using this normal distribution to approximate the true posterior. But this mean variance component, they try to model it by neural network. The likelihood function can be written as these 3 terms. It turns out the first 2 terms can be written down explicitly or can be sampled efficiently. Now for the last term, it's a difference between true posterior and the normal, this approximation posterior. Somehow this term is too hard to handle. Now they just ignore this term. If you ignore this term, it becomes not the exact likelihood inference. You try to maximize the lower upper bound of the likelihood. So that becomes a variation approach. The flow-based model, this is a baby statistics. Okay, it's a baby statistics. Basically it says X is GZ. So G is invertible. So Z follows normal distribution. Now, what is the density of X? That's what we learned in undergraduate statistics. Okay, so since G is invertible, we can write down the density, log density function of X explicitly. Once I have this density form, I can use the likelihood approach. So that's the idea of this flow-based model. Okay, now what are the common challenges for this generative model? Okay, for example, for this GAN, we know the training is very unstable. Since there is no, for example, there is no guidance, there is no like a label information. The training is not stable. Okay, the mode collapsing problem. So mode collapsing, based, for example, for the MNIST data, essentially we have 10 modes. This is a handwritten digit from 0 to 9. Okay, so many times the GAN probably only can generate, let's say 1 or 5. They will always miss 0 or 9. This is called a mode collapsing. Okay, for the variation autoencoder, the target is to maximizing lower bound of the likelihood. I think for most statisticians, they don't like this idea. They would like to have an exact likelihood inference. Okay, so also because of this normal approximation, the quality of the generative sample usually is not very good. Okay, they are very blurry. For the flow model, we know the dimension of the latent distribution is too high because you wanted to use the invertible neural network. So the latent distribution is the same as the data distribution. That's a bad thing to do. Okay, in particular nowadays, the images they are residing in a low dimensional manifold. So this approach has some problem. Also, how to develop invertible neural networks, that's also an interesting problem. Nowadays, they have coupling linear layer to develop a neural network. How powerful, how representative it is, that's also questionable. Okay. Here I borrow an image, a picture from this paper. Okay, this paper. This is a very interesting image. Okay, what it says. It says like I'm gonna train a model, generative model on fashion analysis. Okay, so that means what? I will get a density function. It's used a flow model. I will get a density function from fashion analysis. So this is this blue picture. I try to evaluate the density value for each image. This is a H-square. I will test this same density function on MNIST. So this is a red image, red picture, H-square. It turns out this red one is larger than this blue one. So that basically means what? Fashion MNIST and MNIST, they are totally different images. So you have 2 random variables. They don't share the support. You have random variable X, random variable Y. They don't share the support. Now I have the density for X, but you use the density of X to evaluate the density to evaluate Y. The value is much larger. I will leave this problem to graduate students to think about why this happens. Because in the general statistical theory, that's impossible. You have two random variables, the support, they are mutually exclusive. Somehow, if you evaluate the density of another random variable, the value is higher. So the graduate students can think about what happens. If you don't know, send me email. So for the generative models, there are a lot of other challenges. For example, how to check performance. This is essentially in statistics, that's a hypothesis testing problem. Okay, do you believe my generated sample belongs to the data distribution? Can you provide a score? Of course, there are a lot of existing methods, such as FID scores, inception scores. Okay, but more or less to statisticians, it's a little bit ad hoc. Okay. How to learn the intrinsic dimension of the data? That's also a very interesting but a challenging problem. So the latent space, how to choose the dimension? Of course, at the same time, I would like to have a generative model. Okay, how to perform out of distribution detection? So I give you a new image. Can you tell me it belongs to the same distribution or different distribution? The challenge, as you can tell, because you only observed one class. Now, how can you get information from different class? Okay, so does a neural network, a generative model, really know what they don't know? Essentially, that's a question. So in the next, I will present one of our recent developments in this direction. I cannot solve all the problems, but I try to solve some of the problems, such as mode collapsing problem. So this is called inferential Weierstrass GAN. Okay, so what's new? Okay, so basically my idea is can we propose a model which provides a unifying framework combining the best of VAE and GAN in a principal way? So I like some good things about VAE. For example, the encoder part. With the encoder, that basically means I will map all the data set into the latent space. So that means my training will use all the data information. That will prevent mode collapsing. So encoder is a good part. Okay. For the GAN, of course, this training procedure of the GAN is interesting. It will give you the generated image. Okay. Now, before I answer this question, I would like to answer another important question. Do there even exist these two mappings? For example, this encoder and the decoder for any high dimensional random variable. This QX will follow standard normal. The G is the generator. GZ follows the distribution of this X. So this will answer the existence of the encoder and the decoder. Okay. If it even doesn't exist, why bother to propose different algorithms? Okay. There's some other questions, like is there any probabilistic interpretation, such as everybody likes MLE. So we have a maximum likelihood interpretation. Okay. So to combine the VAE and the GAN is not new. There are a lot of development in this direction. Okay, I will not talk about the details here. So the big picture, the main idea is like this, right? So you have a standard normal random variable. You send it to a decoder. This is the generator. Okay, somehow it becomes the generated image. What's your hope? You hope this guy, the distribution of this guy, is similar to the distribution of this guy, X. That's your data. Okay. On the other hand, you have your data. You send your data to the encoder. So that means you will send your data to the latent space. Okay. So this is your latent code. So the latent code you send it to decoder, generator. This will be called the reconstruction. So now, what's your hope? You hope the generated distribution is same as the data distribution. You hope the decoder distribution is same as the normal distribution. You also hope the reconstruction is the same as the data distribution. Okay, so that's a target. how to make these three objectives in the one framework. That's the issue. I cannot just ad hocly define the distance. That's also, of course, possible. Okay. Now, for the first part, I'll give you the existence result. Okay, existence result. So this existence result basically says what? Give me a continuous random variable x. So this is a random variable, random vector, continuous random vector x. I will assume this x resides in a low-dimensional, d-dimensional, smooth Riemann manifold. So it's in a low-dimensional manifold. Okay. So I can show there exists two mappings. So this Q will map x into the Euclidean space. This G from the Euclidean space back to x. Now the dimension of this Euclidean space is related to the Riemann manifold. Okay, the result is what? This Qx will follow a multivariate normal distribution with zero mean and identity covariance. So standard multivariate norm. Also, this G star Q star is an identity mapping. Okay, identity mapping. So the theory behind essentially is the Nash invariance theorem. By applying Nash's invariance theorem and some results from coupling, you can show this result. Okay, copula. So that gives us the existence of this result. The next is like how to estimate these two mappings. Okay, how to estimate. So I will switch from the statisticians like a KL divergence, because that's equivalent to the maximum likelihood inference. Okay, I will switch from the KL divergence to the Wasserstein distance. So this Wasserstein distance is a natural geometry for probability measures. Okay, that's essentially for KL divergence. What's the issue here? KL divergence, usually it requires the two probability measures, they share the same support. That's the issue for high dimensional data. If they are in different lower dimensional manifold, it's very hard to ask them to share the same support. But that's not the issue for Wasserstein distance. So for the Wasserstein GAN, the distance between the data distribution and the generative distribution is defined like this way. So this is one Wasserstein distance. So this is x minus gz. This is L2 norm. Now the expectation is taken over the joint distribution between x and z. So that's the distance. You take the infimum. Okay, this is pi. So this is one Wasserstein distance between px and pg. Okay. Now for the duality, this problem, it has a duality form. So the duality form is defined as this way. Okay. So this duality form is easier to work with because this expectation, I just replace it by empirical sum. This normal, I can sample as many as I want. Okay. But on the other hand, both are difficult problems because they are constrained optimization problems. This pi is a difficulty. Okay, because marginally you need to require the marginal distribution to be px pz. This one, it requires f to be one Lipschitz. Okay, both are not easy problems. Now, what I observe is like this. The primal variable pi for the primal problem is also a dual variable for the dual problem. The primal variable f for the dual problem is also a dual variable for the primal problem. So the big picture is like what? Can we solve this problem iteratively? Okay, I try to solve the primal problem. I get the primal variable. I will treat this primal variable as a dual variable for the dual problem. Then I try to solve the dual problem. I get a primal variable, then go back. So try to solve these two problems iteratively. That's exactly the idea of the primal dual algorithm. Okay. So I'm also going to introduce the encoder to approximate the posterior, the given x. Okay. Now, if you try to solve this simultaneously, you can get the optimum value for the primal problem. You will get at the end, you can see this is the in-soup form. Similarly, you can get the optimum value for the dual problem is the soup info form. Okay, now I will treat this as my objective function. So this is my new objective function. We call it inferential gain. So this inferential means I introduced the encoder. So this is the distance between Px and Pg. Okay, now if you look carefully, this IW gain objective is equivalent to this form. This one. So this is the upper bound of the one Westermann distance between Px and Pg. Okay, but this upper bound is tight. This upper bound is tight. It's not like a VAE. VAE is not tight. This upper bound is tight. So if this Q star, if you have a good Q star, this upper bound essentially is the same as one Westermann distance. But we gain something Westermann distance cannot give us, is the encoder. So this encoder is critical. So for the time being, we develop some generalization bound for the IW gain. So I will skip this part, the theoretical part. Okay. So for the algorithm, we actually have the very concrete stopping criteria because our method is based on this prime module. This duality gap naturally becomes the criteria for our algorithm to stop. Okay. Okay, so for the numerical analysis, so we start from some toy examples. So this toy examples basically it's a mixture of normal. Okay, mixture of normal. This is a mixture of 8 normals, 20, 25 normal. Okay, it's a toy example, doesn't mean it's easy. Actually, it's not that trivial.
So you have 5 minutes left.
Yes, we're almost done. Yes. So this row, it represents the duality gap. Okay. So this one is a generative sample. The second row, generative sample. Okay. This one is based on the generative sample from the W gain, the famous W gain. Okay. As we can see, in particular for this 25, like a mixture normal example, this W gain totally fails. Okay. It cannot find any mode. We have 25 modes, cannot find any mode. Okay. So for all this simulation, the duality gap actually converted to 0. Our model converts to the true distribution very fast without the mode collapse problem. So we more or less, we can find the corresponding mode. Now the latent space. Latent space, that means I will map the data back into the latent space. Okay, I would like to check how close it is to normal or not. Okay, so visually, these are close to normal. We also use some distance to check how close. So visually, the latent space is very close to the normal distribution. Okay. So now this is a slab A data, right? Slab A is the left-hand side is a W gain, the generative sample. Okay. This right-hand side is our IW gain, generative sample. Okay. At least like visually, the generative sample is much better than this W gain. Okay. We also developed, we also evaluated like by FID score or inception score. So the latent space. So for this data set, the original X space, the dimension is 64 by 64 by 3. Okay. So the latent space in this example, we use the 64 dimensional space. So for each pair, I cannot check like for 64 dimension visually. For each pair of the latent variables, it's more or less close to normal. Okay. But for some dimension, for example, this one is not that normal. Here is interpolation. Okay, interpolation. Interpolation means what? I have 2 images. For example, I can get my face, Anuj's face. I will map both faces into the latent space. Then in the latent space, I can do interpolation. Now I will map it back into the X space. So this is more like how to take an average of my face and Anuj's face. Okay, so this also gives you some indication we can solve this mode collapse problem. Okay, so give me 2 faces. When I do interpolation, that in the middle, they also look like a real faces. So this is a interpolation between 2 images. Now the quality check. So this is more like related to out of distribution detection, or you can see the outlier detection. Okay, so for this kind of outlier detection or auto distribution detection, you can specify two criteria. The first one is reconstruction. So give me a data, I map it to a latent space. Then I use the generator to map it back into the X space. I calculate the reconstruction error. If the reconstruction error is huge, that basically means it's outlier. Other criteria is like you map the data back into the latent space. You use the density of standard normal. Okay, if the density of standard normal is very low, that basically also means that's an outlier. Okay. So for the quality check, we find that these spaces has a high quality score. Okay, these are more like outliers, at least for this Celebra A data set. Okay. So last slide. So we actually compared IWGAN with WGAN, GP, WAE, RE, both visually and numerically. Okay, in terms of reconstruction, generated sample quality, latent distribution. So we think that this IWGAN is a unified framework to fuse the best of VAE and the WGAN. Okay. Now there are a lot of interesting work these days. One, I think there are two directions we can go. One direction is like similar to rejection sampling. The latent distribution can be refined to produce the generative distribution, which is exactly the same as the data distribution. I think this is a recent paper by Benjio's group. Okay, so the generated distribution will always be different with the data distribution. One way you can do something like a rejection sampling idea. Okay, but this rejection sampling idea, you need to do it in the latent space. So this is very similar to Yin Wu's talk in the morning, right? To make the latent distribution to be a energy-based model. It's more flexible. So this energy-based model should depend on the density ratio between the data distribution and your generative distribution. So that's a very interesting idea. Another direction, I think we should solve this problem, like how to adaptively learn the intrinsic dimension of the data manifold. Okay, so for the latent distribution dimension, like I did for Celebra A, is a 64 dimension. How to choose this 64? Why not is 10? Why not is 100? What exactly the latent distribution? Okay, I think that's also an interesting direction to learn the intrinsic dimension of the data manifold. Okay, I'll stop here. Thank you. Yeah.
Thank you. Thank you very much for the nice talk. Let's see if there are questions from those who can talk or the others who could write.
Yeah.
Can I just go ahead, Marina?
Go ahead. Yes, I don't see anything on the chat. Yeah.
Okay, so thank you, Shao. That's a wonderful talk. Also, my personal thanks for presenting the first theorem of the day as the last speaker. So that's refreshing. So you mentioned, I mean, I see this a lot, the use of Wasserstein for comparing distribution, especially for GANs. I mean, it has exploded. And of course, you wrote Nobel Prize and Fields Medal, but that's okay, no big deal. Why is one really interested in using Wasserstein for comparing distribution? What is so natural about it?
I think the comparison is more like between Wasserstein and KL. They try to say that KL is not as good as Wasserstein. That's
I think the comparison is between Wasserstein and Fisher-Rao. I think that's because I understand KL is not even a metric, so that's fine. But yeah. Fisher-Rao can handle the disjoint support. It's very stable. It's fast computing. So I think that's the comparison. But I know all the mathematicians are more excited about Wasserstein. And you okay. said it's natural. So I'm trying to understand. I've asked this to several people.
Natural is cited from Vanani. That's a French guy. that a Fields guy.
Okay. Okay.
So for the Fisher-Rao, I think it can be treated as a good research topic. We can try in that direction. How to hold on. I think I probably already have a GAN model based on Fisher Rao, right? It's not. It's probably it already has a existing literature. I need to double check that.
Well, one of my students did that. I think firstly he did a spherical GAN, and then he used Fisher-Rao metric on a spherical GAN. And I mean, every time somebody does something, you get better results, but results are okay, but I don't think we gained anything more in understanding. So that's what I'm thinking somebody like you can push into. Ultimately, it's a game of comparing distributions or some low-dimensional manifolds.
Yes.
Why is one more natural than other?
Yes, yes,
I think that's a very deep, very important fundamental question that will need to be addressed someday.
Yes, yes. I used to have a student working on that your paper, Fisher Rao, on functional data. Turns out it's too complicated. That guy quit. You know.
The simplest metric on the distribution. It's the simplest.
Yes. Yes. I agree. Yes.
All right. Thank you. Looks like we got to the end of the day. The first day.
Yes, thank you. Thank you very much, everybody. Thank you, Marina. Thanks the speakers for this session. Thank you for all the people who held out. Hey, Ranjan just showed up, so that's good to know.
And thank you.
Hopefully, I assure everybody that tomorrow's sessions are at least as exciting, if not any more. So I invite you to come and attend tomorrow and sit through the session. If there are any feedback, please let us know, and feel free to visit the website.
Yeah, thank you.
Thank you. See you guys tomorrow.
See you tomorrow.
So Shao, I think we should discuss this this Fisher-Rao versus Wasserstein. I feel like Wasserstein is a better thing for this because I think of it as an earth mover, that you are actually moving the peaks from one to another.
Yeah.
I mean, somehow if you have two distributions with different locations of the peak, it's the work done in Fisher-Rao, you have to sort of kill one peak and create another peak.
Yeah.
And so I think there is, in somewhere, there is a nice physical story there.
And also the training, do you have this nice like a duality form for the Fisher-Rao?
I don't think so. I don't think we have because Wasserstein has this sort of matrix structure where you sort of integrate out rows to get one distribution, integrate out columns to get another distribution. That leads to some duality.
That's a primer. Yes. Then there is a duality. That is a primer. Try to match the marginal. Then there is a duality form. Duality form is easy to do large scale data analysis. Okay.
So maybe we should look into it if there is something or if there is not something there.
Yes.
But
the
calculation is very simple.
No. We spend a lot of time in your paper.
That paper was not the Fisher-Rao metric for functional data is different, slightly different from Fisher-Rao metric for probability density.
Okay. I can take a look.
Yeah, I think we can set up a meeting and push this a little bit further.
Sure. Yes. Thank you. Yeah.
Okay. All right. So I think I'm going to close the session. Thank you, everybody, for helping out. Hope to see you tomorrow. Were there any issues that I should know of that I didn't know in terms of people coming in and out or somebody getting logged out? Okay, everything went smoothly. That's good news. Okay. All right. So see you guys tomorrow, 8:30. We'll start the session in the same way. Take care. Thanks, Chao. Chao is here. Thank you very much, Chao. Thanks, Chao.
Yeah.
It was a lot of work for you.
Okay. So tomorrow is still 8:30?
Yeah, same time. I think we have the same 9 to 5.
Okay.
We'll try to come in. I'll try to come in at 8:30 and just do exactly the same thing.
Okay.
Thank you, everyone. Take care.
Okay. See you tomorrow.